Hey everyone, I'd like to warmly welcome you to the AI Engineer Bootcamp, where we'll build the foundations of AI and gradually advance our knowledge to eventually create our personal, exciting AI-powered projects. Developing an AI tool might seem complicated for a newcomer in the field, but let me demonstrate how, with just a few lines of code, we can achieve incredible results entirely from scratch, precisely what you'll learn to do in this course. In this practical lesson, we'll build a chatbot that answers questions about Introduction to AI, the first module you'll encounter in this bootcamp. But I'll set the bar even higher. My goal is to implement the chatbot's backend and user interface in only 5 minutes. Ambitious, isn't it? We'll employ the popular LangChain Python library to implement the backbone of the application and the Streamlit Python library to create an elegant user interface with minimal code. So let's see if creating an app in 5 minutes turns out to be too bold or, in fact, completely achievable. The timer starts now. Our demonstration begins with implementing the backend of our Q&A chatbot in Jupyter Notebook. We've already prepared the transcript of the Intro to AI module as a PDF, so our first task is to load it. LangChain provides just the right tools to make the task straightforward and returns the file as a list of documents. Now, let's split these documents further, ensuring each contains no more than 200 tokens, corresponding to roughly 150 words. This will help feed the chatbot the shortest text possible during the Q&A stage, optimizing the application's cost. Good! Next up, we must transform each document into an array of numbers, also known as vectors or embeddings. This transformation, also called embedding, would later allow our chatbot to quickly find the text most relevant to the question asked. So let's initialize an embedding function by OpenAI to perform this transformation. We'll use it alongside the list of documents to create a chroma vector database that keeps all vectors in a local folder. I'll call the folder Intro to AI. Now, having the vectors at hand, we'll initialize a retriever. The task of a retriever is to find the document most relevant to the question asked. So, if I invoke it with the question, "What did Alan Turing do?" the retriever is expected to fetch the document most closely related to that topic. Let me print the response for a better look. Indeed, we obtain the desired document. The retriever performs flawlessly. Next comes writing the prompts. This is critical in the chatbot creation process because prompts instruct the model about its intended behavior and purpose. Notice the keywords with the curly brackets? They represent input text placeholders, making the prompts reusable. A reusable prompt is called a prompt template. Our templates expect the user's question and the retriever's context. Next in line, we initialize the language model. Let's opt for OpenAI's GPT-4o and set the temperature to 0, ensuring similar answers each run. We also need a so-called string output parser, which guarantees the result will be output as a string. And here's the most intriguing part: implementing the chain, the most important LangChain construction. Its purpose is to link components by passing the output of one as an argument to the next. What we therefore do is store the question and context in a dictionary, feed the dictionary to the prompt template, pass the resulting prompt to the language model, and feed the model's response to the parser, ensuring the final output is a string we can print out. Okay, everyone, let's test the chatbot by asking the familiar question, "What did Alan Turing do?" To stream its response, we must apply the stream function and use a for loop to display each text chunk continuously. The moment of truth. Fantastic! We've successfully streamed the response. Moreover, we can be sure that the chatbot uses the context drawn from the lecture rather than its general knowledge. After all, a response to the same question from ChatGPT would be much lengthier and formatted differently. So, we've just created an extraordinary robot, right? Still, as impressive as it is, we need to wrap it up in a nice package and give it a user-friendly interface. It's time to introduce Streamlit. Our source code starts with essential LangChain and Streamlit imports. The next couple of lines must look familiar. First, we instantiate an OpenAI chat and embedding models. We then initialize a string output parser, a chroma vector store, and a retriever. Note that we'll use the Intro to AI local vector store created earlier. Following that, we have the system prompt, instructing the chatbot about its purpose, and the prompt template, which expects the question and context. Finally, we include our chain. Now comes the Streamlit-specific part of the code. We begin by setting an intuitive title for our application. I'll go with 365 Q&A Chatbot. Let's also add a divider to separate the title from the rest of the elements. Next, create a text input field expecting the question. Let's now check the progress. Type Streamlit Run, add the name of the source file, and hit Enter. Fantastic! All looks good. Now, let's get working on generating and displaying the response. We create a button labeled Ask, responsible for triggering the streaming of the response. If the button is clicked, we proceed with a second if statement to verify that a question has been filled in. If not, we display a warning message. Please type your question. Let's make the warning more visual with an appropriate icon. It's important to sanity check the process frequently. Selecting Ask without filling in a question indeed triggers the warning message. Nice. Continuing the implementation, let's now assume all text fields have been filled in. We therefore create a text placeholder and an empty string that'll shortly store the text. Next, we apply the stream method on the chain object just as we previously did. Inside a for loop, we append each chunk to the string defined earlier and use a suitable Streamlit method to display the string generated so far. And that was the final line of code. Okay, we didn't quite nail the 5-minute mark, but still, I think we performed excellently. And hey, sometimes you've got to let the moment take over. It's now time for the ultimate test. I'll save the file, return to the browser page, and refresh it. Let's finally ask the chatbot, what did Alan Turing do? Selecting Ask, and there we go, works flawlessly. How cool is that? This is the type of project you can build after completing the course. Even if some of the implementation felt a bit advanced, don't worry. That's where the fun begins. You'll quickly pick up all the necessary skills with careful, step-by-step guidance. We'll kick things off by exploring AI's history, key concepts, and those all too familiar buzzwords. From there, we'll dive into a module on Python programming, ensuring you'll have the coding skills you'll need to move forward. Next, we'll discuss natural language processing and large language models in depth. We'll cover essentials like text processing, classification, vectorization, the notable attention mechanism, and how transformers have revolutionized language models. After that, we'll work with the powerful LangChain Python library, learning how to create AI-powered applications seamlessly. As we progress through the bootcamp, we'll reach a module on vector databases. Here, we'll combine theory and practice by conducting semantic searches with the popular PineCone vector database. Then comes an exciting module on speech recognition. In this section, we'll explore the basics of sound and speech theoretically, setting the stage for the practical part where you'll use machine learning and AI to transform speech into text and back again with Python code. We'll wrap up with a fascinating module on applied AI engineering. These lessons will guide you through planning and building an AI-powered tool, precisely an interview simulator for a data scientist position. OpenAI and Streamlit will be your trusty companions on this adventure. And that's the game plan for our bootcamp. So, what are you waiting for? Let's jump straight into the world of AI-powered applications with a module you're well familiar with, Introduction to AI. Enjoy! Welcome to our AI Engineer course, an incredible journey we're excited to embark on with you. To the best of our knowledge, this is the first program of its kind that begins with the basics and guides you step by step. You'll begin with the foundations of AI concepts and Python programming, then progress through NLP programming, and eventually examine large language models, utilizing tools like LangChain and harnessing the power of vector databases with PineCone. But before we dive into the content, let me introduce myself and the team behind this course. I'm Ned, the founder of 365 and a Udemy instructor for a decade. Our courses have impacted 3 million students globally, and it is incredibly fulfilling when these students contact us on LinkedIn or via email to share how our programs have contributed to their professional growth. I collaborated on this course with my colleagues Martin, Christina, Lauren, Eli, and Peter, all of whom have technical data science expertise and computer science degrees from top universities in the UK, Italy, Sweden, and Germany. Creating this program together was a pleasure, and I'm excited to share the content we've developed. Our AI Engineer Bootcamp offers a comprehensive curriculum, beginning with an introduction to the world of artificial intelligence. We'll cover AI mechanics, its various branches, essential tools for AI engineers, and career opportunities in this expanding field. With a solid foundation, you'll be set to learn Python programming. Starting with the basics, you'll gradually enhance your skills, soon writing your own code, utilizing APIs, and exploring web scraping. Next, apply your Python skills to natural language processing, the cornerstone of generative AI. After exploring the NLP module, you'll progress to studying large language models and transformer architectures. In the Programming with LangChain module, you'll acquire essential skills to seamlessly incorporate advanced LLMs into existing web applications. Naturally, we've saved the best for last, a practical case study consolidating the course material and showing you how to apply LLMs effectively. To get the most out of your journey, please don't skip lectures. They progressively enhance your understanding. Starting from the beginning is crucial. It establishes the foundation for tackling advanced topics later in the program. Many of our lessons contain downloadable resources to help reinforce what you've learned. Course notes, exercise files, PDF materials, and handy notebook files are included for easy download. I strongly recommend completing all the exercises. They're crafted to provide practice and enrich your AI engineer skills with additional information. Complete 50% of the course and announce it in the Q&A section to receive your gift, exclusive access to the ChatGPT for Data Science course, delivered via a secret link. Feel free to post in the Q&A section if you have questions, encounter difficulties, or want to share with the community. We are always happy to hear from you. I hope you share my excitement. Let's dive right in and begin this journey together. Here's someone driving on the highway. Another solving complex math, a man crafting poetry, and a girl mastering music. These are just a few examples of natural intelligence, demonstrating our inherent capacity to acquire and learn new skills. But we don't come into this world with all these abilities. Learning them takes time. Fortunately, nature has equipped us with the right tools. Our brains are designed to observe and process vast amounts of information. This is how we learn and become more intelligent than yesterday. The Oxford Dictionary defines intelligence as the ability to acquire and apply knowledge and skills. We don't often appreciate how sophisticated our brains are. The technological innovations created by human intelligence today look like magic compared to the tools available just a few centuries ago. One of our greatest strengths as humans is that we are tool builders. Throughout history, we have repeatedly found ways to boost our productivity. One such way involved the creation of machines. At first, such machines looked like this. This is the Gutenberg's printing press, which was invented in 1440. If we had to rank the most incredible machines of all time, the printing press would likely claim the #1 spot because it revolutionized how we share knowledge. But for all its brilliance, we can't say that this is an intelligent machine, right? This device operated under fixed parameters and couldn't acquire and apply knowledge and skills. It took centuries before the notion of intelligent machines came into existence. Computer scientists, inspired by natural intelligence and human brain processes, envisioned imparting such intelligence to machines. The new field of study aimed at achieving this goal is known as artificial intelligence, or AI. Let's briefly explore the significant advancements AI scientists have made in their pursuit of artificial intelligence. In 1950, the renowned British mathematician and computer scientist Alan Turing asked, "Can machines think?" in a scientific paper. This wasn't the first time someone had asked this question, but Turing's significant contribution was to move the discussion from theoretical and philosophical to practical and experimental terms. He described an explicit criterion, later called the Turing test, for evaluating machine intelligence. In the Turing test, a human interrogator engages in a natural language conversation with one human and one machine, both hidden from view. If the interrogator cannot reliably tell the machine from the human, the machine is considered to have passed the test and exhibited human-like intelligence. This set the stage for modern computational approaches to AI, making his inquiry into "can machines think" a pivotal moment in the history of artificial intelligence. Then, in 1956, the term artificial intelligence was coined at Dartmouth Conference, and AI became a formal field of study. Participants at the conference agreed to bring together experts interested in neural networks, the theory of computation, and automata theory to explore if machines could simulate various aspects of human intelligence. As you can see, scientists have taken inspiration from human intelligence and aimed to impart it to machines from the very beginning. The AI research community has faced many challenges. The 1960s and 70s are known as the AI winter. Technology and data availability limitations reduced funding and interest in AI research. AI didn't make big headlines for decades, until 1997, when IBM's Deep Blue defeated world chess champion Garry Kasparov. Computer power surged in the late 1990s and early 2000s, and the Internet rapidly expanded worldwide. Almost overnight, the necessary ingredients were in place. People worldwide were churning out massive volumes of digital data, and computer processing capabilities skyrocketed. This dramatic shift proved to be a turning point for AI research. It didn't take long before Geoffrey Hinton co-published a paper in 2006 reviving the interest in neural networks with deep learning techniques. Deep learning neural networks are a type of AI that is inspired by how the human brain works. One needs lots of data and high computational power to run deep learning models. So, creating such a model would have been impossible a decade earlier. In 2011, IBM's Watson AI won the Jeopardy quiz show, showcasing substantial advances in natural language processing. AI was able to work with human language. In 2012, researchers at Stanford and Google, including Jeff Dean and Andrew Ng, published Building High-Level Features Using Large-Scale, Unsupervised Learning, a paper that advanced multi-layer neural nets, or deep neural networks. Their system excelled at recognizing cats. In 2017, the Google Brain team developed a fundamental scientific contribution, introducing transformers. This model was a significant breakthrough in natural language processing due to its use of self-attention mechanisms, allowing it to process data sequences, like text, efficiently. Then, just a year later, in 2018, OpenAI released the first version of its GPT series. This generative AI technology utilized transformers to build massive large language models called LLMs. This led to significant enhancements across subsequent versions and introduced a user-friendly AI chat interface, or ChatGPT, in late 2022. If these terms and events seem confusing, don't worry. Everything will make sense as you progress through the course. In this course, we'll frequently talk about AI, machine learning, and data science. Sometimes it might feel as if these terms are used interchangeably, which can be confusing. Let's spend a few minutes clarifying definitions. AI claims to make machines intelligent, allowing them to learn and acquire new skills. Artificial intelligence is a broad discipline encompassing several subfields. Machine learning, one of AI's key subfields, harnesses data to predict outcomes by identifying intricate dependencies beyond mere correlations. Essentially, much like a math function, we feed input data to a model which processes the data in a certain way and produces an output. Consider this practical example. An algorithm can analyze a user's movie-watching history to predict which movies they'll likely enjoy next. Similarly, a customer's financial transactions can be used to generate a credit score that forecasts their loan repayment likelihood. We'll explore various types of machine learning models later in the course. But for now, remember this definition and that ML is a significant branch of AI. And how does data science fit into the picture? Well, AI and machine learning are an essential part of data science. Every data scientist worth their salt can work with machine learning algorithms. But data scientists often use other statistical methods that are more traditional, so to say, such as data visualization and statistical inferences. Often they aim to extract insights from data without relying on ML. Therefore, data science has an essential intersection with AI and its subfield, machine learning, but also relies on math, statistics, and data visualization to gain business value from data. A data scientist can develop a sophisticated algorithm to predict future client orders, but they can also plot clients' orders against store visits and uncover valuable business insights. In our last lesson, we discussed a machine learning algorithm that predicts movie recommendations from your viewing history. We described this as a form of artificial intelligence, but we can agree that this is limited intelligence. The machine can perform a specific task that it's been designed to do. We call this type of artificial intelligence narrow AI. This type of AI is already integrated into our daily lives and has proven valuable for businesses. When OpenAI released the ChatGPT and ChatGPT 3.5 models in 2022, we saw one of the first successful attempts at creating semi-strong AI. Everyone who has tried ChatGPT knows that it can handle a wide range of tasks. It can even generate responses often indistinguishable from those a human might provide, which is what Alan Turing envisioned with his imitation game, remember? We've reached a point where an AI can successfully pass the Turing test. Today, ChatGPT can write jokes, proofread your text, recommend the best course of action, read and create pictures, create Excel and Python formulas, and solve math tasks. So at the very least, we can call this a semi-strong AI. OpenAI, Google, and other top AI research institutions have yet to achieve artificial general intelligence, AGI. Sam Altman, OpenAI's CEO, defines AGI, also referred to as strong AI, as the most powerful technology humanity has ever created. AGI will generally be more intelligent and capable than humans in several tasks. Many believe that for an AI to be considered a GI, it should be able to create science on its own. This means using all collectively available knowledge to make new discoveries and ideas. How close are we to achieving strong AI? Perhaps pretty close. Sam Altman states AGI could be developed in the reasonable, close-ish future. As we edge closer to this frontier, we must consider the immense potential and ethical implications of creating machines that can think, learn, and even create science better than we do. Okay, we are doing great. In this part of the course, we'll discuss data, the main ingredient needed to create an AI model. There are two main types of data: structured and unstructured. As the name suggests, structured data is organized into rows and columns. If I want to see how many sales transactions there have been this month, I can create a nice Excel spreadsheet with rows and columns and put the data in it, which then takes the form of structured data. Unstructured data, such as text files, images, videos, and audio files, lacks a defined structure and cannot be organized into rows and columns. 80 to 90% of all the world's data is unstructured data. This means that most data doesn't have this simple row-column predefined field structure. In the past, structured data was considered more valuable because it was easier to analyze. But AI advancements today have found a way to turn unstructured data into valuable insights, with companies like Meta and Google excelling in this area. Analyzing unstructured data is opening up enormous opportunities for businesses. They now have billions of photographs, video footage, text messages, and emails. For the first time, they can use this information to gain unprecedented insights. But how have AI scientists made sense of so much unstructured data? We'll talk about that in our next lesson. Thanks for watching. Hey everyone, welcome back. The MNIST database is the Hello World example for students who want to learn machine learning. The dataset includes 70,000 28 by 28 pixel grayscale images of handwritten digits. This exercise aims to train a machine learning algorithm to recognize the numbers we have in an image, even though they're never the same because people have different handwriting. If you write the number 3, and I write the number 3, we'll have similar but slightly different versions, right? So how does the computer distinguish between images of 3, 6, or 9? It boils down to the fundamentals of computer science and electrical engineering. All information can be broken down into zeros and ones. Here's how this happens. The handwritten number 3 can be represented in the following way. Each pixel in these images has a value between 0 and 255 that describes its shade of gray, where 0 is white and 255 is black. In computers, all information, including these pixel values, is stored in binary form, using combinations of zeros and ones. When we consider the pixel values in MNIST, or any digital image, these numbers are converted into a binary format, so computers can store and process them. So we see different pictures of the number 3, but they are pictures with similar number sequences for the computer. To solve the MNIST task via machine learning, the computer is trained to identify and differentiate these numerical sequences, enabling it to recognize digits from 0 to 9. This example is fundamental because it shows how we can turn different types of information from the world around us into data that computers can read. Similarly, videos are thousands of pictures composed of hundreds or even thousands of pixels. Each pixel, in turn, corresponds to a number represented in binary form, with only zeros and ones. Even sound and written speech can be represented as sequences of zeros and ones. This is how computers receive the necessary structure to learn. They use this information to find patterns, study similarities, and ultimately learn how to execute different types of tasks. We don't always appreciate how remarkable human brains are. We can see the world around us and collect a lot of information simultaneously. Our minds process countless details subconsciously, using our senses to absorb what we see, hear, and taste. This complex system allows us to understand and respond to the world, helping us to interact meaningfully with everything around us. AI researchers aspire to provide machines with such capabilities, utilizing tools that collect data through sensors, video, audio, texts, social media, satellite images, and internet browsing patterns. They gather information by scraping the web, accessing APIs, and harnessing big data analytics. This wealth of data enables them to train algorithms, refine machine learning models, and enhance artificial intelligence systems to better understand and interact with the world. Data scientists often say, especially when building AI models, garbage in, garbage out. High-quality data input ensures excellent model output. Hi, welcome back to our AI modeling lesson. Two primary methods exist for collecting and preparing data for AI modeling: labeled or unlabeled data. Imagine you have a data set of 10,000 photos featuring various animals, including dogs. Before any modeling begins, someone meticulously reviews each photo, classifying them as dog or not a dog. This process creates a labeled dataset. Of course, this concept can be applied when working with pictures and for text, audio, video, and other data types. Now envision a collection of YouTube comments. We can classify comments as positive, negative, or neutral to train a model that categorizes new platform comments and flags harmful ones. Manually labeling is undoubtedly time-consuming and expensive. So why go through all the effort? The advantage is that in the end, we'll be able to train an AI model with high-quality data that can significantly improve its accuracy. Models typically trained on labeled data are more reliable and perform well in real-world applications. But a clear trade-off is the time and resources spent labeling data versus model performance. The other option is to work with unlabeled data. Today's machine learning advancements allow us to work with unstructured data, such as images, video, text, and unlabeled audio. This means feeding the dataset of 10,000 photos before going through every picture. In this case, we leave to the AI model to learn on its own. We'll explain the learning process in more detail later. For now, you must be able to tell the difference between labeled and unlabeled datasets. Thanks for watching. Okay, check this out. The main reason for the advancement of AI in recent years is the rapid digitalization of our lives. The growth of online shops, mobile phones, cameras, social media, sensors, and the Internet of Things devices has led to an exponential increase in data generation. Today, we enjoy access to not only more data, but also significantly higher quality data. Consider the sharp contrast between photographs you took with your older phone several years ago and those taken with your smartphone today. This surge in high-quality data has significantly fueled the development of AI. But how do people recognize and make sense of the ever-growing ocean of digital data? Much of this data is unstructured and too voluminous to label. Metadata proves invaluable here. Every dataset should include it. Metadata is data that describes other data. It summarizes key details like asset type, author, creation date, usage, file size, and more. Here's what the file's metadata for this lesson looks like. In our example with the dogs dataset, each photo includes metadata detailing its name, capture date, photographer, file size, and more. Whether you handle structured or unstructured, labeled or unlabeled data, it's essential to include metadata, especially in large datasets and complex systems. Hi, and welcome back to the Intro to AI module of the AI Engineer Bootcamp. In this section of the course, we will start talking about the different types of machine learning. But first, I would like to ask you a favor. I would be really grateful if you could go to the course dashboard, which is very easy to do, and click on Leave a Rating. This will mean a lot to me and will help other students know that this course is worth taking. The reason I'm asking you to do this now is that this is a large course, and most people do not complete all the lessons in one sitting, eventually forgetting to leave a rating. So, please do it now. It should only take a couple of seconds, and it will really validate our efforts. Thank you so much for this. Okay, having said that, let's continue with the Intro to AI module. Okay, great. So far, we've explored AI basics, its history, and the distinctions between weak and strong AI. You already learned about the key ingredient to building AI, high-quality, abundant data. We're making excellent progress. Next, we should explore machine learning, the AI subfield pivotal to its recent success. The idea of ML is fascinating because it boils down to designing a system capable of learning and improving through a trial and error process. Consider building a machine learning model similar to a student taught by a teacher. In this case, the machine learning model is the student, and the data scientist is the teacher. The teacher's role is to help the student learn how to solve problems. To do this well, the teacher must provide the student with many suitable learning materials, which in the world of machine learning means providing a lot of good data. With sufficient information, the student carefully studies and absorbs the training materials. Similarly, the machine learning algorithm learns to recognize patterns in the fed training data. The aim is to prepare students to succeed on their final exam, featuring unfamiliar questions that test previously covered material. In the ML model's case, we aim to teach it how to solve a particular problem with data it has never seen. The more up-to-date and better the training data, the better the model can solve new, challenging problems it has never seen. Without adequate training, a student may underperform compared to a well-taught one, regardless of natural talent. The same goes for machine learning. A simple model with lots of good data might do better than a more complicated one with less data. Adopting new teaching methods and tailoring styles to students can significantly enhance their performance. Similarly, in machine learning, models improve prediction and analysis as they encounter new data types and updated algorithms. This continuous learning and adaptation process is crucial to developing robust AI systems that can handle diverse challenges and evolve. Just as some students excel in problem-solving across various fields, certain ML models are better suited to specific ones. The data scientist needs to understand this and be able to use the appropriate ML model in a given situation. I hope this somewhat abstract example was helpful. Let's give a more practical example of how ML can help businesses. A real estate agent plans to develop a mobile app to provide prospective clients with an estimated selling price for their homes. Users can receive this estimate by answering targeted questions within the app. This could significantly boost the real estate agent's business by enabling them to collect contact details from people interested in selling their property. To put the plan in motion, the real estate agent contacted a data scientist and asked whether the project was feasible. The data scientist's first question regarded the availability of a sufficiently large list of past transactions. Fortunately, the real estate agent's company had access to a database with thousands of past transactions over the last few years. Later, the data scientist was pleased to find the data well organized, detailing house prices, sizes, room counts, bedroom numbers, distances from the city center, neighborhoods, and other fascinating aspects. "I can build an ML model with that," said the data scientist. Here's how the data scientist simplified the model for his client. You're familiar with the classic function notation where y is a function of x, right? Imagine we want to develop a machine learning model to predict house prices in our city by analyzing past real estate transactions in your training dataset. So, we have plenty of past transactions where both x and y are known. We need to train a machine learning algorithm with historical data to discover patterns and learn the best way to predict the future price of a home, y, based on the data from past transactions and the home's known characteristics. Clients enter their home's characteristics into the app. This forms input x. The ML model then generates output y, predicting the home's price based on similar historical data. This is where we'll end the story. Spoiler alert, the app was a huge success for the real estate agent's business. I hope this lesson clarified what machine learning is and how it works. In our next lesson, we'll discuss the different types of machine learning models. Thanks for watching. In this video, we'll describe 3 main types of machine learning: supervised, unsupervised, and reinforcement learning. Then, in the next one, we'll explore deep learning, a sophisticated subset of machine learning powered by neural networks and inspired by the human brain. If this sounds too abstract and complicated, please don't worry. We'll talk about the intuition of these AI techniques without getting into too much detail. Supervised learning excels when we work with labeled data. In the earlier example, the training data set reveals whether a picture contains a dog. This is how the algorithm can learn to classify new pictures as dog or not dog. We've provided the ML model with an extensive training data set with labeled data, and it knows what to look for. Later, when we provide a new picture, it can identify whether it contains a dog based on the feedback given during training. This is a classification problem solved by supervised ML. The other primary application of supervised learning is predicting an outcome. Remember when we discussed the real estate agent's mobile app in our last lesson? Well, the dataset with past house sales transactions contained both known prices and features of the homes. We didn't merely highlight home features. This is an example of supervised learning too, but it's used for prediction, also called a regression problem. When a user inputs the characteristics of a new home into the app predicts the new home's price based on its features and historical information for similar homes. So, simply put, in supervised learning, we explicitly train the model with known outputs to guide its learning. In unsupervised learning, we process data without labels. For example, in a data set of 10,000 animal pictures, half feature dogs, and the other half various animals. But we provide the machine learning model with no labels or indications. It will need to scan through all pictures and look for patterns. Ultimately, it will be able to distinguish specific groups and individuate them. We'll have a group of dogs, a group of cats, and so on. The ML model, however, doesn't specify the contents of these images. It merely indicates that they share similar characteristics, grouping them. Unsupervised learning is helpful in many situations. First, labeling data is costly and not always practical. Moreover, sometimes we don't know what relationships we should look for in the data, so it makes sense to have the algorithm find these interesting relationships first. In this way, a supermarket chain could find clusters of target customers with different behaviors, or a real estate agent could use an unsupervised model to determine which types of properties are sold most often. Another key ML type is reinforcement learning, which operates without labeled data and is applied in specific scenarios where the machine figures out how to reach a designated goal. Reinforcement learning shares with supervised ML the understanding of the desired output. We essentially direct the computer to optimize our goal achievement. But unlike supervised learning, we don't provide labeled data to the ML model. Instead, we create rules. The ML model learns through trial and error within specific parameters of our created rules. Reinforcement learning thrives in robotics and online recommendation systems. For example, platforms like Netflix use reinforcement learning to enhance recommendation systems. Unlike traditional methods that rely on labeled data, which indicates which TV shows a user might like, reinforcement learning employs a system where the model learns from user feedback through interactions. Initially, Netflix may provide random show recommendations. As a user interacts with these suggestions by watching a show, adding it to their list, or skipping it, the system gathers feedback. Positive interactions, like watching a full episode, signal the model to recommend similar content in the future, while negative responses, like skipping a show, guide it to adjust recommendations. Over time, the model refines its predictions to better align with individual user preferences, constantly adapting to new viewing patterns and behaviors. All right, so that's the intuition behind supervised, unsupervised, and reinforcement learning. In the next lesson, we'll examine deep learning, a truly fascinating feat of computer science. Deep learning is a fascinating subset of machine learning, inspired by how the human brain works. Here's an AI-generated image. What do you see at first glance? It's a sunny day and a crowded beach, right? Upon closer inspection, we see children playing in the sand around a massive sand castle at the center. We then examine each person on the beach more closely. We find that AI rendered this individual's face oddly, resulting in a bizarre and slightly unsettling appearance. Our brain processes information in various phases and at varying depths. Initially, viewing an image provides a raw, broad impression that presents insights into the scene's context. The more time and attention we devote to details, the more information and subtleties we can process and observe. In the context of deep learning, a neural network processes information similarly. Here's what a neural network resembles. Please don't be scared. Everything will make sense in a second. Picture the first layer as our input information, similar to observing a sunny, crowded beach day. Then, as the data passes through more network layers, intermediate layers start recognizing more complex features, such as shapes or specific objects. Remember how I noticed the enormous sand castle in the middle? Every intermediate layer of the neural network builds a more detailed understanding of the basic features identified by earlier layers. So there's an incremental increase in the level of detail acquired. The deeper layers of the network synthesize lower-level features into high-level features, representing more complex aspects of the input data. This is how we can spot the strange face generated by AI. It took some time to process the information and get to this conclusion. Honestly, I think I subconsciously wanted the picture to reflect that, because I was curious if the AI had produced a quality example. And eventually, my brain focused on this little detail. Okay, perfect. So that's the intuition behind deep learning. It's a complex process that allows machines to learn by processing input information in stages. Let's explore some technical details to deepen our understanding. We call this neural network artificial neural network, or ANN. Biological neural networks inspire it, but they work much differently. Like our senses, an ANN's input layer sends raw data to the brain. Then the intermediate layers, or hidden layers, process input information. Neural networks can have one or multiple hidden layers. Increasing layers enhances complexity. Adding more layers to a network increases its learning capacity, but the downside is that it needs to be carefully managed to ensure effective learning. We also have an output layer that generates the final result. Every layer of the artificial neural net is made of neurons, or nodes, responsible for processing and transforming the information received. If you recall, I previously referenced the MNIST example in one of our lessons. We noted that training a model to recognize handwritten digits involves supplying it with thousands of pre-labeled examples. How does this training happen? While the process may initially appear complex, let's simplify it to a more manageable form. The process starts with the input layer of the ANN receiving an image of a handwritten digit. Each pixel of this image serves as an input node. In the case of MNIST, images are 28 by 28 pixels, so the input layer typically has 784 input nodes. Imagine that the 784 input nodes are stored as a vector inside the neural net to form the input layer. Each of the 784 input nodes contains a number based on how bright or dark it is. Here, 0 represents white, while any value greater than 0 indicates a color other than white. We call this number activation. The higher the number, the darker the content inside a given node. We describe the 784 input nodes in the input layer as the neural net's width, and its number of layers as its depth. Here, the network comprises 3 hidden layers, along with the input and output layers, totaling a depth of 5. We have numerous connections between nodes because each layer's nodes are linked to every node in the subsequent layer. This extensive network of connections is essential for learning from input data, serving as mathematical transformations. These transformations occur through a mix of weights and nonlinear operations, with optimal weight combinations across all nodes enabling learning. This method translates the input via various layers, refining the information before it generates a result. Learning occurs by designing a system that identifies optimal weights and biases to solve a specific problem, involving thousands of repetitions to discover the best combination. So, why do we need several layers? What kind of transformations can we expect in each layer to end up with a system capable of recognizing the digits in a photo? Well, when we see an image in the background, our brain connects various components of what it is made of. For instance, the number 3 comprises 2 elements, a rounded top and a curved bottom. The first hidden layer in our neural network might learn to recognize these features from the input data. Then, in the second hidden layer, we continue to build on the information processed by the previous one. We've identified edges and curves, and now we can use them to discern more complex shapes, like loops and intersections, bringing us closer to recognizing numerals. When the information reaches the third layer, the neural network has learned to recognize the overall shape and configuration representing the number 3. Finally, the output layer takes the processed data from the last hidden layer and determines whether the digit is a 3. This is how a neural network learns to perform what appears to be a simple task, recognizing a number. The underlying process, however, involves intricate mathematical manipulations, which we didn't describe fully. In essence, the layers of an ANN, through their depth and breadth, create a robust system of pattern recognition and data interpretation that mirrors some aspects of human cognitive processes, albeit more structured. This capability to analyze large, high-dimensional datasets and recognize complex patterns with high accuracy makes deep learning a revolutionary tool in AI. It's what has made today's incredible AI advancement possible. Tales of mechanical beings date back to ancient times. For instance, the myth of Talos depicts a colossal bronze man built by Hephaestus, the Greek god of invention and blacksmithing. Tasked with safeguarding Crete, this bronze figure patrolled the island 3 times a day, hurling boulders at enemy ships nearing the coast. In the medieval European and Islamic world, devices like Al-Jazari's automata, including water clocks and programmable machines, showcased early engineering prowess. One of the greatest pioneers of the Italian Renaissance, Leonardo da Vinci, sketched designs of a mechanical knight capable of limited movements, foreshadowing today's humanoid robots, and a mechanical lion. So, the idea of robots and the robotics field is not new. People have been fascinated with them for a long time. It's a true phenomenon in pop culture that has captured the imagination of previous generations. So, what's different today? Rapid technological advancements, and mainly the incredible growth of AI, are making possible the creation of intelligent machines, which we could only imagine and depict in movies in the past. Robotics is the branch of technology that deals with the design, construction, operation, and use of robots. Machines that can perform tasks automatically or with human-like capabilities. Let's break this down. Mechanical engineers are needed to construct robots' physical structures. They are responsible for designing and constructing robots, including their mobility mechanisms. Electronics and electrical engineers design systems that enable the robot to operate and control its actions. While electronics power the system, various types of AI drive the robot's decision-making and behavior. Robots are equipped with various sensors and cameras to collect necessary data and perceive their surroundings. This is how AI developers and engineers pitch in. So, this truly interdisciplinary field requires specialized skills in several distinct areas. Like other types of AI, the robotics domain is inspired by human capabilities. Robots are designed to mimic and augment human abilities. To achieve that, researchers use a multidisciplinary approach combining different AI technologies. Typically, we should consider a system with multiple models instead of a single model that does it all. For example, an autonomous robot might use computer vision for object detection and environment understanding, simultaneous localization and mapping for navigation and mapping, reinforcement learning for decision-making, and a natural language processing model for understanding and generating human language. Combining all these models allows a robot to perceive the environment, make decisions, communicate with people, and act accordingly. Let's point out several intriguing use cases. You probably know that under the direction of Elon Musk, Tesla is building a Tesla bot, which is described as a general-purpose robotic humanoid. The goal is to create a robot that can relieve humans of dangerous, repetitive, and boring tasks in logistics. For example, a Tesla bot could help with factory and warehouse work, moving and stacking boxes, counting and auditing inventory, and lifting weights. And it's not just Tesla. Many companies develop their own autonomous robots and contribute with valuable research. Medical robots are a fascinating use case already in the mass adoption phase. These robots can perform incredibly accurate medical interventions and even complex surgeries, which save lives. There's so many amazing innovations that are becoming mainstream. Self-driving cars, harvesting robots, cleaning robots, space robots, search and rescue robots, security and surveillance robots. The future is here, and AI is at the forefront of all of these innovations. IBM defines computer vision as an AI field that uses machine learning and neural networks to teach computers to derive meaningful information from digital images and videos. Consider this analogy. If AI functions as the brain, computer vision serves as the eyes. As humans, we effortlessly understand our surrounding environment with all its nuances. We can distinguish moving objects, changing shapes, and different colors. Sometimes we can notice the slightest differences and the most subtle details. The study of computer vision is a monumental effort to develop sophisticated AI models that allow computers to comprehend real-world information. To do that, computers consume input through images and videos. Images are simpler because they capture a single moment statically. Conversely, videos are more complex, appearing as continuous sequences of images, for example, 30 frames per second, that require processing. The computer must analyze each frame and understand its context and continuity. There are 4 main families of computer vision models. First, we have convolutional neural networks. CNNs are foundational for computer vision because they are great when working with high-dimensional data. In the early days, AI researchers used other types of neural networks for computer vision problems, but they struggled with high-dimensional data images due to the immense number of parameters required. In contrast, CNNs are great at capturing spatial hierarchies in images. But what does this term mean in plain language? It means that CNNs are great at organizing the elements in an image based on their importance and depth. Imagine looking at a picture where some things seem closer to you and others farther away. The foreground is up close. The middle ground is between, and the background is distant. Larger objects often appear closer and more significant. Overlapping items make those in front look nearer, and centered or top-positioned elements typically attract more attention, enhancing their importance. CNNs are effective at processing information due to their layered structure. This enables the network to learn basic features, like object edges in initial layers, and progressively capture complex, high-level features, such as shapes and objects, in deeper layers. Next, we'll focus on transformers, a key topic in our upcoming discussions on generative AI. For now, we can just say that, in some cases, AI researchers apply transformer architecture to images for the purposes of computer vision. Third, generative adversarial networks, GANs, primarily create lifelike images. Lastly, specialized networks, like UNet, excel in medical image segmentation, while EfficientNet optimizes performance by efficiently scaling neural network dimensions and utilizing computational resources. Computer vision has a ton of exciting real-world applications. Self-driving cars, medical imaging, security, surveillance, and other areas we previously discussed show great promise in robotics. It's important to remember that computer vision does not need to be part of robotics to be an incredibly useful product. For example, consider face recognition software. It's just a model built into a software product without a robotic body. Some of the most exciting advancements in computer vision are currently in virtual reality. revolutionizing such industries as education, entertainment, and long-distance communication. In our next lesson, we'll discuss traditional ML methods. Thanks for watching. Products like ChatGPT, Tesla's self-driving cars, and robots make the headlines. But we should remember that the more significant portion of the value created by AI today is related to less flashy business use cases. Financial institutions use machine learning to detect fraudulent activity or predict a customer's likelihood of repaying their mortgage. Insurance companies use ML to offer more precise pricing for life and non-life insurance packages. Machine learning allows retail companies to predict demand and optimize their orders. E-commerce giants like Amazon optimize pricing and conversions through ML algorithms. They can also predict what product you'd like to buy next based on previous shopping history. The list goes on and on. These and many other use cases have existed for over a decade. Very few businesses fail to benefit from AI. We should remember that while general AI is trendy and promising, the traditional AI applications I mentioned continue to impact businesses and deliver significant value. ChatGPT became a global phenomenon upon its release, sparking widespread excitement about AI's advanced future potential. And the branch of AI behind impressive models like ChatGPT is called Generative AI. Generative because it can generate new data or content. The word generative highlights the system's ability to create something new, rather than process existing data. Every conversation you have with ChatGPT is open-ended. The model, trained on extensive text data, generates new and unique real-time responses. Similarly, providing DALL-E, OpenAI's image generation model, with a detailed description will prompt it to create a unique picture tailored to your specifications. This illustrates the core capability of generative AI, producing novel content by leveraging patterns learned from training data, a common feature among these models. But AI developers can use several different techniques to achieve generative AI, including large language models, diffusion models, generative adversarial networks, neural radiance fields, and hybrid models are also possible. I'll briefly describe each type of these generative AI. Large language models, or LLMs, are the foundational technology behind ChatGPT. I want to provide more details and give you a good foundational understanding of NLP, language models, and the development of models like ChatGPT. To grasp the workings and origins of this vital technology, we've dedicated the next 2 sections of the course to a detailed introduction. LLMs are neural networks trained on vast text volumes, learning to predict word relationships and the next likely word in a sentence. But more on LLMs in the next section. Diffusion models, like DALL-E, are advanced AI tools primarily used for generating images and video. During operation, DALL-E begins with a random noise pattern and progressively refines it into a detailed image, applying requested shapes and learned patterns through multiple steps to enhance realism. Generative adversarial networks, or GANs, introduced in 2014, are commonly used for generating text and images. GANs function by comparing 2 algorithms. One generates content, while the other judges its realism. Through this interaction, both algorithms enhance their capabilities, refining the content until it's nearly indistinguishable from reality. Neural Radiance is a specialized AI for 3D modeling, which emerged around 2020. And lastly, the increasingly popular hybrid approach combines LLMs and GANs into one powerful content generation system. Currently, there's an incredible amount of investment in different generative AI initiatives around the world, with the big tech firms leading the pack. It definitely feels like this is the key AI domain everyone's paying attention to. And how could they not? Generative AI can create and work with content in various formats, including text, images, videos, audio, data, code, design, and 3D. As technology improves, it will significantly impact the corporate world. Therefore, it will be highly advantageous to understand how it operates and how we can be at the forefront of this remarkable innovation. On November 30th, 2022, OpenAI released ChatGPT 3.5, a model fine-tuned for dialogue and trained to produce text. ChatGPT was one of the most successful and impressive product releases ever, so sensational that some called it scary good. Naturally, this brought in many first adopters. Over 1 million people created an account in just 1 week and started using the algorithm. It didn't take long for 1 million users to become 100 million. By January, in less than 2 months, ChatGPT had reached that figure, making it the fastest-growing consumer application in history. It took TikTok 9 months to reach that many registrations. But why is everyone so hyped up about ChatGPT? What's the reason behind this explosive growth? The answer is straightforward. The product is incredible. As soon as people began interacting with ChatGPT, they realized it can help them in their daily work. Everyone can use a powerful AI tool capable of summarizing text, generating responses to highly technical questions, and assisting with any technical task. Whether a student or a working professional, this software can benefit you. The release of ChatGPT 4.0 showed the tremendous leap between different versions of generative pre-trained transformer models. Some of the tasks GPT 3.5 struggled with or provided mediocre answers for were solved impressively by GPT 4.0. This will likely be the case with every subsequent version in the future. Gen AI is here to stay. So in this part of the course, we want to study the nuts and bolts that led to ChatGPT's creation, how it all started, and which technical principles led to the creation of large language models. Stay tuned, and thanks for watching. Natural language processing, more frequently referred to as NLP, is a field of computer science that studies how computers understand, interpret, and generate human language data. NLP came to life around the 1950s. In the early days, the first NLP methods focused on rule-based systems, which used language grammar rules to try to process the text. For instance, in designing such a system, I might establish a rule: treat sentences starting with can you, will you, or is it as questions. Then, when the system processes the sentence, can you help me, it will recognize it as a question. This rule, however, seems quite basic and manual, doesn't it? In the late 1980s, and especially early 90s, statistical NLP emerged, marking a shift from rule-based systems to a probabilistic approach that interprets language data through extensive data analysis. In the 90s, a statistician might have been tasked with designing a program to identify whether can is used as a noun or a verb in a sentence. The difference is very important because, as a verb, can describes a person's ability to do or accomplish something, whereas as a noun, it refers to a container, like a Coca-Cola can. So, back in the 90s, I would have to gather many sentences containing the word can and make annotations whether the word was used as a noun or verb in any of these sentences. This would allow me to perform context analysis by analyzing other words can was used with. For instance, the analysis might reveal that when words like you or I are close to can, it typically indicates a verb. Alternatively, if words like soda are used in the sentence, we most likely have a noun. The final goal of this analysis is to obtain a model capable of indicating the probability of whether can is a verb or a noun in a given sentence based on the frequencies calculated earlier. Attempting to discern patterns in the data in this way seems akin to primitive machine learning, doesn't it? In our next lesson, we'll learn how vector embeddings, machine learning, and deep learning have advanced the NLP capabilities we've witnessed today. Thanks for watching. In the 2000s, NLP experienced a significant boost when statistical analysis made its way to machine learning-led NLP. Vector embeddings were a key facilitator in this process by transforming words and sentences into numerical arrays, effectively capturing the meaning and relationships within the text data. How does this happen? Well, the great thing about vectors is that they can represent more complex types of information, such as text, images, audio, and other types of unstructured data. For example, each word in a sentence can be represented as a vector and stored in a high-dimensional space called vector embedding. When working with AI models, vector embeddings are typically several hundred to thousands of dimensions deep, not just 2 or 3. When working with AI models, vector embeddings are not 2-dimensional, they're not 3-dimensional, but a few hundred or thousand dimensional. As you can imagine, the meaning of something as complicated as human language can't be captured with 1, 2, or 3-dimensional vectors. Instead, we need hundreds, even thousands of dimensions. The key idea is to use embeddings to store and retrieve data based on semantic similarity. So, text data can be represented through vector embeddings, which serve as a critical enabling factor. Moreover, powerful new ML models emerged, enabling computers to analyze extensive text databases as vector embeddings. These models learned to detect subtle linguistic cues indicating sentiment, like sarcasm or irony, nuances previously elusive to basic statistical methods. The emergence of neural networks in the 2010s revolutionized NLP tasks like translation, speech recognition, and text generation. This is because neural networks, with their deep, multi-layered structures, excel at detecting complex patterns beyond the reach of conventional machine learning methods. Transformer architecture, introduced in 2018, is one of the most recent innovations. It revolutionized the NLP field and led to the creation of large language models. This architecture made the development of LLMs like GPT and Gemini possible. In our next 2 lessons, we'll discuss the crucial topic of language models and the transformative impact of transformers. Thanks for watching. As a child, I enjoyed playing a team-based word association game with my friends. 4 players were divided into 2 teams. One player would whisper a secret word to an opponent, who must then say a related word aloud to help their teammate guess the original whispered word. The teammate gets 1 guess. If incorrect, the next team can describe the secret word with 1 word. The first to guess the original whispered word wins. For instance, if I hear banana, I might say yellow to my teammate. But yellow can be associated with many things, including taxis, sunflowers, lemons, or gold. So while there's a possibility that my teammate might guess banana from the word yellow, it's not the most likely outcome. Using the word peel could improve accuracy, since peel is more often associated with the word banana than yellow. There are many yellow things, but peel is frequently linked with banana. Perhaps there are even better associations than peel, right? Anyway, to be good at this game, you must think of the word that maximizes the likelihood of your teammate guessing correctly. Some words may be too complicated, so you'll need a few tries to understand them, providing more context. If I'm given grapefruit, I might need 2 turns. First, citrus, which gives my partner a low success chance. Then, bitter, which ensures they guess correctly. Alternatively, saying citrus and pink also offers a high chance of success. Context is crucial. So why am I telling you this story? This is a great analogy of how language models operate. A language model primarily predicts the optimal word to fill a blank space. For example, if a user types to be or not to be, that is the model would respond question. Like in the word association game, the model fills in the blank with the next most probable word. So language models are probabilistic, capable of predicting the missing word in a sentence based on the context provided by preceding words. We generally have 2 types of language models: masked and autoregressive. Masked language models can guess the missing word regardless of its position in a sentence. So, for example, consider the sentence water, blank space, at 0 degrees Celsius. In this case, the model could use the information before and after the blank space to fill in the missing word, freezes. Autoregressive models predict the next word. They'll use the context of preceding words and guess what should follow. An autoregressive model will be able to forecast that the next word in water freezes at 0 degrees is Celsius. OpenAI's GPT models are autoregressive, which work by conditioning each prediction on all previously generated words. But how can language models predict the next word in a sequence? This is rooted in statistical learning from vast amounts of data. A language model gains the ability to work with language by analyzing and learning from the patterns and structures found in the input text it processes. This involves digesting large datasets containing diverse linguistic styles and uses, which enable the model to recognize and predict likely word sequences in different contexts. Over time, the model builds a probabilistic map of word associations and dependencies, enhancing its ability to generate coherent and contextually appropriate responses to more complicated prompts. The outputs of language models are open-ended, meaning that they can use the vocabulary built by learning from training data to generate an infinite number of possible outputs. The word generate is key, hence the name generative AI. Initially, AI developers focused on creating models tailored to a single language, but modern models are capable of processing and understanding multiple languages. Generally, we discuss language models, though often the focus is on large ones. Obviously, the difference between the two is size. But what size qualifies a language model as large? The term LLM lacks a formal definition and can be used quite flexibly. The term large language model reflects their training on vast data quantities, and this data volume continues to expand over time. So what is deemed large today will not be in a few years. For example, GPT-3 was trained on 175 billion parameters, GPT-4 over 1 trillion, and GPT-5 is likely to use even more. It's believed that the richer the training data for LLMs, the smarter and more versatile they become. In our next lesson, we'll talk about the process of training LLMs and why it's scalable compared to what we had before. Thanks for watching. In supervised machine learning, we provide labeled data to the computer. For example, if we want to train a model to distinguish between positive and negative customer reviews, we could get a dataset of 100,000 customer reviews and manually label them as either positive or negative. The computer will then use these labels and learn how to categorize new unseen reviews as positive or negative. The drawback to this approach is that it's expensive to label data. If categorizing one review costs 30 cents, we must pay that person $30,000 to classify the entire training dataset. Categorizing a review is fairly simple. Can you imagine how much more expensive it would be to sort articles, or novels, and medical records? It wouldn't cost 30 cents, but probably $30 or more. So going through 100,000 data points would cost north of $3 million. Therefore, we can conclude that supervised learning has significant limitations in terms of scalability. The cost increases exponentially with the complexity of the data fed into the model. People often say ChatGPT has virtually read the entire internet. Can you imagine how much labor would be needed to read and categorize the entire web? How biased would the categorizations be if made by just a few individuals? So, large language models need a slightly different approach. The other obvious option is unsupervised learning. This type of ML operates without labels, seeking to discern the data's underlying structure without direct performance feedback. But with this approach, there isn't a clear objective. Without a specific goal, it's challenging for the model to learn structures that help it understand or generate human language. Moreover, language is a form of expression in which context matters significantly. Words in a single sentence can create context, and each paragraph builds upon the last to enhance it further. Unsupervised learning does not prioritize predicting the next word from previous contexts, potentially overlooking essential language nuances. So, we need a balanced approach, an ML system that scales and self-learns, predicts contextually, and autonomously generates labels. The self-supervised learning approach was the breakthrough that led to the creation of LLMs. It analyzes text databases, automatically generates labels, and predicts subsequent content based on contextual cues from surrounding words. This hybrid approach allowed for the creation of models like ChatGPT and improved their ability to understand and generate language in a natural and aware way. Our next lesson addresses the gradual progress of language models that led to the Transformers architecture. This other key innovation allowed AI researchers to work with massive amounts of unlabeled text data. Earlier, we discussed the incredible evolution of language models, from statistical modeling and basic tasks to advanced neural networks and LLMs. In this lesson, I would like to explore the world of language modeling more, adding technical detail to the picture. This will help improve our overall understanding. We'll describe 4 core techniques used for language modeling throughout the years, and how each solved the preceding issues. The first technique, n-grams, is a fundamental building block for language modeling. The idea behind n-grams is pretty simple. We can estimate a word's probability based on the preceding n-1 words. So, in an n-gram with n equal to 1, called a unigram, 1 minus 1 would equal 0, right? This means that the prediction is not based on any context. Let's see how this works. We have the following sentence, and aim to predict the final word. The n-gram model functions by not using any words from "my favorite sport is" to predict basketball. Instead, it would review the entire text, and look for the word that appears most often, assuming that the word with the highest frequency is the best bet to fill the blank space in the sentence. So, the unigram model might predict common words like the or and, regardless of their actual fit with the previous words in the sentence. But if n equals 2, called a bigram, the prediction of basketball depends solely on the previous one word. In My Favorite Sport Is, we focus on is to analyze the frequency of all subsequent words in the training data. The same goes for a trigram. The model analyzes instances of sport is in the training data to predict the most frequently occurring subsequent word. So this is how ngram works. Far from ideal, huh? The model seems to miss the subtleties of context and prior information. It simply aims to optimize predictions based on appearance frequencies in the training data. Neural nets are undoubtedly a giant leap forward. Recurrent neural networks, or RNNs, are neural networks that work best with text. A key strength of RNNs is their ability to retain information from prior steps in the neural network. Analyzing previous words in a sentence helps the RNN network decide on the next word. This is a considerable breakthrough compared to ngram models because the order and context of data points are crucial when dealing with language. The primary challenge with RNNs is their difficulty in handling large texts, as they tend to lose earlier information with progressive text segments. This problem is called the vanishing gradient issue. To solve this, AI scientists developed long short-term memory, or LSTM networks. LSTMs improved traditional RNN models by introducing a gate architecture to choose which information to retain and which to discard. This allows the network to keep important long-term information and forget irrelevant data, which makes LSTMs significantly better at tasks involving complex text data. The main drawback of LSTMs is their high computational cost and slow training speed on large datasets, making them unscalable. But in 2017, the paper Attention is All You Need introduced the concept of transformers and the attention mechanism. The attention mechanism allows a model to assess the significance of various words or parts of words or tokens in an input sequence to generate an output. Therefore, the model identifies key words and focuses more intensely, lowering computational costs and enhancing scalability. Transformers process text by selectively focusing on relevant sequence parts at each step, rather than handling the entire text simultaneously. This is achieved by assigning an attention score to each word in the input sequence. Words with higher attention scores are deemed more significant, enabling transformers to handle long-range dependencies. Okay, great. So now you know how we got the technology that made the creation of LLMs like ChatGPT possible. We're making excellent progress. In our next lesson, we'll discuss different phases when building an LLM. Thanks for watching. Hey everyone, in this video we'll discuss the different stages when building a large language model, including model design, dataset engineering, pre-training, preliminary evaluation, post-training, fine-tuning, and final testing and evaluation. These stages are not always strictly sequential in a real-world environment and could sometimes overlap. Nevertheless, using this representation would make it much easier to illustrate and explain the LLM creation process. The initial phase we discussed, model design, involves AI strategists and developers selecting the neural network architecture to employ. For example, they might choose transformers, CNNs, RNNs, etc. Additionally, they must decide on the model's depth, number of layers in the neural network, and the total parameters it will contain. The architecture choices at this stage will determine the scope of work and what the model can and cannot do. There's a popular saying among data practitioners that a model is only as good as the data used to build it. Undoubtedly, the dataset engineering phase is crucial, involving the collection, cleansing, and structuring of training data for the model. There are two main ways to acquire data to build an AI model: scrape publicly available data from the internet, or use proprietary data. But few companies possess enough data to build an LLM with proprietary data only. Many AI strategists, like Bernard Marr, agree that the companies that own the most proprietary data will likely have a competitive advantage when building AI systems. It's essential for AI developers engaged in dataset engineering to consider key ethical issues, including data diversity and building datasets that address various biases. Once these preparations are complete, the pre-training phase begins, involving training the model on a large corpus of raw data from the dataset engineering phase. During pre-training, we obtain a raw version of the model. But, depending on the pre-training data, the model could provide undesired outputs. For example, if we trained it with Internet forum data, the model could provide output responses containing offensive language and different biases. Moreover, we might be building a model that will be used for a specific domain. And when a model trained on general data needs to be used in a specific industry, we need to adapt its outputs to meet the specialized requirements of the field. Suppose you're working on a customer support chatbot. In that case, you want to train the chatbot to reply in a customer-friendly way that corresponds to client expectations and the service they use when talking to human customer support personnel. So, AI developers evaluate the preliminary performance of the model and gain an idea of its capabilities. Once they understand what needs to be improved, they'll address these issues in the post-training phase. Post-training consists of two steps. First, AI developers use supervised fine-tuning with high-quality data to improve the pre-trained model. In the second step, they'll refine the model by incorporating human feedback, like annotations. The next phase of model development, fine-tuning, updates the model's weights to enhance its quality and speed. For example, by changing weights, we can make a model smaller and faster, better suited for a specific task, and less capable in general performance. Lastly, in the final phase, we again test and evaluate the model. This time, we are much stricter and want to put ourselves in the end user's shoes. We aim to evaluate the model's response quality, accuracy, speed, and, crucially, its ethical behavior. In the next section of the course, we'll discuss model evaluation and how it's performed in practice. Thanks for watching. Right. I want to summarize 3 crucial Gen AI concepts in this lesson. Clarifying these terms with an easy-to-understand example is helpful because people often use them interchangeably, even though they describe different activities. You might often hear, "We'll fine-tune the model," or "We'll use prompt engineering to improve the model's performance." Typically, they refer to one of 3 distinct methods: prompt engineering, RAG, or fine-tuning. All 3 techniques enhance an LLM's response accuracy and effectiveness in specific scenarios by targeting different aspects of AI functionality. Prompt engineering is when we explain to the model how to behave or what context to consider. We don't change any of its weights or add new data. We use instructions and provide verbal examples, explaining the desired output we want to obtain. This is fairly easy to do, And the best part is that we can consistently refine our prompts through multiple iterations to achieve satisfactory AI outputs. It's important to note that the model doesn't change. It merely adapts to our verbal instructions. Retrieval Augmented Generation, or RAG, is another technique that doesn't change the model's weights. With RAG, we attach a database to the model, which can be used as a library for expanded context. This method provides significantly more examples of how the model can be used to learn to perform optimally. RAG and prompt engineering are effective, but making an LLM smarter or faster is unlikely without modifying its weight. This complex task requires additional training for an already trained model. This process is known as fine-tuning. Sometimes extra data is required to conduct fine-tuning. Moreover, fine-tuning can be computationally expensive, and we can't use an iterative process like prompt engineering and adding RAG. Let me explain an example that will clarify matters further. Since GPT's introduction, our team has been eager to explore products utilizing an LLM. We eventually developed an interview simulator based on the GPT engine. If we were to retrain the GPT model and assign it new weights to make it lighter and faster to give responses to users quicker, this would have been fine-tuning. We couldn't do that because OpenAI's fine-tuning was an experimental program inaccessible to all developers during the tool's construction. But even if it was available, it doesn't fit our use case because we want to create an interview bot that can generalize well and adapt to the changing circumstances during an interview. We aimed to enhance the model by integrating a database of sample interview questions, providing context for tailored queries based on the user's selected interview type. This led to the incorporation of RAG, with multiple adjustments made to the database during the app's development based on the model's performance. The prompt engineering phase was the most time-consuming. We had to instruct the model on displaying code questions, the types of queries for various interview stages, evaluating students afterward, the communication tone, following up on responses, and other aspects. This project indeed showed us the rising importance of prompt engineering skills and the multiple back-and-forth iterations necessary to build an AI product that behaves as expected. I hope this example clearly illustrates fine-tuning, RAG, and prompt engineering. Thanks for watching. Until recently, the machine learning models developed by companies were limited to narrow applications. Image recognition models were trained to excel at identifying objects within images. Speech recognition systems specialized in converting spoken language into written text. NLP models dealt with narrow language tasks such as sentiment analysis or translation. Time series models were used to predict stock prices, market volatility, etc. All these models excelled in a very narrow range of tasks. The introduction of large language models led to a significant transition over the last few years. LLM's complex and sophisticated structure, trained on massive data, allows them to excel in general-purpose tasks. LLM's capabilities are not confined to one or two types of tasks, or are within a single domain. Instead, with some fine-tuning and prompt engineering, LLMs can perform well in many fields. At first, LLMs were purely text-to-text models, generating responses based solely on textual input and output. But it wasn't long before they could work with code and different types of files, such as Excel and PDF, and even read the information in images and videos. Many were surprised by how fast this technology progressed. The point at which LLMs evolved from mere text-to-text frameworks to generating text, code, images, and video marked their transition from strictly language models to more sophisticated multimodal systems. The correct term the AI community used to refer to them is foundation models. This name comes from the idea that these models serve as a foundational layer for various applications across multiple disciplines. Foundation models are enormous, can perform various tasks, and are immensely powerful. According to OpenAI's Sam Altman, few organizations will be capable of building their own foundation models in the future. Big tech firms want to compete in this market, and several governments may wish to create their own foundation model. Everyone else will either build their application-specific in-house models or build on top of the foundation models created by big tech. Or the open-source community may rise to the occasion and prove big tech executives wrong. We'll talk more about that in our future lessons. Thanks for watching. One of the eternal dilemmas in the business world is known as buy versus make. This decision determines whether to outsource specific company processes or retain them internally. The golden rule MBA graduates are taught is that a company should try to retain internally all strategic value-adding activities because they are essential for the business. In turn, management can externally delegate non-core activities aimed at efficiency. All of that's great, but when discussing AI and large language models, the situation is unique. As we previously mentioned, few companies and organizations worldwide will be able to build their own foundation models. Creating these models is costly, and few businesses can achieve the necessary scale. Most companies face a critical choice: either build on an existing foundation model or develop their own version from an open-source model. In many cases, firms lack the expertise and resources to train a custom model, yet they recognize AI as a core value add to their business. Consequently, these businesses must rely on organizations like OpenAI, which offer access to foundational models like GPT through a model-as-service arrangement. So, you see the contradiction, right? AI can be a core value-generating aspect of the business, but AI availability and development don't fully depend on a company's in-house efforts. So, how would regular businesses compete with each other if everyone could use OpenAI's API and gain access to some of the world's most advanced AI models with a single API call? In this scenario, the ability to adapt AI to specific use cases will be an actual differentiating factor. The expertise of in-house AI engineers in prompt engineering, RAG, and fine-tuning will help many businesses gain an edge over competitors. Consequently, the demand for skilled AI engineers is expected to surge in the near future. These fascinating developments indicate a significant paradigm shift that will continue. ChatGPT is brilliant, but sometimes we give it more credit than it deserves. We can make big mistakes if we don't fact-check an AI's output. As a rule of thumb, try to remember the following principle. An expert in their field works with AI and reasons within the AI conversation box, rather than copying and pasting every answer and mindlessly trusting. In fact, OpenAI clearly states at the bottom of the screen, ChatGPT can make mistakes. Check important info. You can obtain two types of undesired behavior from GenAI tools: hallucinations and inconsistencies. Hallucinations are observed when the AI provides false output to generate any production. Now that you understand how GenAI operates, you realize that models often predict the next word in a sequence using context to enhance accuracy. Despite the power and sophistication of these models, their predictions can occasionally be incorrect. Another reason hallucinations could occur is that the AI could be trained on factually incorrect data to begin with. If trained with false data, the model will likely produce incorrect outputs, right? A legitimate tactic for dealing with hallucinations is to give an instruction that says, "Provide an answer only if you know the answer." In some cases, this type of prompt engineering could be helpful. On the other hand, inconsistency occurs when a model provides very different responses to the same question. Especially when ChatGPT first came out, it felt like the AI was smarter in specific sessions and dumber in others. This is due to variations in the hardware used to run the model, or other uncontrollable factors, primarily when the model is hosted externally. One unproven way to reduce inconsistency is by instructing the AI to take its time. Hopefully, if you do that, it won't rush to produce a response, and the system could allocate more hardware resources for every prompt. In any case, detecting hallucinations and inconsistencies and finding ways to deal with them will be one of the major topics of AI research in the years to come, and will surely become a market worth billions. The two main factors determining how powerful an AI model is are dataset and model size. A larger, higher quality dataset significantly enhances the model's learning potential. Meanwhile, the model's size determines its learning capacity. Think of the large dataset as a library full of books. All else being equal, the more high-quality books we have in the library, the more we can learn. In this analogy, model size can be compared to a student's learning capacity. Students who can remember and internalize more information can use this extensive library. Similarly, a larger AI model that has more parameters will be able to capture more intricate patterns and make more complex decisions based on the information learned from the dataset. So, in general, the larger an AI's dataset and model size, the higher its performance can be expected. But building the largest model isn't always the best strategy, because it involves a clear trade-off between performance and cost efficiency. It's expensive to acquire large, high-quality datasets, and even more costly to set up and purchase the computing power to train a considerably large model. So, budgeting is a crucial topic and a fundamental skill AI developers need to acquire. You can't start building your AI model and then figure out how big it will be and how much it will cost during the training process. Instead, it's much better to consider the available budget beforehand and decide what portion will be allocated to data acquisition and computing power. This aspect is quite tricky. Sam Altman revealed in an interview that training GPT-4 cost OpenAI over $100 million. Most organizations cannot afford multiple attempts at training their AI models and must succeed on their first try. Finding the right balance between how well an AI works and how much it costs is key to AI development. Bigger AI models need more computing power during training and operation, which can get expensive. Creating a large model should hinge on a significant boost in effectiveness that aligns with the organization's goals and resources. In some cases, building smaller models that can be retrained and fine-tuned frequently makes more sense. Training smaller, specialized models is more cost-effective and faster than using vast resources to train a large model for limited applications. One key issue when building customer-facing applications is that today's users have low tolerance for slow loading times. The latency issue becomes even more critical when business customers want to use Gen AI to boost personal productivity or build products based on an AI model. In such scenarios, the stakes are higher. because delays frustrate users and directly impact business operations and revenue. Regarding latency, the biggest challenge of LLMs today is that the models use an autoregressive architecture, where each word generated depends on the words that came before it. This sequential nature limits the speed at which outputs can be produced, because each step must wait for the previous one to be completed. If an LLM sequentially generates each word in the sentence, "My favorite sport is basketball," at 0.2 seconds per word, it would take 1 second to complete the sentence. To solve this issue, AI developers are exploring different architecture types and parallel computing. An effective immediate strategy is to optimize model size. Smaller models are often faster than their larger, more complex counterparts. When we see diagrams like this one, it's natural to expect that the next version of an LLM will be significantly larger than the previous one. But one major issue is likely to hinder this process. If GPT-4 has already read and processed a significant part of the publicly available data on the internet, where would the new data for GPT-5 come from? AI developers risk running out of data and face a potential slowdown in the growth of model capabilities. Moreover, now that ChatGPT has gained popularity, there's a significant risk that many of the new articles and materials posted online will be written using AI. This makes learning new or nuanced information challenging for future LLMs because they frequently encounter repetitive or derivative content. Future models will simply echo what previous models have written, thereby increasing the risks of hallucination, biases, and inaccuracy. Another obstacle to data availability is that following the hype surrounding Gen AI, several large organizations worldwide filed lawsuits and prohibited data scraping of their websites. Some of the first litigations came from the New York Times, Shutterstock, and best-selling author John Grisham, while platforms like Reddit and Quora changed their policies to make it illegal for AI developers like OpenAI to scrape their platform data. To mitigate this issue, OpenAI has started a content licensing program and has already signed agreements with several organizations that own some of the largest proprietary datasets in the world. OpenAI offered publishers between $1 and $5 million a year to access archives and train its Gen AI models. They signed deals with organizations like Shutterstock, Axel Springer, the Associated Press, Le Monde, and Prisa Media. In the future, competition between big tech firms developing LLMs will likely significantly increase the price of large proprietary datasets. No and low-code tools are a popular way to get started with AI. They've grown in popularity in recent years and are certainly trendy. You can use them to develop chatbots and gain an initial idea how you can build your own AI product. In some cases, they'll even allow you to build real-life products. But while there are some incredible no-code tools, if you're serious about learning to work with AI and develop applications that incorporate AI, you must know how to code. Learning to code is essential for profoundly engaging with AI because it allows you to use APIs from major AI providers like OpenAI, Llama, and Anthropic. Coding skills enable you to tailor AI behavior through prompt engineering, integrate databases, and modify model parameters, capabilities currently beyond the reach of no-code tools and crucial for creating sophisticated AI-driven applications. Python is the leading programming language for data science and AI, according to the TIOBE Index. Its comprehensive libraries and robust infrastructure enhance scalability for AI engineers and developers. There's a significant number of open-source tools and libraries you can use. The most popular ones include NumPy for multidimensional arrays, matrices, and math functions, pandas for data preprocessing, and matplotlib for data visualization. To begin in Python, install an IDE like Jupyter Notebook, Google Colab, Spider, or PyCharm. Our Python course guides you through the setup process. To wrap up, learning the coding aspects of AI development requires considerable effort, especially for beginners, but it's essential for creating reliable applications. Some website owners use APIs, application programming interfaces, to facilitate data extraction. An API serves as a bridge between a client, like your computer, and a server, enabling them to communicate. The client sends a request across this bridge, and the server responds with the required data. Consider the usefulness of this. Imagine two companies, 365 company and a job board business, seeking to collaborate. If 365 company wants to share up-to-date information about how much a student has learned with the job board, they can use an API. This way, the job board gets the latest student data directly from 365's servers. The process involves two main steps: the API request and the API response. The job board sends a request to 365's servers via the API, and then the server responds with the data. To integrate a foundation model like GPT from OpenAI into your product, you need to connect to OpenAI's API. This connection is essential to send requests to and receive responses from OpenAI's services, allowing you to use their foundation models in your application. Using APIs is another critical skill AI developers and engineers need in their arsenal. Relational databases organize information in rows and columns. This makes them perfect for structured data. But they're not optimal when we have to deal with unstructured data such as text, images, video, and audio. To convert multimedia into a format that computers can understand, we use vector embeddings, which are then stored and organized in a vector database. Essentially, in a vector database, we have arrays of numbers clustered together based on their similarity. Let's imagine YouTube's database with millions of videos. These videos can be grouped based on their genre. We can have vlogs, gaming videos, tutorials, how-to videos, tech reviews, music, and other formats. The goal is to index all videos and organize them in a way that allows very fast retrieval and search. To do that, vectors are organized in the database so that videos with similar content are positioned closer together in the vector space. This organization is based on similarity metrics that measure how close or distant the vectors are from each other, which can be interpreted as what is the difference between videos in terms of genre, content, length, or other stylistic similarity. Please consider how much data can be used to train an LLM. In some cases, we can have millions and millions of vector embeddings, which means that querying millions of vectors and looking for similarities would be very slow. To ensure fast retrieval of the data, vector databases rely on indexing and use ML techniques that allow them to search efficiently. The use case of vector databases I described here is about search. We can use vector databases for similarity search and search based on meaning and context of words. In addition, one of the coolest applications of vector databases is giving LLMs like GPT and Gemini long-term memory. By storing past interactions or learned information as vectors, a model can reference this data to better understand context. For example, if you use an LLM as a chatbot assistant, it can store information about previous conversations with you and similar customers, and provide more informed responses. For your AI projects, consider popular vector databases like PineCone, Weaviate, Milvus, Chroma, and Elasticsearch. While highly popular, PineCone is not open source, which may limit some projects. In contrast, Weaviate, Milvus, Chroma, and Elasticsearch offer popular open source alternatives. We'll spend more time discussing open versus closed-end AI tools in our next session. Thanks for watching. We've done a lot of looking over our shoulders at OpenAI. Who will cross the next milestone? What will the next move be? But the uncomfortable truth is, we aren't positioned to win this arms race, and neither is OpenAI. While we've been squabbling, a third faction has been quietly eating our lunch. According to this leaked Google document, the emerging third faction threat comes from open source models, a significant concern for Google and OpenAI. The author starkly notes that Google or OpenAI do not have a secret sauce that makes their AI models better. But didn't we say that Sam Altman and other big tech execs believe there will be very few organizations globally with the resources and skills to build LLMs? Isn't there going to be one model to rule them all? Well, let's see. One of the eternal battles in the software development world is the one between open and closed source development. Today, this clash will play a significant role in the AI industry's evolution. It's true that few organizations have the resources to build and develop their proprietary LLMs. But this doesn't mean that the rest cannot construct versions based on open source AI. While everyone is focused on the battle between big tech firms developing proprietary closed-source foundation models like GPT and Gemini, open-source AI's rapid growth needs to be noticed and happens behind the scenes. Open-source software is developed by a community of skilled and motivated individuals who can build on each other's work and provide public access. Such a collaborative environment accelerates innovation, fostered by open-source software's main strength, the ability to rely on collective knowledge and creativity. The tribe is stronger than the individual, if you will. One of the critical factors that boosted the growth of open-source AI is that the users could reduce hardware requirements for AI development. Once that happened, innovation and model improvements snowballed. The leaked Google document reveals that the gap in terms of quality is closing astonishingly quickly. It also notes that some open-source models are pound for pound more capable than GPT and Gemini. The open-source community has successfully tackled running large language models on smartphones and developing scalable personal AI. Therefore, proprietary LLM developers understandably sense a threat because they've invested heavily in AI models aiming for significant returns. Yet, the open-source community is rapidly gaining ground. Closed-end solutions are generally easier to implement, offering plug-and-play convenience with minimal configuration. Using an open-source AI model means you avoid Google or OpenAI fees, but you still incur compute costs. Additionally, it's unclear and subjective whether the costs of customizing and fine-tuning an open-source AI will exceed the total expenses OpenAI charges. Besides easy integration, closed-source AI offers optimized user experience, customer support, solid APIs, and ethics and legal compliance. You can imagine how important this is to large enterprises. Another critical benefit of closed source is that your business data should have a lower chance of leaking to the public, which is of paramount importance. The 2023 leak of Meta's Llama AI model, which may not have been entirely accidental, turned out to be beneficial. Once released, the open-source community began to build infrastructure on top of Llama, inadvertently boosting Meta's AI offerings. In a way, we can say that one of the big tech firms embraced the open-source approach and combined massive resources and initial investments necessary to build an LLM with the power of community development. We don't know which school of thought will prevail. And to say that closed source or open source models will win over time would indicate a limited understanding of the topic. There will likely be wildly successful closed and open source AI projects in the future. I think open source models will be advantageous for narrow use cases requiring a specialized AI. Such domain-specific problems will be solved brilliantly by fine-tuning a base model. In these cases, using a broader model like GPT to solve a niche problem would be much more expensive. Moreover, fine-tuning a closed-source model can be expensive because some companies charge significantly. Closed-source models would probably stay more expensive overall. Still, due to the vast datasets they're trained with, they will also be more powerful when faced with complex tasks that require generalized understanding and skills. A crucial advantage of big tech firms is that they have the resources to acquire proprietary data, which allows them to build even more robust foundation models and, therefore, widen the difference in performance quality. While we're on the topic of open source tools, our next lesson will be about Hugging Face, often regarded as the GitHub of machine learning and AI. Hugging Face is a leading advocate for open source AI, fostering collaboration on models, datasets, and applications within the machine learning community. Hugging Face is often referred to as the GitHub of machine learning because it aims to promote open source ML and AI. To train a state-of-the-art NLP transformer model, you need to invest significant funds, which, as we said before, isn't feasible for startups and small businesses. Hugging Face helps democratize the process by giving everyone access to pre-trained models, which can be found on their platform. Such models are freely available and can be used to develop proprietary AI by avoiding the massive expenses needed to train an LLM from scratch. Moreover, Hugging Face introduced the Transformers Python library, which is very helpful because it allows AI developers to access pre-trained models easily via an API. Additionally, the Transformers library provides an efficient way to create machine learning pipelines. With Hugging Face, users can share ML models, use pre-trained models, fine-tune ML models, host demos, and evaluate ML models. Founded in 2016, Hugging Face now boasts a valuation exceeding $4.5 billion, indicating substantial resources and commercial status. Like GitHub, owned by Microsoft, Hugging Face's infrastructure isn't open source, though user-uploaded models and datasets are. LangChain, a valuable tool for developing AI-powered apps, is an open-source orchestration environment available in Python and JavaScript. It allows you to build an app and use any foundation model you'd like with it. You don't need to rewrite code, because LangChain's modular components, like functions and object classes, can replace one foundation model with another in a structured, easy-to-implement way. Much like constructing with Lego building blocks, you can easily replace one piece with another and continue building forward without any issues. Similarly, LangChain enables developers to integrate multiple foundation models and external data sources. The platform essentially serves as a library, offering a collection of commonly used programming components and patterns. These tools are tailored to help developers efficiently work with language models, simplifying complex tasks. This helps developers save time and prevents their applications from inconsistent code. Here's an example. Let's say you want to integrate an AI chatbot into your product. So, without LangChain, you'd manually select a language model, like OpenAI's GPT. Next, you'd need to integrate the API, handle user queries, pre-process these into a format suitable for the model, and Finally, interpret the language model's responses to provide clear answers to the user. This process requires detailed knowledge of APIs, request handling, and data formatting in Python. Alternatively, LangChain lets you leverage pre-built components to build chatbots. You utilize these components to handle the API interactions, data preprocessing, and response generation. For example, if a user asks, "What's the weather like in New York today?" LangChain can manage the entire workflow, from understanding the question to fetching and formatting the appropriate answer, significantly reducing the complexity and amount of code needed. This tool's advantage is that it gives developers a quick and user-friendly way to integrate LLMs into their apps. At the same time, LangChain allows for less customization than writing all LLM integrations manually. Another frequent use case of LangChain is adding long-term memory to such apps as chatbots, virtual assistants, and customer support systems. This helps AI systems improve their interactions and become more intelligent by considering the history of previous conversations. Earlier in the course, I mentioned that our team built an interview simulator app powered by GPT a few months ago. The most challenging phase in the development process wasn't preparing the database with interview questions to be fed to the AI or the developer's work. Instead, we discovered that we spent the most time on prompt engineering the AI and QAing its responses. This highlighted a vital issue everyone building AI products faces: model evaluation. After you've built an AI-powered product, you need a reliable way to test its output. If you skip the evaluation phase, you risk going live with an AI product that hallucinates, provides inconsistent responses, has ethical issues, which nowadays is probably the biggest deal breaker, and, in general, releases a product that isn't up to the required standards and doesn't perform as expected. So, we decided to use the popular AI as a judge approach, which essentially means asking an AI to evaluate the output of another AI. The AI judge will select and evaluate a sample of questions and responses from the AI interview simulator. Our app is built in a way that allows learners to be asked two main types of questions: open-ended and coding questions. The two are very different from an AI perspective. Code questions are closed-end tasks and much easier to evaluate than open-ended ones. With coding questions, the AI knows what type of output it should expect from the task and can, therefore, easily assess whether the tool calculated correctly or whether its code produced a given output. Open-ended questions are much more subjective and difficult to evaluate, but strong models are improving in this activity. According to LangChain's State of AI report, 58% of the projects built on their platform used AI as a judge, which shows the increasing importance of this part of the AI dev cycle. The substantial benefits of evaluating AI by AI include cost-effectiveness, scalability, speed, and the ability to review a larger volume of interactions with customers. This is especially important if you have thousands or tens of thousands of users and want to deploy an AI-powered app. On the flip side, AI models lack human intuition and ethics, which can lead to challenges in contexts where nuanced understanding and moral judgments are crucial. Therefore, it's also imperative to involve human judges in the evaluation process. In this course segment, we'll explore various AI roles, covering job descriptions, typical backgrounds, essential skills, and their positions within the corporate hierarchy. Let's start with the AI strategist role. Today, everyone is hyped about AI's disruptive potential. But not all companies will benefit from AI, often because they fail to strategically implement it. It doesn't suffice to simply initiate AI projects without a clear plan, hoping that innovation and business results will happen naturally. Ideally, your company should have an AI strategist to guide this journey, focusing on the overall business strategy and company goals from the outset. One of the guiding principles in this process is that an AI strategy needs to be in sync with the firm's overarching business strategy for it to be successful. There are a few key ways in which AI can benefit your business. It can help you sell better products and services, AI can improve your company's processes, and AI can facilitate decision-making. An AI strategist will consider your company's overall business strategy and identify and map multiple AI use cases related to the business. The company will pursue the use cases that best align with its business strategy and are expected to have the highest impact. Despite its non-technical sounding title, AI strategist is indeed a technical role. Besides identifying and suggesting viable AI use cases, an AI strategist needs to be able to help their company execute in practice. They'll guide the company in determining the optimal type of AI model, considering the performance of different solutions and their respective costs. Once the company has committed to a framework and a specific model, the AI strategist needs to envision how the AI model will be deployed in production and integrated into the firm's existing products. Finally, they'll need to set procedures to help the company evaluate and optimize the performance of the AI models it has deployed. Another critical aspect of an AI strategist's contribution that shouldn't be overlooked is AI evangelism. This means promoting AI adoption across the company and ensuring employees understand how AI can help the business become more competitive. Okay, so what is the typical background of an AI strategist? What did they do in the past to get to this stage of their career? This is a new role, and requirements are fluid. But in most cases, the candidate will be a data scientist with an extensive technical background in data, machine learning, and AI. Throughout their career, they've been able to work with many business stakeholders and understand what drives business value. A good data strategist knows what it takes to build a technical solution and has the business acumen to envision the project's impact. An AI strategist must possess such critical skills as comprehensive business understanding and strategic and technical expertise in ML and AI, ideally with a development background. Additionally, they need strong soft skills like exceptional communication and project management capabilities to effectively collaborate with top management and various stakeholders. As you can imagine, it's rare and difficult to find individuals with such a comprehensive and diverse background, and organizations would be willing to compensate AI strategists exceptionally well. Typically, AI strategists are hired as directors or heads of a dedicated team as VP roles. Or when companies want to embrace AI, they can be given a C-suite role. Considering how rare the AI strategist profile is now, their substantial compensation and sometimes AI implementation can be seen as a one-off, temporary project. Some firms could hire AI strategists who are not full-time employees, but rather come in as consultants. Naturally, this approach has the advantage of lower costs, and an AI strategist who works with many companies and can share industry best practices. The drawback, however, is that they might not have sufficient time to understand the business in depth, and therefore, AI strategy could turn into a one-off project for AI adoption. The AI field is in its infancy, and job titles are inconsistent. Employers often use various titles such as AI developer, AI engineer, and machine learning engineer for roles with the same job descriptions. It is still early days for the AI field, and job titles are not well established. Here's my interpretation. An AI developer builds foundation AI models, while an AI engineer builds applications on top of foundation models. In this lesson, we'll focus on the AI developer function, while in the next one, we'll describe the AI engineer job opportunity. As mentioned earlier in the course, building a foundation model requires extensive financial resources. Until now, the best-known foundation models include OpenAI's GPT, Google's Gemini and BERT, Meta's Llama, and Anthropic's Claude. Numerous organizations, however, are ambitious enough to develop their own foundation models, including governments and the open source community. Building a proprietary foundation model that successfully competes with the powerful alternatives available in the AI market is challenging. The organizations that aim to do so must innovate and navigate an ever-evolving, complex landscape of technical challenges and new solutions proposed by the AI community. Therefore, AI developers need to spend a significant portion of their time researching and trying to study ways to push the boundaries of what AI can achieve. The R&D component of this role is essential because it allows AI developers to stay abreast of industry developments and test new ideas. In practical terms, research helps AI developers understand the optimal architecture for the solution they want to build and decide on the model design to be used. They'll define the type of neural network and how many layers of depth the model will have. Once AI developers make these decisions, the dataset engineering stage begins, collecting, cleaning, and structuring the model's training data. These essential preparations for the pre-training phase involve training the model on vast raw data corpus. AI developers must meticulously ensure accuracy during this critical time because training is costly and leaves no room for errors. Once trained, AI developers conduct a preliminary evaluation of the model, refining it with higher quality data and prompt engineering. They then continue to refine and evaluate the model until it's ready for production. This demanding role requires advanced technical skills, including proficiency in Python coding and experience with key mathematical libraries like NumPy and Pandas for data cleaning. Moreover, an AI developer needs an excellent understanding of statistics, linear algebra, calculus, and probability to understand AI research and complex topics such as deep learning and transformers. Since AI developers work on generative AI, they need strong knowledge of NLP in semantic similarity, transformers, vector embeddings, tokenization, and many others. But that's not everything. AI developers need proficiency in containerization, DevOps practices, and the ability to work with tools like Docker. Furthermore, being familiar with API design and cloud software is advantageous. This is one of the most demanding jobs in the tech world, and relatively few people are qualified to work as AI developers. Though slightly less demanding, AI engineering is becoming one of the hottest future careers. We'll discuss this in our next lesson. Thanks for watching. Earlier, we said that an AI engineer builds AI-driven products on top of existing foundation models. This means they're not focused on AI modeling and training, but on integrating AI foundation models with new or existing products, such as websites, mobile applications, hardware systems like the Internet of Things devices, and smart home systems. So, the AI engineer's main task is to build the bridge between foundation models developed by organizations like OpenAI and Google and a product that can benefit from AI. They also optimize the AI model's performance by performing various model adaptation techniques, such as fine-tuning, prompt engineering, and RAG. AI engineers require strong coding skills, ideally in Python, which hosts most data science and AI libraries. This coding language allows you to script initial data analysis, explore datasets, and prototype simple models. In addition, Python libraries, such as Pandas and NumPy, can help you prepare data and ensure it's ready for your AI project. Hugging Face is a valuable platform for AI engineers. It offers the Transformers library with state-of-the-art foundation models for fine-tuning specific tasks your company needs to address. Familiarity with Hugging Face is highly beneficial. LangChain is an indispensable tool for AI engineers. It enables the integration of foundation models into products and offers the flexibility to select and switch between various LLMs as needed. LangChain helps simplify the AI integration process significantly. Vector databases like PineCone are also helpful, as they aid AI engineers in handling complex data structures like embeddings. The vector database stores this data efficiently and quickly retrieves it on request. This allows the engineer to focus on improving the AI application's UX and quality of responses rather than worrying about latency and scalability. Another critical skill AI engineers need is a solid understanding of LLMs and NLP. They can benefit significantly from working with cloud services and containerization tools like Docker. Finally, to be a full-stack AI engineer, an individual must combine ML engineering, AI, and software development skills. Such diverse backgrounds are rare, but many companies seek talent with computer science and ML engineering backgrounds to fill AI engineering roles. They're often looking for a talented individual with an ML or computer science foundation willing to invest the time to build up their skills in the area they lack. Most job advertisements for AI engineers cite a bachelor's or master's degree in computer science, math, statistics, data science, or another related field. Becoming an AI engineer is a great career opportunity. The number of companies that want to capitalize on Gen AI will increase exponentially in the coming years, and there will be more opportunities to integrate consumer products with extremely powerful and sophisticated foundation models. The Oxford Dictionary defines ethics as moral principles that govern a person's behavior. AI ethics is a collection of moral principles to maximize AI's benefits for the common good and minimize potential harm from its development. It's natural to think of AI as a computer's intellect and perceive it as something beyond human control. But AI models are still conceived, designed, developed, trained, and refined by humans at this stage. So, a vital issue that AI ethics must address is determining human accountability in AI development and identifying who is responsible for the AI's actions once it's operational. It would be an understatement to say that artificial intelligence could help humanity. It could democratize and improve access to education, revolutionize drug discovery in healthcare, and make a decisive push toward environmental sustainability by optimizing energy consumption. At the same time, AI's widespread adoption poses significant challenges regarding, among other perils, data privacy, dissemination of false information, and job displacement. We're not far from the day when advancements in robotics and AI will make it possible to manufacture competent AI weapons. Moreover, AI can potentially penetrate a country's critical infrastructure systems from a distance and paralyze its economy. These issues make many governments anxious and eager to be the first to develop a more capable AI. This is a classic example of moral hazard, in which a few reap the benefits of technology while the potential risks and damages are distributed among the many. This dynamic creates an environment where the incentive to push boundaries in AI development is heightened despite the associated risks. So, the international community must promote the debate on AI ethics and agree on sustainable AI development principles. Besides security risks, AI poses significant socioeconomic challenges. It's expected that many jobs will become redundant due to AI. According to an analysis from the U.S. White House, about 10% of U.S. workers are in jobs that face the most significant risk of disruption from rapidly evolving AI. In addition, the report found that workers with less education and lower income are especially exposed to AI, raising the risk that the technology could amplify inequality. But many experts believe that layoffs are not just coming for less educated workers. On the contrary, NVIDIA's CEO, Jensen Huang, who is at the forefront of AI innovation, says that kids no longer need to learn programming. Imagine the implications of that. Using AI ethically starts with building AI ethically. To achieve that, AI developers must adhere to ethical standards regarding the training data used for AI models. Using as much data as possible is natural, and those who don't will probably develop less sophisticated models. But training AI with personal data for which you don't have the necessary user permission, or training with web-scraped data against website policy, is unethical and can be seen as IP theft. Governments worldwide understand that it's time to act. Even the Pope weighed in on AI at the G7 summit in Italy. He was one of the first global personalities falsely portrayed as wearing a Balenciaga coat and a white cross through Gen AI deepfake. His attention was piqued by the emergence of technology that can produce images that are perfectly plausible but false. Consequently, he advocated for AI regulation, stating that AI offers new freedoms, but also the risk for tech dictatorship. The European Union was the first global player to introduce a regulatory framework on AI. Known as the EU AI Act, this EU legislation aims to protect citizens, businesses, and government agencies by making AI development safer and more transparent. To comply with such legislative requirements, AI developers must make the necessary investments to protect their models from bias and discrimination, protect consumer privacy, and ensure compliance with EU standards. Initially, this would require extra costs, but then the compliant organizations would have the opportunity to reap the benefits of responsible AI. Hopefully, global powers will soon agree on a unified framework for AI governance that transcends national boundaries. This would level the playing field and facilitate international cooperation in advancing AI technologies in a manner that prioritizes human well-being and safety. Bloomberg reports that by 2032, the generative AI market could reach $1.3 trillion. Compared to the U.S.'s annual GDP of approximately $25 trillion. PricewaterhouseCoopers, PwC, is even more optimistic, predicting that the generative AI market will reach $15.7 trillion by 2030. The two forecasts have a massive gap. We don't know which will prove correct. We do know that the AI sector will experience unprecedented growth. This technology will continuously evolve and improve. The rate of growth, however, depends on several critical factors. The three essential resources AI models need include electricity, data, and computing power. The availability of new training data is a rather sensitive topic, considering that using social media data and website proprietary data to train huge foundation models can be unethical. At the same time, it seems that LLMs will become even larger. It'll be interesting to witness how the Internet's largest data owners approach this issue. Perhaps we'll see even more licensing deals than those announced by OpenAI. Moreover, in some regions, governments will likely impose AI regulations, prohibiting training models with users' private data, unless certain agreements exist. We might even see organizations that develop LLMs willing to pay users to access their personal data and train models with it. It will be interesting to see how AI developers tackle the challenge posed by the increasing volume of AI-generated content on the Internet. If that content is used to train new AI models, it could create feedback loops, diminish the accuracy of AI models, and amplify existing biases. Secondly, we must consider that large and sophisticated language models require substantial electricity. As people find new applications for AI and the adoption of AI models grows globally, the overall usage and, consequently, the electricity demand for AI is set to skyrocket. At some point, we must evaluate AI's global energy and carbon footprint and consider how the demand for AI services impacts global energy prices. Consider this report title from the Conference Board, an independent business membership and research association. The rise of AI threatens to explode U.S. electricity demand and overburden the grid, but also promises new efficiencies. Right now, it appears that AI will play an essential role in shaping future energy prices. Finally, we need computing power to develop and operate state-of-the-art Gen AI models, extremely capable AI chips. In 2023 and 2024, the U.S. chipmaker NVIDIA skyrocketed in value because it found itself as the best-positioned player to capitalize on the growing demand for semiconductors driven by the AI hype created by ChatGPT. There seems to be a significant shortage of high-quality AI chips, but that might change because NVIDIA's huge profits have attracted the attention of other semiconductor producers. The other major plotline in the AI industry is whether the AI models developed by the open-source community will become competitive with closed-source AI. Alternatively, big tech firms like Google and OpenAI will continue to dominate the market. Regardless of the outcome, witnessing firsthand the transformative impact that AI will have on various aspects of our lives will be thrilling, potentially surpassing the changes brought by the digital revolution of the Internet. I want to thank you for sticking until the end of the Intro to AI course. It has been an absolute pleasure being with you. I hope that you learned a lot and will check out more of 365's AI courses. Good luck, and thank you.
All right, what do you need to know about programming if you are just getting started? We all have to deal with certain tasks in our daily lives. Many we can solve on our own, while others, especially the ones that are more complicated, can be solved with the help of a computer. Assume you have defined a problem that must be solved and you know the steps that must be taken to solve it. Even if you could structure your logic perfectly and type a brilliant solution in English, the computer will not understand it, as it understands zeros and ones only, no other symbols. Similar to a light switch, it recognizes two phases, on and off. To communicate a real-life problem to the computer, you need to create a specific type of text called a source code or a human-readable code that software can read and then process to the computer in zeros and ones. A program is a sequence of instructions that designate how to execute a computation. Therefore, the formal definition of programming is the following: taking a task and writing it down in a programming language that the computer can understand and execute. You need not be a geek or computer scientist to program. Actually, the subject of computer science is not the study of programming. These are different things, and this can confuse beginners. Computer science is about understanding what computers can do. Programming, instead, is the activity of telling computers to do something for us. Think about the world we live in today. There are more than 1,000 programming languages out there, and each language is designed for carrying out specific tasks. So, depending on the sphere to which your problem applies, only some languages can be of good use. For instance, PHP is good for web programming, but is not suitable for programming devices. C++ can definitely help you with the latter, while Python and R are some of the favorite tools of data scientists and people from the finance industry. When you meet an experienced programmer, don't think he can program in all languages out there. Instead, it is likely he can work with one or maybe a few languages, but he has mastered them well. Right, but how does somebody become good at programming? First, programming requires problem-solving skills and involves abstract thinking. You are supposed to understand your task perfectly and then break it down into a sequence of instructions or smaller computational steps that the computer can execute. For example, John is asked by his boss to do the following. Create a program that adds 10 to any number his boss inputs with the keyboard. The correct reasoning would be, if x is the unknown provided, we need an output of x plus 10.
Once you've created these steps using a programming language, you'll begin writing clean, well-structured lines of code. So, the second crucial skill to develop is mechanistic thinking. If we set aside artificial intelligence, also known as AI, computers can only execute what you explicitly ask them to do. They won't understand what you imply through your instructions. Even AI may sometimes misinterpret your intentions. Therefore, you should learn to write clear code the computer can execute to produce the desired result, regardless of whether it's interpreted by you or by an AI. Fortunately, even though AI may sometimes outperform us in interpretation, humans remain the ultimate decision makers when responsibly understanding, overseeing, and adjusting code instructions. This is why a solid knowledge of a programming language's syntax and the ability to read and write code are paramount. It will positively influence your thinking process by helping you break down problems into parts the computer can execute. This skill is essential even when working with AI, because strong programming skills enable you to understand its behavior, debug effectively, and connect all the puzzle pieces.
In the example we provided above, John must think of the following subtasks. First, he must define a function that takes x as an argument and then returns as an output a new variable equal to x plus 10. This is how this problem can be solved. Regardless of the problem you are facing or the programming language you are using, your coding style is crucial. Remember that. Having 3 lines of code is straightforward to understand. However, in practice, you will likely work with hundreds of lines of code that must be sent to other people. If your work is difficult to read, unnecessarily complicated, full of variables as names, conveying no meaning, it will be poorly received by other programmers. Therefore, throughout this course, we will pay attention to the best practices that will help you organize your code. Programming challenges are great as they develop your mechanistic thinking and problem-solving abilities. This involves formulating problems, breaking them down into meaningful steps, and communicating these steps to the computer in an organized way. This will do for now. Thank you for watching. Although it may be new to some of you, Python has been on the programming stage for over 2 decades. There are 2 main reasons you should learn Python. First, it has several technical advantages compared to other programming languages. And second, its practical application covers several industries. It is a powerful computational tool when we have to solve complicated tasks in the field of finance, econometrics, economics, data science, and machine learning. Therefore, it is a perfect stepping stone for somebody who learns how to code and is determined to pursue a career as a data scientist. Here's a slightly more technical description of Python. It is an open-source, general-purpose, high-level programming language. Let's break this definition into several pieces and try to understand each of these attributes. Open source means it is free.
Python has a large and active scientific community with access to the software's source code and contributes to its continuous development and upgrading. Depending on users' needs, this is the main reason Python is cross-platform. It is available for all major operating systems, Windows, Mac, and Linux. The benefit of it is Python can be quickly applied anywhere. Domain-specific languages like MATLAB and SAS, also used for solving financial and econometric tasks, are paid. This plays a role in a language's popularity. General purpose. There's a broad set of fields where it could be applied. For instance, Python can be used for web programming through the Django framework. Although this is beyond the scope of this course, you should be aware of the wide scope of application, and the interoperability with other programming languages could be an explanation why some large organizations have chosen Python as their main programming language. High level. This is slightly more technical. Broadly speaking, computers can run programs written in low-level languages only, also called machine languages. So, a program written in a high-level language must be first interpreted into a low-level language before it can be executed. This process takes time. There is specialized software and applications that will do this interpretation for you. The advantages of using a high-level language are huge. It is difficult to code and understand low-level programming languages. They are too technical. High-level languages employ syntax a lot closer to human logic, which makes the language easier to learn and implement. It allows the programmer to focus on the task at hand, instead of trying to figure out unreadable lines of code. To summarize the technical advantages that make Python a powerful programming language, often preferred over other programming languages, we can say the following. It is free and constantly updated. It can be used in multiple domains. It does not require too much time to process calculations and has an intuitive syntax that allows for complex quantitative computations. What we've said so far demonstrates Python's enormous practical applicability. It is clear we are living in the era of big data. People in different disciplines, economics, finance, computer science, marketing, and many more can retrieve huge amounts of data. We can talk about big data when we have millions of observations. In such situations, the computational capabilities of traditional data processing applications like Microsoft Excel become insufficient. We need a more powerful tool to tackle big data in more or less the same way, regardless of the field application. Python is perfect for these situations, as it gives us flexibility. To conclude, Python's popularity lies on two main pillars. One is that it is an easy-to-learn programming language designed to be highly readable, with a syntax quite clear and intuitive. And the second reason is its user-friendliness does not take away from its strength. Python can execute a variety of complex computations and is one of the most powerful programming languages preferred by specialists. For this course, you must install both Python and Jupyter on your computer. If you have them, you can still complete this lecture, because we will say a few interesting things about Jupyter. So, why isn't there just one software application called Python you can install on your computer that is automatically being updated and that runs everything smoothly? I am sorry to tell you, but it's not the case. We have to deal with reality. First, Python is a programming language. It can allow you to communicate with the computer. To do that, you'll need the help of a specific software or an application. Namely, the Jupyter Notebook app, which is more often called Jupyter, can help us to do that. It is a server-client application that allows you to edit your code through a web browser. Consider the following graph. All units represent different software. On one side, you have several language kernels. These are programs designed to read and execute code in a specific programming language, like Python, R, or Julia. The Jupyter installation always comes with an installed Python kernel, and the other kernels can be installed additionally. On the other side, you have various types of interfaces where you can write code. They represent the clients. An example of such a client is the web browser.
The Jupyter server provides the environment where a client is matched with a corresponding language's kernel. In our case, we will focus on Python and a web browser as a client or as an interactive shell. Your work will be stored on a notebook document, and since we will strictly be using the Python language, it will be called IPython notebook file with the file format .ipynb. Having said all that, we can explain why Jupyter is used in so many large corporations like Google, Microsoft, and IBM. For its design, it is well suited for demonstrations of programming concepts and training. First, in large corporations, solving a particular task could require coding in a few languages, say Python, R, Julia, or PHP. Instead of installing different interfaces for each language kernel you need, Jupyter allows you to use the same structure of the notebook type of file. Simply, each notebook you create will connect to the language kernel you request. Consider also, this file can be easily stored locally or on a remote server. Therefore, Jupyter facilitates the communication between teams in a corporation tremendously. Second, Jupyter is not a text editor that opens a new window every time you execute a different part of your code, as is the case with some other software applications. In the same file, you can have pure text that can communicate a message to the reader, computer code like Python, and output containing rich text like results, figures, graphs, pictures, and others. This simplifies the process of the workflow immensely, and Jupyter Notebook is increasingly preferred over other software packages. That's why we'll use it too. The next step would be to install Anaconda, a software package that contains both the Python programming language and the Jupyter Notebook app. Thank you for watching.
There are various ways to install Python on your computer. For new Python users, installing Anaconda is highly recommended. Anaconda will install Python, Jupyter Notebook app, and many packages for scientific computing and data science. Please remember that Anaconda constantly updates its products and website like any other online service. So the functionalities will likely remain the same even if their interface or organization looks slightly different when you access their web page. In any case, remember to always look for a free-to-download individual edition. That said, let's open www.anaconda.com and click on the free download button at the top of the homepage. Then you'll be asked to send your email to Anaconda, but you can also choose Skip Registration. We'll do the latter, directing you to the download page for the installer. By pressing the download button, Anaconda will suggest the best version that suits your operating system. Alternatively, you can scroll down and manually pick a version for one of the three: Windows, Mac, or Linux. In this lesson, I'll show you how to install Anaconda on Windows, but the procedure is practically identical for Mac or Linux. Additionally, you'll see that each operating system lists Python 3.13. This is the latest version of Python as of this recording. If this is no longer current, please select the most recent version. To download the available Windows version, click 64-bit graphical installer. Then you must find a directory to install the distribution and press Save. When the download has finished, run the application. Then follow the instructions provided by the standard Windows installer. Click Next to agree and select a default or specific destination folder. To choose the latter, press the Browse button. When satisfied with the indicated directory, choose Next once again. Then follow the recommendations made by the installer. For example, I'd like shortcuts created and will only select the recommended options, omitting the second one. Click Install and wait for confirmation that the operation is complete. That's all you need to do. You've just installed the complete Anaconda distribution, which includes Python, a text editor, and numerous applications and packages. Now click Next. Select only Launch Anaconda Navigator and hit Finish to open the Anaconda Navigator, an interface for managing your installed Anaconda features. The Jupyter Notebook interests us, so click the button under its icon to launch it. This will open a new tab in your browser with the Jupyter dashboard, which displays your user's folder by default. Bear in mind that there's an alternative for starting Jupyter. Open the Windows Start menu and select the respective icon. A new window will appear, and the app should load within a few seconds. When done, your web browser will again open a new tab containing the same Jupyter dashboard. In our next video, we'll study the dashboard in detail and learn how to use Jupyter. See you there! Thanks for watching! Okay, so in this lesson, we'll take a quick tour of the Jupyter Notebook dashboard, the starting point of the Jupyter Notebook app. But before we do that, please remember that this one is occasionally updated like any other popular application. Therefore, aside from some minor visual or functional changes, the version of Jupyter we use in this video should act as an accurate and precise guide for using this tool. That said, as soon as you load the Jupyter Notebook, its dashboard opens. Here, you'll see the path to the folder where you work. For instance, we're now in Documents. The respective icons indicate that we only have folders and files, more precisely, notebook documents. The logic regarding directory management is the same as that of an operating system. Files can be grouped into folders, and folders can contain other folders. Click on Folder to explore what's in it. It's empty. Let's assume we don't want to create any items in it. To return, click on the name of the folder, in this case, Documents. In the Documents folder, each item has a checkbox next to it. By checking an item, you could manipulate it a certain way. For instance, as you tick the box to the left of a folder, we'll rename it or carefully delete it. We've confirmed that the folder is empty and that we have no plans to use it, so let's go ahead and remove it. To do that, make sure you've clicked to the left of the folder icon and then press the Delete button here at the top. Confirm, and as you can see, we were only left with 5 items in Documents. Both remaining folders contain files. So it would make sense to rename the second folder to folder-02. To do that, tick the box to the left of it. Press the Rename button and provide the desired name. In contrast, when using files, you can open, download, rename, duplicate, or delete them by checking the box to the left of their name. All right. Note that Jupyter indicates which documents from the displayed list are currently running. Go to the Running tab to view all files and processes you've started and are still active. Moreover, a little green dot appears between the Notebook's icon and the checkbox in the Files tab. In our case, these 2 untitled notebook documents are running. You can access and work on them from the other 2 browser tabs. Before we get to that point, remember that the selection menu allows you to select all files together. This is useful if you want to apply the same manipulation to all items. The suggested manipulations can be found by right-clicking on the selected area. To return to the previous state, uncheck the box at the top. From the Upload button in the top right corner, you can upload a notebook into your directory. The standard Explorer box opens. When you select a file, you can click on Open, and it will immediately appear in your directory. Finally, you can expand the New button. From the drop-down list, you'll most likely need to create either a new folder or a new notebook file. The orange icon indicates a notebook document. On our list, we only have a Python-type notebook document based on a kernel named IPyKernel. The browser immediately opens a new tab for me. This is the interactive shell we mentioned earlier. Here, you'll write your code and see its output. Think of it as a notebook document that runs on the IPyKernel. It's saved in the IPython notebook format with the .ipynb extension. You'll see it appear immediately in the Documents folder. By the way, don't fear this other new name, IPython. Think of it as the predecessor of Jupyter. Consider the IPython notebook format a legacy file format. One last thing before we conclude. When you finish your work, go to the Running tab, right-click the process you'd like to terminate, and select Shut Down Kernel. Otherwise, if you close Jupyter, all related processes will be ended automatically. In our next lecture, we'll write code and see how Jupyter displays the output. Thank you for watching. Okay, great. Now that we know more about the Jupyter Notebook dashboard, we can examine the shell and see how to code in Jupyter. First, the field you see here is called a cell. That's where you'll provide text and code. Second, remember that there are two modes in which you can manipulate Jupyter cells. You're currently in command mode. This mode involves manipulating, or better, organizing the notebook as a whole. We'll explore some of the associated functionalities in a minute. The other mode, edit mode, allows you to write and edit text or code. To access it, either click the gray box labeled as the input field, or select the cell and press Enter. Once you've done that, you'll be able to see the cursor, so you can start typing code. To close edit mode, click elsewhere on the document or press the Escape button. Naturally, as you do any of the two, you'll return to command mode. This is why the cursor disappeared. If you want to ensure you are in command mode, just press Escape. Doing so will always get you out of edit mode. The blinking cursor is your best indication that you're ready to start typing code. When you see it, you're in edit mode. If it's not visible, which can happen after pressing Escape or clicking outside a cell, you've entered command mode instead. Since I'd like to write some code now, I'll hit Enter again. I'll type a short code line defining x as a list of 4 numbers, 1, 2, 3, and 4. After that, I can ask the computer to display this list by typing x and running the cell. I can execute these commands in several ways. The first is to hold Control and press Enter. By doing this, the machine will execute the code in the cell, and I will stay there, meaning I will not have created or selected another cell. So I'll also go back to command mode. Observe that an output field with the same number as the input field appeared. Input and output fields of the same number are always grouped. The output represents the machine's response to the code provided in the corresponding input. Please note that you cannot modify the output per se. You can only change the code and execute the cell again if necessary. For example, to add the integer 5 to your list, switch back to edit mode, type 5, then hold Control and press Enter again. See? The output has changed, displaying the value of 5 in the list too. The second option allows for more fluid code writing. To execute the same code, hold Shift and then press Enter. The previous 2 lines are executed and a new cell where you can write code is created. Please note that when using Shift and Enter, a new cell will be created only if there's no cell after the one you are currently typing in. In other words, I'll now try running the cell above again. To do that, I will select it by clicking somewhere on its area and then use the same keyboard combination, Shift and Enter. In this case, Jupyter will navigate me to the next cell in command mode, not edit mode. A third way to run the cell would be to press the tiny triangle icon here in the top menu. This option works exactly like using the Shift and Enter keyboard combination. Finally, Alt and Enter runs the current cell, adds a new one below, and puts you in edit mode so you can keep coding right away. See? Interestingly, when you work with more complex code that requires tougher calculations from the computer, a little star will appear over here inside the square brackets next to the cell while running the code. Sometimes this process takes too long to complete, so to interrupt it, or break it as some might say, pressing the classical stop symbol can do that for you. In this lesson, we presented the Jupyter Essentials. After some practice, the meaning behind the few options we discussed will undoubtedly become second nature to you. In the next lesson, we'll further explain how to become an even more autonomous Jupyter user. See you there! This lesson will provide additional information to improve your coding experience in Jupyter. Earlier, we discussed executing a cell either by referring to this tiny triangle here or by applying any of the following commands: Control and Enter, Shift and Enter, Alt and Enter. These three are examples of Jupyter shortcuts. The exciting part is that there are many more you can use to accelerate your coding experience. First, make sure you're in command mode. You can check this by confirming that no cursor is blinking in any cell, or simply press Escape to enter command mode. Once you've done that, either go to the Help menu and choose Show Keyboard Shortcuts, or, as suggested, use the Control, Shift, and H shortcut to access the desired list. I'll use the keyboard combination. A new window will appear, showing each operation on the left and its corresponding shortcut on the right. Let's scroll down a bit to see if you recognize any of the shortcuts listed here. Aha! Enter Edit mode is triggered by pressing the Enter key. What else? Here are the commands we just mentioned for running a selected cell: Control and Enter and Alt and Enter. Great! You can always refer to that list while coding, because in your practice, you'll increasingly need more functionalities and operations. The best way to use this feature is to check the desired shortcut, close the Keyboard Shortcuts window, and apply the functionality in question. To achieve this, you can either press the Escape button on your keyboard, or hit the Close button at the bottom right of the window, or click elsewhere on the screen. Okay. Now let's explore a different Jupyter functionality you'll find very handy. Without focusing on the syntax, consider the following cell containing a comment and 2 lines of code. One indicating that the value of a variable x will equal 3 plus 5, and another printing the value of that variable, x. Press Control and Enter to execute this code, and you'll obtain the value 8 as an output. Open the View menu, and you'll see an option to collapse items. For example, select Collapse Selected Code to hide your written code. See? The code disappeared. Only the comment and output remained. To bring it back, select Expand Selected Code from the same menu. You might wonder why we're highlighting this shortcut. In this example, the output doesn't take up much space, but this feature becomes especially useful when working with longer code. Another shortcut worth mentioning is pressing Shift and L. In the Shortcuts menu, you'll see that Shift and L is used to show or hide line numbers. Close the Keyboard Shortcuts window, and then select the cell again. Hold Shift and press the L key. You now see line numbers displayed along the left side of each row. Once again, the line numbers may seem unnecessary for shortcode, but as your code grows, they become helpful, especially when collaborating with others to troubleshoot or review work. It's incredibly useful that you can, among others, cut, copy, paste, and delete cells. To apply these cell-level commands, hover over each icon to see its function, then click to use it.
Since we are keen supporters of ergonomics, we suggest you get used to the keyboard shortcuts. When coding, you will mainly have to use the keyboard, so it's worth memorizing different keyboard combinations that would allow you to work faster. Let's see how we can apply shortcuts in practice. I will cut this cell by selecting it, and then pressing the X key. Remember, you can always use the arrow keys to navigate along your notebook file. So, I will move up and then directly press the V key to paste it. Voila! My cell has moved up here, below the cell I had selected before I pressed the V key. Now, I will press C to copy the same cell. I will use the arrow keys again to go down this time, and at the end, I will press V again. Apparently, this cell was copied and pasted below.
Next, Holding Control, Shift, and pressing the upward or downward arrow allows you to move a selected cell up or down, just as I am doing right now. Notice that the corresponding output field moves along with its input cell. Lovely!
3 other shortcuts could accelerate your coding a lot. Suppose I have selected this cell. After I press the A key, a new empty cell will be inserted above. If I select the same cell and press B, another cell will be created just below. Imagine the last step was a mistake, and I need to delete that empty cell. In this case, it has already been selected, so I can press the D key twice, and it will readily disappear. Wonderful! All the cells we saw so far were code cells. Let's see what is a markdown cell. It is a cell that contains strictly documentation, text not executed as a code. It will contain some message you would like to leave to the reader of the file. To convert a selected cell into a markdown cell, you should either expand this list and opt for Markdown, or simply press the M button. Press Enter to access the cell and type some text. When I run this cell, the output will be a simple statement. Now, if you want to turn a markdown cell back to a code cell, select it and opt for Code from this drop-down menu. Or press the Y key. To conclude, there are 2 advantages of using Jupyter. First, when your code becomes longer, markdown cells turn out to be useful, as they allow you to leave comments and explain the solution you've created. This is why practitioners love to use them. The other benefit of using this app is you can select and execute whichever cell you want to. You need not run all the previous cells to run a particular cell. This allows for solving a problem in pieces and saves a lot of computation time.
This was a long but indispensable lesson. In the next one, we'll continue with handling errors while coding. Thanks for watching. Hi, and welcome back. When speaking a foreign language, or even our native language, we sometimes make mistakes. While coding, the situation is no different. What's great about programming is that you get notified about your mistake. Python, like any other programming language, will display an error message when you request it to do something it does not understand. Consider the following Jupyter Notebook document. Disregard the syntax we'll use and focus on the operations conceptually. They will be a mix of mathematical and programming requests. To begin, we will execute this cell to specify that we'd like x to be equal to the sum of 5 and 3, that is 8. Then we'd like Python to display the value of x for us by running print x in the following way. In the output field, we see what we expected, the value of 8. This means that we have worked correctly and have abided by Python's syntax. But what happens when we do the opposite and disregard the Python rules? As we request the value of y to be displayed, we obtain an error message. How come? The reasons can be many, but what is sure is that we have asked Jupyter to do something it cannot understand. To solve this problem, Jupyter itself assists us by explaining to the best of its abilities what prevents it from executing the operation from the relevant code cell. Please remember, and this is extremely important, the idea is to use this hint to improve our code so that we obtain the desired output. In this example, we are having a name error. Jupyter is even being specific by telling us it doesn't understand what we mean by y. Here is the moment where you, as a programmer, have to realize what type of an error that is. Considering that the interpreter is reading your code letter by letter and line by line, this means that there was nothing wrong with what we've written until y. So, the error seems to be related to that letter, and the last line of the error message confirms it. Please remember that in the majority of times, the last line of the error message indicates where the problem is coming from. Then, as programmers, we realize we can solve this particular problem in 2 ways. One would be to provide a value for y. The other is to assume that we have just not referred to the correct variable. Therefore, we can substitute y with x and execute the cell again to obtain a satisfactory output. Great! It doesn't sound hard at all, right? Well, Yes, but that's just the beginning. It is important to realize there's no guarantee that you're having a single cause for a problem. For example, if you type print y like this, Jupyter will just indicate that it doesn't understand what the first 4 letters are there for. It will be the job of the coder to remember that the command they need is print, not prit. At the end of the day, you may have just made a typo. However, when you correct this and re-execute the code, you'll receive an error message again. At least, this one looks familiar. You know how to solve it within the boundaries of our example. So, substituting y with x can finally lead to the right outcome. All right. Aside from the technical perspective, there are several takeaways from this lecture. We can't rely on Jupyter to be always telling us the exact reason why it was not able to execute or request at a specific moment. It is amazing how accurate and precise it can be in its suggestions. But don't be surprised. Sometimes the obtained error messages won't be very clear to us, the programmers. Therefore, it will be our job to understand the messages and decide on how to solve the given problem. Then, don't forget that coding is all about using a programming language to solve certain analytical tasks. So, every programmer has encountered countless error messages on their way. What is important is to know how to handle them. Try to understand and resolve them, and don't pretend you're able to write the perfect code from the first try. That is impossible. On that note, please follow this guideline. Don't quit on your task, and be ready to respond to as many errors as you need. Of course, this doesn't mean there's no place to get support from. For instance, you can Google the error. Just paste the last row of an error message online and see if there's a thread or a post that can help you solve the problem yourself. This approach will not be preferred or needed throughout the course, I believe, but will serve you a great deal after completing it, or also as a professional when you will already be an independent programmer. In other words, Googling the error is what you would do on the job, so it is good to get used to it. Regardless of whether this strategy works, you can search for the relevant error in the Q&A forum. Alternatively, if you can't find an answer there or you stumble upon a recurring problem, please do feel free to post a question yourself. We will be happy to reply as soon as we can. Just when you do that, please stick to the following structure. Let us know what your task is and what output you're aiming for. If you can point us to a particular lecture or section from the course, please do that as well. Then, paste the exact code you have executed before obtaining an error message. Third, provide a screenshot of the error message, or at least its very last line. That one is very important. Finally, anything else you can share about the problem will be much appreciated. Having this type of information will help us immensely to assist you better. So, we would be extremely grateful if you spend the time to provide it. To conclude, you don't need to just try and execute random code at this stage, but the principles delineated in this lecture will be applicable while programming in Python or other languages throughout the entire course and beyond. This will do for now. Thanks for watching.
This is a video in which we will share 2 specific Jupyter functionalities with you. If you have worked on a file and have closed it after having run its code cells, the next time you open it, you will not see the code in the input cells only. You will see also the obtained results stored in the output fields.
Now, imagine you would like to run the cells from the very beginning. What should you do? The best way to do that is to expand the kernel option from the Jupyter menu and select the option Restart Kernel and Clear Outputs of all cells. After you click on it, you must confirm by pressing the Restart button. Then we will see the only thing left in the notebook file is the code. None of these cells have been executed. That's why there is no number associated with the input cells. So after we execute the first cell, it will have the number 1. The next one will be numbered as 2, and so on. Great! The other interesting option would be to select Restart Kernel and run all cells after expanding the kernel option from the Jupyter menu. It will basically proceed similarly to the option we just saw. This time, however, Python will run all code cells from the first to the last unless it encounters an error somewhere on the way.
In case some cells contain an error, Python will simply stop there. In our case, there were no mistakes in the code, and the cells were set in the correct order, so everything will run from the beginning until the end. Is that correct? Yes, lovely. These options can be applied anytime you must redo what you have done with the notebook file. This usually happens after spending a long time on a document when you want to verify your code can run smoothly from the beginning to its end. We hope you enjoyed this video. Thank you for watching. All right, great. Warm up your fingers. In this lesson, we will start coding. One of the main concepts in programming is variables. They are your best friends. You will deal with them all the time. You will use them to store information. They will represent your data input. Let's say you want to have a variable x that is equal to the value of 5, and then ask the computer to tell you the value of that variable. So, we must tell the machine that x equals 5. And this is how you could do this in Python. Type x equals 5. To go through the process of programming, the line that says x equals 5 is called a command or a program. This is just a line of text. To make something out of it, we must execute it. Only then will the computer carry out operations with it. Press Shift and Enter, not just Enter, and a variable called x will be created and assigned with a value of 5. To be more precise, equality in Python and in programming means assign or bind to. Okay, we carry this operation, but we see nothing right now. How can we ask the computer to show us the output of what we just did? It would be sufficient to write x and then press Shift and Enter. And here's the result, 5. Great. As you can see, typing in a single line of code entails a few concepts of programming simultaneously. In the next few lectures, we'll make sure everything falls in place. Now, let's assign the value 8 to a variable we call y. All right, Shift plus Enter, and we can check y. However, I'll type capital Y. Oh, an error. This shows us that Python is case sensitive, so pay attention to that. It matters if you use lowercase or uppercase letters. An alternative way to execute the instruction that will provide the value we assign to y would be to use the print command. At first sight, it seems redundant. As we showed, we can just type y. Nevertheless, this command is applied often. You'll see it in most of the code produced by professionals. It complements the logical flow of your instructions. For instance, if we say print y, the machine will simply execute this command and provide the value of y as a statement, and this is all a programmer must see sometimes. The last thing I'd like to share with you in this lecture is you can assign a certain number of values to the same number of variables. To create the variables x and y, we have to assign 2 values, say 1 and 2. We must separate each of the variables and each of the values with a comma. The parentheses here are not obligatory, but we use them to improve the readability of our code. Now, if I call x or y separately, the computer will correctly give me their respective values. It is very important that the number of variables on that line equals the number of values. Otherwise, you'll get an error message. See? Great. This is a great start to our journey in Python. Make sure you go through the exercises attached to this lecture. We'll see you in the next one.
In this course, you'll encounter multiple coding exercises to solidify your programming and analytical skills. I'm sure you'll get the gist after completing just a few. As a first step, please take the time to watch this video covering the essential differences between coding locally and coding in the browser. To begin with, please remember that to solve the coding exercises, you'll only need techniques and code we've explained throughout the video lectures and the articles. That's why we advise you to always follow the order of the course items. Secondly, if you wish to complete only the coding exercises from a specific section, please refer to the relevant videos provided beforehand to obtain clarification. Then, crucially, if you need further assistance, compare your work with the code files provided in the resources section of the lectures corresponding to those coding exercises. Although the latter sometimes intends to use different data, completing the tasks locally still tests the same techniques as the coding exercises. Finally, if this doesn't help, feel free to write in the Q&A section of the course, and we'll be happy to provide the relevant guidance. Without further ado, let's see a practical example. On the left-hand side, in the Instructions tab, you'll find the exercise title, task, and a link to the lecture that covers this task's topic. In this case, you're asked to produce an output equal to click OK. To solve the exercise, you need to provide code on the right. Let's intentionally make a few mistakes to explore different scenarios you may encounter. Assume you want to try to solve the given problem by executing click correct, where only correct has been written as a string. If you press Run Code, you'll get an error message stating that you didn't follow Python syntax. Naturally, there's no way to successfully solve a Python coding exercise under such circumstances. If you enclose the expression in single quotes and then run the code, you'll obtain a statement saying, "Run completed," meaning that you provided valid Python code. Will that mean you have solved the task correctly? To check that, you'll need to press Run Tests. The results say you failed, and at the bottom of the error details, you can see that a wrong string had been inserted. What might we have done incorrectly? First, never forget that Python is a case-sensitive language. So let's capitalize the first letter of click and change correct to OK. Executing the line of code shows that it abides by the Python syntax. But when running the tests, we fail again. Why? To obtain click OK, as shown in the task text, you'll need to pass this string as an argument of the print function. This will deprive your output of the quotes. Running the code confirms the run was completed and displays the provided string. Does this piece of code solve the given task? Yes. As a result, you'll obtain success. As a side note, remember that sometimes there may be multiple solutions. But please always solve the exercise as instructed because we not only check for correct Python code, we also verify whether you're carefully following the steps outlined, much like you would expect to do in a real-world business and analytical environment. Finally, after conducting a successful or unsuccessful test, you can check your answer with the suggested one. To do the latter, check Solution Explanation at the top left part of the screen. So I guess you figured it out. As long as you've obtained success, you can move on to the next lecture or exercise. Let's consider another example. This time using Python lists. Don't worry if you're not familiar with this topic yet, you'll learn about it in the following course sections. In brief, a Python list is a structure containing values that can be manipulated. You'll always be required to write the entire solution code yourself. Part of it will sometimes be provided, as is the numbers list provided here. Unless specified otherwise, you won't have to alter it. Subsequently, you'll only need to add lines of code. After that, all rules regarding running code and tests shall apply. With all that in mind, you might wonder, should you code in the browser or work locally using Jupyter? Of course, the two can act as substitutes. Code locally if you're experiencing connection issues, or code online if your software installation isn't working. Ideally, you should do both since the more you practice, the more knowledgeable you'll be when encountering challenges in a working environment. Here are the benefits of following each of these approaches. Coding in the browser exercises have been constructed to assist you in learning the material quickly. There, we can check if you can answer a programming or analytical task precisely without adding unnecessary lines of code to the solution. These factors make the coding exercises more challenging. The environment itself is more similar to Spider or PyCharm than to Jupyter, meaning the output may look different when using the print function, even though the code itself remains unchanged. This only helps you get used to applying your Python coding skills in a slightly different setting, as would sometimes be the case in a professional context. Alternatively, working in your local coding environment also has its benefits. Exploring Python capabilities, such as trying other solutions for the tasks in the coding exercises, can deepen your skills. Applying a specific code structure to a different dataset or revising code from previous lectures would also be easier. In addition, you could explore new commands or combine the solutions from multiple exercises into a single file. There's just one important caveat to consider. Obtaining a result won't necessarily mean you've correctly answered the analytical question. Nevertheless, with these notes in mind, Jupyter can lay the foundation for you to become a truly autonomous Python user. To sum up, if you don't manage to solve a coding exercise on the first try, then we encourage you to repeat the instructions because we usually look for a correct result and comply with the required steps. Rewatch the reference videos because returning to them is perhaps the best way to learn the new material. Check with the solution explanation provided in the final tab. Or if none of these are helpful, feel free to post in the Q&A section. To conclude, remember that when coding in the browser, we're not only asking you to provide code that adheres to the relevant language syntax, but also looking for a response to a specific task. The effort will be worthwhile. The coding exercises will strengthen your ability to understand tasks and interpret analytical results. Use the lecture references, hints, and suggestions, and enjoy the journey. Good luck!
When programming, not only in Python, if you say that a variable has a numeric value, you are being ambiguous. The reason is that numbers can be integers or floating points, also called floats, for instance. Integers are positive or negative whole numbers without a decimal point. Let's create x1 and bind it to the value of 5. Now, x1 is an integer. Do you agree? A specific function in Python can prove this is correct. It is called type. Within the brackets, we must place the name of the variable whose type of value we want to verify. So in this case, I'll type x1. OK. Shift plus Enter, and the result we obtained is int, which indicates the value is an integer. The type function can also be applied directly to a value instead of a variable. For instance, if I write type, open parentheses, -6, close parentheses, Python will correctly point out that -6 is an integer. Good. Now, let's assign the value of 4.75 to a new variable, x2. I would like to check its type. Hence, I will use the type function again. This is a float. Great! Floating points, or as you'll more frequently hear, floats, are real numbers. Hence, they have a decimal point. 4.75 is such a number, therefore, Python reads it as a float. Let's look at two other built-in functions. int transforms the variable into an integer. That's why 4.75 turns into 4. Float, instead, will add a decimal point to the integer value and will turn it into a float. Not all variables should assume numeric values. An example of such type of values is the Boolean type. In Python, this means a true or false value, corresponding to the machine's logic of understanding ones and zeros. On or off, right or wrong, true or false. Let's provide an example with a new variable, x3, which is equal to true. Right. The output of the type function is bool, which simply means x3 is a Boolean. An important detail you should remember is you have to type true or false with capital letters. Otherwise, Python won't recognize your variable as a Boolean and will display an error message. So, to wrap it up, the two Boolean values a variable can have are true or false, and they must be written with capital letters. Thank you for watching. In this lesson, we'll learn about another type of values that can be useful when working in Python. Strings are text values composed of a sequence of characters. Let's see how we can create a string in practice. If we ask the machine to display the name George this way, we'll obtain an error message. Why? Because Python assumes George is the name of a variable to which we have assigned no value. Here's the magic trick that will correct this mistake. Let's type single quotation marks around the name George first. And now, let's type double quotation marks around it. You see the output values of these two inputs are the same. This is how Python displays text results if you don't use the print command. Should you use print, the output will be shown with no quotes. You'll be able to see plain text. If we assign this value to a new variable, let's say x4, we can obtain its output as we did with the integers and floats. Alright, so that's it. If the values you'd like to assign are not numerical, the quotes can come into play. Assume the variable y is supposed to represent the number of dollars you have in your pocket. In addition, you would like to ask the machine to print out a statement that says y dollars, where y is a number. The proper way to combine the value of y and the string dollars is to use a plus sign, as shown here. Let's execute this cell to check if we are missing something. Apparently, we did not respect the rules of coding in Python. We cannot put different types of variables in the same expression. Y is an integer, and dollars is a string. We can convert y into a string. String, str, is the built-in function we need. Analogically to integers and floats, string will convert our number into text, and that will unlock our result. To summarize what we said so far, Python can automatically guess the type of data you are entering. It is within its capabilities to know for sure whether you have assigned an integer, a float, a boolean, or a string. You need not declare the types of variables explicitly, as you must do in some other programming languages. Python always knows the type of variable. What will happen if you type something like, "I'm fine"? You'll need the apostrophe in the English syntax, not for the Pythonic one. Observe, if you execute the command like this, you will make a mistake. To avoid that, in such situations, you can distinguish between the two symbols. Put the text within double quotes and leave the apostrophe, which technically coincides with the single quote between I and M. Now you are fine. An alternative way to do that would be to leave the quotes on the sides and place a backslash before the apostrophe within the phrase, and we'll still obtain the same correct result. This backslash is called an escape character, as it changes the interpretation of characters immediately after it. And what if we wanted to state press enter, where we put enter within inverted commas? Same logic. The outer symbols must differ from the inner ones. Put single quotes on the sides, and you obtained the desired result. Finally, let's go through a few ways of stating values. Say you wish to print red car on the same line. If I write it like this, two words next to each other, separated by a blank space, I'll see them attached. One trick would be to put a blank space before the second apostrophe of the first word. Let's see. Nice. That looks like the desired result. Another technique would be to sort of add one of the strings to the other by typing in a plus sign between the two, just as we did with the $10 example a minute ago. Okay. As your intuition probably tells you, if you print this combination instead, you'll obtain the same outcome, but it won't have the quotes on the two sides. And here's a new trick. I'll type print red, and then I'll put a comma, which is called a trailing comma, and Python will print the next word, car, on the same line, separating the two words with a blank space. Shift plus enter. Great. Let's print the number 3 next to the number 5. Boom! Fantastic! Here it is. What will happen if I don't use the print command and just list a few integers, floats, and strings, separating them with commas? Python will execute the command as expected, but will place the values within parentheses. We've made excellent progress, and you've learned a lot about the Pythonic syntax. As we did so far, going step by step perhaps, it looks simple and easy, but it is actually important to respect the syntax of a language while coding. In the next lectures, you see this is true. Stay tuned for the next lesson, where we will continue exploring Python's syntax. Thanks for watching.
Hello there. In this lesson, we'll introduce the Anaconda Assistant. This online tool integrates generative artificial intelligence into your Python work. It suits practitioners at all levels and is a great learning assistant, especially for novice and intermediate users. It can boost your productivity and save you considerable time typically spent handling errors, searching for the correct references in the documentation, determining which Python tool to apply in a particular case, performing data cleaning, and more. To respond to your requests, Anaconda uses the language models that OpenAI uses to create ChatGPT. In contrast to ChatGPT, the Anaconda Assistant has specialized in Python code creation, explanation, and debugging. But it doesn't provide as much general knowledge and tech solutions as ChatGPT. To use Anaconda Assistant, register using anaconda.cloud. Please remember that this assistant is part of the Anaconda distribution, so its interface and functionality are similar to Jupyter's. In addition to the classic notebook document located in the center of the screen, there's a file manager on the left and an Anaconda tool panel on the right. You can show or hide these panels by clicking the small icons in the top right corner of the screen and at the middle of the top bar. To communicate with the assistant, use the field at the bottom of the right panel. You can type in plain English or many other languages. To guarantee consistent assistance across its various tools, the latest version of Anaconda allows you to access the same assistant from your Jupyter Notebook or Jupyter Lab. To do that, press the relevant icon in the code cell where you need help, or click the Jupyter Lab icon to use the same AI tool in a different interface. Overall, the interface and functionalities are quite intuitive, so you can quickly master them by practicing. If you're interested in trying out this assistant in any of the two options, in the cloud or locally, you can register on Anaconda Cloud and follow the Anaconda AI lessons we've provided throughout the course. Good luck! Hello again. Think back again on the lesson on Python strings you just completed. Let's stick to the same topic to explore how the Anaconda Assistant works. First, select the option to launch a notebook. Then, select a kernel to open a new notebook document. Execute George as you hear it. You'll receive a name error message saying that the name George is not defined, meaning that a variable with his name has not been declared yet. In the right panel, just above the chat box, the assistant suggests you start a new conversation. Click Debug the active code cell to proceed. The screen explains our mistake and asks if you'd like to suggest a solution. Type Yes in the box, press Enter, or click the green button on the right. We obtain a solution that shows that the Anaconda Assistant has understood that we did not intend to create a variable called George, but rather that George is a text value, which is why it had been placed within quotes. Additionally, as good practice suggests, this string has been assigned to a variable called name, which indicates its content. Then, by choosing Copy, we can copy the obtained code and paste it into the cell in the Anaconda notebook or elsewhere. But now, we'll select the more intuitive option provided, Run Code in Notebook. By doing this, we created a variable called name, containing the string George. Great! Now, let's see if the generative AI models can help us solve a slightly more complex exercise. Imagine you were coding, locally or online, and while writing in a code cell, wanted to assign the value of 10 to a variable y. And suppose you wanted to print out the text $10 by referring to y. You've written the following code cell, but as you run it, you receive a type error message, which you don't know how to handle. Unless you can spot the mistake yourself, one approach is to copy the last line and paste it into a Google search. This can lead you to the most frequently mentioned solutions on the subject. But if you produce the same error in a notebook and ask for assistance by clicking Debug the active code cell once again, you would obtain a precise explanation stating that in Python, you cannot concatenate variables of different types, such as an integer and a string, in such a scenario. You would also obtain a suggested solution pattern. Once we confirm we'd like to receive the corrected code, which includes the string function, we can run it in our notebook directly. Once again, we quickly obtained a clear explanation of our mistake and a solution. You get the idea. As your programs become more complex, you'll increasingly appreciate the impressive capabilities of this Anaconda tool. The trade-off is that the assistant may not always understand your requests, so you must ask questions about fragments from your code. In other words, you'll need to take a step-by-step approach. Keep learning and practicing Python and use the assistant as required to do that well. To conclude, please try to retain the principles taught throughout the Anaconda Assistant lectures. Anaconda's AI tool is constantly updated to provide the best solutions and suggestions. Therefore, receiving different outputs from the assistant when running the same commands on your end is natural. To optimize that AI tool, however, ensure you always interact as clearly as possible with its responses. Overall, what do you think? Quite exciting, isn't it? Thanks for watching.
Great! We are making excellent progress. We've covered some of the basics of Python syntax and the way it functions. In this lesson, we'll continue to build our syntax knowledge. We are one step away from covering the essentials, and then we'll be able to dive into more interesting programming tasks. The next topic on our agenda are arithmetic operators. The addition and subtraction signs are straightforward to use. Technically speaking, in the equation you see here, 1 and 2 are called operands, while in the next one, the operands are 3 and 5. The plus and minus signs are called operators, and given they also represent arithmetic operations, they can be called arithmetic operators. Division is more interesting. If we want to divide 15 by 3, we will need to use the / sign. What will happen if we try to divide 16 by 3? 5 again. Yes, the output was 5 because in Python 2, the quotient is an integer by default. Mathematically, if we divide the integer 16 by 3, we will obtain a quotient of 5 and a remainder of 1. If we use real numbers or floats, the float 16 divided by 3 will result in a float value of 5.33. Therefore, we obtained as a quotient the integer 5 and no information regarding the remainder of the division of 16 by 3. This is one of the few substantial differences between Python 2 and 3. In Python 3, you would immediately get 5.33 as an answer, or a float, because the software will understand your first number was a float value. To avoid this, when we use Python 2, we should look for the quotient of the float 16 divided by 3, and not of the integer 16 divided by 3. So, we should either transform the number into a float or type it as a float directly. See? This is the correct answer. Now, let's obtain the remainder of the division of 16 by 3. How can we make Python produce 1 as an output in this cell? The operator that can help us is the percentage sign. I'll type 16 %3, and when I execute the command, I will obtain the remainder. The answer we received is 1. Good. Multiplication. As usual, we can use the star sign when we want to multiply. For example, 5 star 3 will lead us to an output of 15. For the record, you can assign any arithmetic operation to a variable. If we assign 5 times 3 to the variable x and then we call x, we will obtain 15 again. Great! How could you calculate 5 to the power of 3? By using the double star operator. Type 5, 2 stars, 3, and here you go, 125. Easy, right? Okay, basically, this covers arithmetic operators. Stay tuned for the next lesson, where we will explore some other useful operators. Thank you for watching. You know the right way to interpret the equal sign when programming is assign or bind to. For instance, assign 5 to the power of 3 to the variable y. Bind 5 to the power of 3 to y. This means from that moment for the computer, y will be equal to 125. Here's what will happen when you double the equality sign. Let me type y double equality sign 125. The correct way to read this code is y equals 125. When you run this command, the computer will assume you have requested an answer to the question, is y really equal to 125? This is why, after the execution of this cell, the machine will respond with a Boolean value. It will either return true or false. Let's check our output when we state y is equal to 126. Great! The machine replied with false because 125 and 126 are different numbers. Wonderful! Remember, when you mean equality between values and not assignment of values in Python, you'll need the double equality sign. Anytime you use it, you will obtain one of the two possible outcomes, true or false. In our next video, we will show you how variables can be reassigned in Python. Thank you for watching. Okay, let me explain a programming concept that is valid for other programming languages as well. If I assign the value of 1 to a variable z, my output after executing z will be 1. After that, if I assign 3 to the same variable z, z will be equal to 3, not 1 anymore. How come? Well, the order of the commands matters. Initially, we said z will be equal to 1, and that was true, until we changed the value to 3. For the computer, from that moment on, z is not equal to 1, and it will continue to be 3. As proof, see this. If we add 5 to z, we will get 8. Not 1 plus 5, which is equal to 6. Then, if we suddenly decide z is equal to 7, z will not be equal to 1 or 3 anymore. Python reassigns values to its objects. Therefore, remember the last command is valid, and older commands are overwritten. Thanks for watching. Especially when your code becomes longer, and by longer, I mean containing tens or hundreds of rows, it becomes difficult to understand how your work has been structured because there are too many lines. What you could do in these situations is leave a comment. Comments are sentences not executed by the computer. It doesn't read them as instructions. The trick is to put a hash sign at the beginning of each line you would like to insert as a comment. I'll improvise with a random sentence. It is just a comment and not code. Execute with Shift and Enter. When you run this cell, there will be no output because the comment does not count as code.
Let's add code. Print, open parentheses, 7, comma, 2, close parentheses. Execute with Shift and Enter. Yes, precisely. We got 7 and 2 on the same line, and the comment row marked with a hashtag produced no output. It remained visible only to the programmer. The computer executed the print command only. If we would like to leave a comment on 2 lines, don't forget to place the hash sign at the beginning of each line. These 2 will be comments. everything seems to work.
Okay, perfect. I'd like to show you a neat trick that will be extremely valuable when you become an advanced Python programmer and work with large amounts of code. This is a very handy feature, so please pay attention. Sometimes the length of the cell will not suffice for you to finish your line. Lines of code could get long. Or, just for the matter of organizing your code, you might prefer to send part of the code to the next line. So, 2.0 times 1.5 plus 5 could be written in 2 lines, and the machine could still read it as one command. This could be achieved by putting a backslash where you would like the end of the first line to be. It indicates you will continue the same command on a new line. Cool, right? All right, great. Let's look at another important concept that will help us a great deal when working in Python: indexing. This is a technique we'll use frequently later in the course, especially when we focus on Python's application in the world of finance. So, here's an example of how indexing works. The word Friday is written here, right? Is it possible to extract the letter D? Yes, we can do that by using square brackets, and within them, we should specify the position of the letter we would like to be extracted. A very important thing you should remember is that in Python, we count from 0, not from 1. 0, 1, 2, 3, 4, and so on. That's why I'll ask for the fourth letter, D, by writing 3 here. See? And we obtain the letter D. Had we put 4, we would have obtained the letter A. This is the syntax in this occasion. Square brackets right after the word, or the string of characters if you wish, and a number indicating the position of interest. This is how indexing works in Python. Thanks for watching. The next concept for programming in Python we will see here is fundamental. It is called indentation. The way you apply it in practice is important, as this will be the only way to communicate your ideas to the machine properly. Here is what I mean. Let's define a function, 5, that takes as an argument an unknown x. It will be a simple one. X will be reassigned the value of 5, and the function will return the value of 5 for us. Please note that I am using an indent. Now, we can print the result of 5 with an argument of 3. Nothing happened. Why? Because printing 5 of 3 is within a function, so it will be executed only when the function is applied. If we place print on a new line instead, aligned to the def command, the output will be different. How come? The print command is executed on its own, not as part of the 5 function. Def and print form 2 separate and written in this way, clearly distinguishable blocks of code or blocks of commands. It makes sense to use indentation, doesn't it? Everything that regards the function is written with one indentation to the inside. Once you decide to code something else, start on a new line with no indentation. The blocks of code are more visible, and this clarifies the logic you are applying to solve your problem. Working with functions is interesting, right? Keep up the good work, and I promise to come back to that soon. All right, excellent. You are familiar with the main syntax in Python, and that will help you in the next lessons. In this section, we will learn more about the operators that will help us in our work in Python. We will start with comparison operators. We said if we type the equality sign twice, we can verify the left and right side of an equality are equal. Well, if we use an exclamation mark and an equality sign, then we could verify if 2 sides are not equal. So, it would be false to say 10 is not equal to 10. And it will be true that 10 is not equal to 15. If we use an exclamation mark and equal, and the 2 sides we are comparing are 10 and 15, we'll obtain true, as we wanted to verify they are not equal. Good. What is next? Greater than and less than. We can use the well-known symbols to test if a value is greater or smaller than another value. Is 100 greater than 50? Yes, it is. Is it smaller? No, it is not. And that's why we get false. That's great. The logic behind checking whether an operand is greater than or equal to and less than or equal to is the same. Don't forget that on the right side of the operand, we are not limited to providing only one number, like 10. We could insert an expression, like 10 plus 10. So is 15 greater than or equal to 10 plus 10? No. Is 15 less than or equal to 10 plus 5? Well, that is true. Great! This covers everything we can possibly say about comparison operators. Now, let's see what is intended with the expression logical operators, also known as Boolean operators. Briefly, the logical operators in Python are the words not, and or. They compare a certain amount of statements and return Boolean values, true or false, hence their second name, Boolean operators. Let's start by providing an example with and. And checks whether the two statements around it are true. Let's use only the Boolean values true and false for now. True and true will result in true, while true and false gives an answer, false. False and false will naturally bring us to false. Okay. Or checks whether at least one of the two statements is true, hence false or false will come back as a false, whilst true or true will return true. In this cell, true or false will return true. The order in which we have the two statements does not matter, so false or true will still result in true as well. The way not functions is it leads to the opposite of the given statement. Not true leads to false. Not false leads to true. Let's see a slightly different example. The idea is to show you in this cell that the Boolean operators can be applied not only to Boolean values. The statement 3 greater than 5 is false, while 10 less than or equal to 20 is true. False and true entails false. And this is what we obtained. Good. The fun starts when you combine these logical operators. In these occasions, you must respect the order of importance of these three operators. It is not comes first, then we have and finally or. The examples in these three cells will help you get the right intuition. In the command true and not true, we should first consider what the operator not will do. It will be applied to the value true, and not true means false. Therefore, what's written in this cell must be interpreted as true and false. Now, the remaining operator and can be applied. True and false leads us to false. The answer is correct, false. Let's do an example with all three Boolean operators, false or not true and true. False or not true and true logically is the same as false or false and true, because before anything else, not true must be read as false. Then and has an advantage over or. This is why we will concentrate on the phrase false and true. Its outcome is false. We are now left with false or false. Both values are false, which always leads to false. As expected, false. To solidify the concept, let's go through another similar example. True and not true or true is the same as true and false or true, because initially, not mattered most. Now, and will convert true and false to false. Now, we can think about the remaining false or true, because the OR operator needs at least one true statement to return true. Our result after running this cell will be true. Great! Let's see what identity operators are about. The identity operators are the words is and is not. They function similar to the double equality sign and the exclamation mark and equality sign we saw earlier. Let's illustrate their application with the following examples. If we say 5 is 6, we'll immediately understand it is false. The same as if we wrote it like this, with the double equality sign. If we said 5 is not 6, that'd be true. And it will be the same as if we wrote 5 exclamation mark equals 6. Great! You have learned a lot about operators in Python and about its syntax. It is the right moment to dive into something more interesting. Starting from our next lesson, we'll deal with a topic that is a big part of a programmer's everyday life: conditionals. You are prepared to dig deeper, so do the exercises and see you in our next video. Thank you for watching. In the previous lectures, you saw how you can assign different values to a variable. In this lecture, you will see values act as the most basic or primitive data elements necessary to form not only variables, but any expressions. A prominent example of conditional statements in Python is the if statement. What you can use it for is intuitive, but it is very important to learn the syntax. Think of the following. If 5 equals 15 divided by 3, then print hooray. First, don't forget we should use the double equality sign here, because we are checking whether 5 is equal to 15 divided by 3, and we are not assigning the value of 15 divided by 3 to be 5. 5 is not a variable name, it is a number. Good. Now, it is crucial to place a colon. The colon will tell the computer what to do if the condition we just wrote has been satisfied. For achieving good legibility, we advise you to write the print statement on a new line. Please remember, it should be indented. Otherwise, you will run into an error. All right. Now this should work correctly. Yes, 5 is equal to 15 divided by 3. Hooray! Will it work if we check for 5 being equal to 18 divided by 3? It is not supposed to, since 5 differs from 6. We got nothing, because we have not told the machine what to do if the provided condition is not satisfied. So, there is no reason for the machine to print out hooray. The graph could help you imagine the process of the conditionals. Before it displays the outcome of the operation, the machine follows these logical steps. If the conditional code is not to be executed because of the if condition is not true, our program will directly lead us to some other output, or, as it is in this case, to nothing. After any of the two situations, the machine will go to the next black point and will progress from there on. Let's try with an inequality sign, which can be written with an exclamation mark and an equal sign. Isn't 5 different from 3 times 6? Yes, it is. It is true that it is different. Hence, we have hooray as an output. This was a brief introduction to if statements. This logic will help you proceed to the next lecture, where we will complicate things a little bit, but not too much. Thank you for watching. Let's assign the value of 1 to x. We can ask the computer to display case 1 if x is greater than 3, and case 2 if it is less than or equal to 3. Okay, we could write two if statements one after the other. Let's see if we get the correct outcome. Yes, we are in case 2. There is a shorter and better way to express ourselves here. In the second part, instead of saying if x is smaller than or equal to 3, we could write directly else and insert a colon. Else will tell the computer to execute the successive command in all other cases. In our little program, that would mean in all cases when x is not greater than 3. That translates into when x is less than or equal to 3. Let's verify if what we did was correct. Bingo! Case number 2.
This picture adds up to the one we saw in the previous lesson. Instead of leading to no output, if the condition is false, we will get to an else code. In our case, this is the print function with the string case2 as an argument, written in parentheses. Regardless of whether the initial condition is satisfied, we will get to the endpoint. So the computer has concluded the entire operation and is ready to execute a new one. Wonderful! Now, please allow me to share 2 notes on the subject. Don't fall into the trap of organizing your code on a whim. There is a strict manner to do that, and indentation plays a key role again. Should you put the else keyword just underneath the first print word, nothing will happen. Remember to place the if and the else keywords on the same vertical line. This is the right moment to introduce you to the notion of blocks of code. The if statement, meaning the condition plus the relevant print function, forms the first block of code. The entire else statement forms another block of code on its own. Therefore, in a long sheet with much code, you'll have a whole lot of blocks. And larger programs are constructed on a block-by-block basis.
We are ready to look at elif statements. Thanks, and see you in the next video. In this lesson, we'll learn an elegant way of adding a second if statement to one of our expressions. This is done with the help of the elif keyword, as shown in this example. If y is not greater than 5, the computer will think, else if y is less than 5. Written elif y is less than 5. Then I will print out less. And the else statement follows as a tail with the respective block that says return equal. Let's confirm we wrote the code correctly. We can print out the compare to 5 function with a value of y equal to 10 in the following way. Then we'll expect to see a statement that says greater because 10 is greater than 5. Correct? Okay, perfect. What if we carry out this operation for the number 2? The machine tells us that 2 is less than 5, and that's what we expected. To obtain the third outcome, we must compare the number 5 with a number that is not greater or smaller than 5. This will happen only if the argument of the function is 5, right? Shall we try this one? Great! We obtained equal as expected. Know that you can add as many elif statements as you need. Let's provide an example. If y is less than 0, the string negative should be displayed. I will place the block between the if and the other elif statement. Let's see what happens. The function with an argument of -3 shows negative, just as it should. Let me just control whether our little program will run properly if I asked it to compare to 5, a value that lies in the range between 0 and 5, say 3. Yes, we see less, so everything is okay. A very important detail you should try to remember is the computer always reads your commands from top to bottom. Regardless of the speed at which it works, it executes only one command at a time. Scientifically speaking, the instructions we give to the machine are part of a control flow. This is something like the flow of the logical thought of the computer, the way the computer thinks, step by step, executing the steps in a rigid order. When it works with a conditional statement, the computer's task will be to execute a specific command once a certain condition has been satisfied. It will read your commands from the if statement at the top, through the elif statements in the middle, to the else statement at the end. The first moment the machine finds a satisfied condition, it will print the respective output and will execute no other part of the code from this conditional. In our example, if the first statement is correct, we will see the corresponding output number 1, which is printing the string greater. The computer will disregard the elif and the else statements and will proceed with the rest of the code. If the first statement is not correct, we will move forward, and the computer will check whether our second statement is true. If yes, we will see output number 2, which is printing the string negative. If not, we will get to statement number 3 and so on until the computer finds a satisfactory outcome to print out. Now, I will switch the order of the two elif statements to prove that the order of instructions matters. Okay? Let me print compare to 5 of -3. Ha! Instead of negative, we obtained less. This is how the computer reasons. Assume y equals -3. Print out greater if y is greater than 5. Is it greater than 5? No. So the computer continues and checks if there are any other statements in our code. Given we have other statements, it moves forward. So is y less than 5? Yes, it is. At this moment, the computer thinks, lovely, I got it. My number is less than 5. I satisfy what my programmer asked me to do. I print out less, and I am fine. And the machine stops there and does not execute a single letter of the code that follows in this block. The fact that you examine the cases when y is less than 0 or equal precisely to 5 have no application. They become useless. Whether you ask for the output of -3 or 3, you will still have to be satisfied with the less label. You found this interesting, didn't you? Stay focused for the next lecture, when we will share something more about computational logic. Thank you for watching. You probably noticed we talked about Boolean values a few times. Here, we would like to provide a short video that aims to explain their application. Let x be equal to 2. What you see next is the following if-else construction. If the value of the x variable is greater than 4, print out correct. In all other cases, print incorrect. So, which is the Boolean element we have in this computational logic? Basically, after you insert your if statement, the computer will attach a Boolean value to it. Depending on the value of its outcome, true or false, it will produce one of the suggested outputs, correct or incorrect. If the first statement is true, that is, if x is greater than 4, the machine will print the corresponding statement, correct. Else, which means if the statement x greater than 4 is untrue, or more precisely, false, the statement incorrect will be printed. From a certain perspective, everything in a computer system is Boolean, comprising sequences of zeros and ones, false and true. This is why we are paying attention to the Boolean value. It helps us understand general computational logic and the way conditionals work in Python. Okay, excellent. We can wrap it up here. This wasn't an easy section, right? But you learned a lot and are making a great progress. Now you know more about conditionals in Python, and you understand the control flow of if, elif, and else statements. In addition, You saw once more complying with the Pythonic syntax is crucial for the execution of your code. Where you type the colon sign and indentation matters. Last, you saw the order in which you declare your commands leads to a specific outcome. If you change the order of your commands, the outcome could change, and this may take you to undesired results. Wonderful! In our next section, we'll dive into the world of Python functions. See you there, and thanks for watching. Great! Let's step it up a notch. Starting from this lesson, we'll deal with Python's functions as an invaluable tool for programmers. The best way of learning is by doing, so let's create a function and see how it can be applied. To tell the computer you are about to create a function, just write def at the beginning of the line. Def is neither a command nor a function. It is a keyword. To indicate this, Jupyter will automatically change its font color to green. Then you can type the name of the function you will use. For instance, simple, as we will create a very simple function. Then we can add a pair of parentheses. Technically, within these parentheses, you could place the parameters of the function if it requires you to have any. It is no problem to have a function with 0 parameters. This is the case with the function we are creating right now. To proceed, don't miss to put a colon after the name of the function. Since it is inconvenient to continue on the same line when the function becomes longer, it is much better to build the habit of laying the instructions on a new line with an indent again. Good legibility counts for a good style of coding. All right, let's see what will happen when we ask the machine to print a sentence. Not much, at least for now. The computer created the function simple that can print out my first function, but that was all. To apply the function, we must call it. We must ask the function to do its job. So, we will obtain its result once we type its name, simple, and parentheses. See? Great! This will do for now. Thanks for watching. Okay, good. Our next task will be to create a function with a parameter. Let it be +10 with a parameter a. That gives us the sum of a and 10 as a result. Always begin with the def keyword. Then type the name of the function, +10, and in parentheses, designate the parameter a. The last thing to write on this line would be the colon sign. Good. What comes next is very important. Don't forget to return a value from the function. If we look at the function we wrote in the previous lesson, there was no value to return it. It printed a certain statement. Things are different here. We will need this function to do a specific calculation for us and not just print something. Type return a +10. This will be the body of this function. Now, let's call +10 with an argument 2 specified in parentheses. Amazing! It works! Once we've created a function, we can run it repeatedly, changing its argument. I could run +10 with an argument of 5, and this time the answer will be 15. Great! Pay attention to the following. When we define a function, we specify in parentheses a parameter. In the +10 function, a is a parameter. Later, when we call this function, it is correct to say we provide an argument, not a parameter. So we can say call +10 with an argument of 2, call +10 with an argument of 5. People often confuse print and return and the type of situations when we can apply them. To understand the concept better, try to imagine the following. There is an argument x which serves as an input in a function, like the one we have here. The function in this case is x +10.
Given that x is an input, we can think of it as a value we already know. So the combination of x and the function will give us the output value y. Well, in programming, return regards the value of y. It just says to the machine, after the operations executed by the function f, return me to the value of y. Return plays a connection between the second and the third step of the process. In other words, a function can take an input of one or more variables and return a single output composed of one or more values. This is why return can be used only once in a function. Therefore, we can say the concept of a function applies to programming almost perfectly. There are some extra advantages to consider. You could also assign a more intuitive name to a function, +10 or addition of 10, and the function will still run correctly. This is a sign of good design. On a sheet with 1,000 lines of code, if you call all your functions x1, x2, x3, and so on, your colleagues will be confused and utterly unhappy. Naming functions clearly and concisely makes your programming code easy to understand, and it will be accepted as one of good style. There is another way in which you could organize the definition of your function. Start by defining +10 with an argument of a and a colon. On the next line, instead of directly returning the value of a +10, another variable can be created inside the function to carry that value. I will use the name result here. I will assign it with the desired value of a +10. Let's check what we just did. If I execute the code in the cell, I will get nothing. Why? Because of this moment, I have only declared the variable result in the body of our function. Naturally, to obtain the desired outcome, I will also have to return that variable. See? When I call +10 with an argument of 2, I obtain 12. It is all fine again. Print takes a statement, or better, an object, and provides it printed representation in the output cell. It just makes a certain statement visible to the programmer. A good reason to do that would be when you have a huge amount of code and you want to see the intermediary steps of your program printed out, so you can follow the control flow. Otherwise, print does not affect the calculation of the output. Differently, return does not visualize the output. It specifies what a certain function is supposed to give back. It's important you understand what each of the two keywords does. This will help you a great deal when working with functions. The following could be helpful. Let the same function also print out the statement outcome. If we put down only return outcome and then return result, what will we get when we call the function? Just the first object to return, the statement outcome. If instead we print the statement and then return result, we will get what we wanted, the outcome statement and the result of the calculation, 12. This was to show you we can return only a single result out of a function. This will do for now. Thank you for watching. It isn't a secret, we can have a function within the function. For instance, let's define a function called wage that calculates your daily wage. Say you use working hours as a parameter, and you are paid $25 per hour. So, this should work. Okay, good. Notice, I don't technically need the print command here. I could print out the wage afterwards, but I don't really need to. So, I'll proceed this way, just returning the value I need. When you do well in a day, your boss will be very happy to give a bonus of $50 added to your salary. Hence, I'll define a with bonus function for you. And as a parameter, I will take again the working hours. But this time,
I will allow myself to return directly the wage with working hours as an output, which would be the value obtained after the wage function has been run, plus the extra $50 you've earned. This is how the first function is involved in the output of the second one, a function within the function. Let's see what the output will be if you worked 8 hours today and the boss was very happy with your performance. Wage with an argument 8 and with bonus with an argument of 8. Great! 200 of base compensation and 250 with the bonus. Don't forget to do the exercises after this lecture. This is the best way to reinforce what you've learned. We know how to work with if statements, and we know how to work with functions. In this lesson, we'll learn how to combine the two. This is a fundamental concept in programming, so please pay attention. You'll encounter it quite regularly when coding. Johnny's mom told him that, by the end of the week, if he has saved at least $100, she would give him an extra $10. If he did not manage to save at least $100, though, she would prefer not to give him the extra cash. Clear? Now, let's define a function called add10, which takes as a parameter the unknown m that represents the money Johnny saved by the end of the week. What should we tell the computer to do? If m is greater than or equal to 100, then add 10 to the saved amount. If it is not, return a statement that lets us know Johnny should save more. That is, if m is greater than or equal to 100, let m assume the value of m plus 10. Yes, it is what you saw. We have m on both sides of the equation, and that is perfectly fine. As a matter of fact, it is not an equation. Remember that the equality sign stands for assigning the expression on the right side to what is written on the left side. Let's complete the if part with return m. To sum up, logically, we mention m as a parameter. Then, we substitute its value with a greater value than m with 10. At the end, we say, from now on, return a value equal to the new m. Finally, in all other cases, for instance, save more. Johnny should learn it is a good habit to have some cash on the side, right? Let's see if our intuition was correct. Add 10 of 110. Good, 120. And if m was equal to 50, amazing! Everything is correct. When you think of it from a logical perspective, it makes sense, doesn't it? What would you use a computer for? To solve problems for you. And it can do that through functions. You'll most probably need to ask the machine to execute something if a given parameter is within certain limits, and ask it to execute another thing if the parameter is beyond these limits. Therefore, combining your knowledge about conditionals and functions in Python comes right on the money. Great! Just keep the pace for our next video. Thank you for watching. We are almost there. In this lesson, we'll learn how to work with more than one parameter in a function. The way this is done in Python is by enlisting all the arguments within the parentheses, separated by a comma. Shall I call the function we have here for, say, 10, 3, and 2? I get 4. Seems easy to add a few parameters, right? And it is. Just be careful with the order in which you state their values. In our case, I assign 10 to the variable a, 3 to b, and 2 to c. Otherwise, the order won't matter if and only if you specify the names of the variables within the parentheses like this. b equals 3, a equals 10,
and C equals 2. And of course, we could obtain the same answer. 4. This is how we can work with functions that have multiple arguments. Awesome! Let's see what's next. When you install Python on your computer, you are also installing some of its built-in functions. This means you won't need to type their code every time you use them. These functions are already on your computer and can be applied directly. As a matter of fact, you saw examples of built-in functions in the lesson about data types. The function type allows you to obtain the type of variable you use as an argument. Like in this cell, type of 10 gives int for integer. The int, float, and string functions transform their arguments in an integer, float, and string data type, respectively. This is why 5.0 was converted to 5, 3 was converted to 3.0, and the number 500 became text. Great! Now, let me show you a few other built-in functions that are quite useful. Max returns the highest value from a sequence of numbers. This is why Max returned a value of 30 as an output in his cell. Good. Min does just the opposite. It returns the lowest value from a sequence. So, we get 10 in that cell over here. It is the smallest among 10, 20, and 30. Another built-in function, abs, allows you to obtain the absolute value of its argument. Let z be equal to minus 20. If we apply the abs function to z, the result will be its absolute value of 20. See? Perfect! An essential function that can help you a great deal is sum. It will calculate the sum of all the elements in a list designated as an argument. Consider the following list made of 1, 2, 3, and 4 as its data. When I type sumList1, my output will be equal to 1 plus 2 plus 3 plus 4. The sum of these numbers equals 10. Round returns the float of its argument, rounded to a specified number of digits after the decimal point. Round 3.555 with 2 digits after the decimal point will turn into 3.56. If the number of digits is not indicated, it defaults to 0. 3.2 is rounded down to 3.0. Great! If you are interested in elevating 2 to the power of 10, you know you could type 2 $10. You can get the same result if you use the pal function, which stands for power. Write pal, and in the parentheses, specify the base and the power, separated by a comma. In our case, 2, 10. Execute with Shift and Enter, and voila! 1024. And what if you wanted to see how many elements there are in an object? The len function, as in length, is going to help you do that. If you choose a string as an argument, the len function will tell you how many characters there are in a word. For instance, in the word mathematics, we have 11 characters. There are many other built-in functions in Python, but these are a few examples you will often need to use when programming. Thank you for watching. Great! We've made excellent progress so far. By now, you know a bit more about Python's syntax, about if, elif, and else statements, and about functions. In this section, we'll cover an important topic for Python programming: lists. So, what is a list? A list is a type of sequence of data points such as floats, integers, or strings. Therefore, understanding lists relates to your ability to organize data, a crucial skill in today's labor market. Moreover, you'll see Python creates a friendly environment for dealing with lists. Assume you wanted to create a list called participants that contains the names of John, Leela,
Gregory and Kate. Follow the rules about creating a generic variable, but be careful about two things. Place the strings within square brackets and make sure you use quotation marks. Precisely. These brackets indicate the elements inside form a list and not some other type of a sequence. Good. We see the participants list has already been prepared. Am I going to be able to extract the name of one member of the group? Of course I can. Do you remember how we extracted the letter D from Friday? Using brackets after the word Friday. The logic here is the same. I'll write the name of the list, and in brackets, I'll indicate the position corresponding to the name I am interested in. It is important that I don't use parentheses or braces. For instance, let me extract the name of Leela. As programmers, we start counting from 0. So, 0, 1. 1 should be the correct position. And it is. For the sake of argument, in such a situation, a computer scientist might say you have accessed the list by indexing the value 1. This means you have extracted the second of the elements in this list variable. Okay, nice. In addition, there is a way to get to the last element from your list. Start counting from the end towards the beginning. Then, you need the minus sign before the digit, and don't fall in the trap of thinking we begin enumerating from 0 again. To obtain Kate, we have to write -1. To obtain Gregory, we need -2. Okay, now let's study a key feature of lists, replacing or deleting items in a list. Let's assume Kate had to quit for some reason, but Maria could replace her. Here's what we can do. Across the value at position number 3, which currently refers to Kate, and assign it with the string Maria. Let's check if our intuition was correct. 100%. Amazing! Another scenario. Unfortunately, Gregory got a better offer somewhere else, so he quit as well. There's nobody to replace him, but we must adjust our list accordingly. The del keyword could deliver the required result. Type del, then correctly index Gregory's position by typing participants 2. And voila! Important to note is that deleting an element changes the indices of all successive elements. After removing Gregory, Maria's position shifted one place to the left and is now at the second position. There is no element at the third position. In our next lesson, we'll learn what to do if we have to add a new person to our list. Thank you for watching. So, a new name, Dwayne, needs to be added to the participants list, and we'll use a method called append. Think of the terms method and function as interchangeable, because in practice, methods work quite like functions. However, the technically correct term to use in this situation is method. Here is the syntax that allows you to call ready-made built-in methods that you do not have to create on your own and can be used in Python directly. After the name of the object, which in this case is the participants list, we'll put a dot called a dot operator. The dot operator allows you to call in or invoke a certain method. To call the method append, state its name, followed by parentheses. To insert the name Dwayne in our list, we must put the string Dwayne in inverted commas between the parentheses. After we execute the cell, we should have Dwayne added to our group. Shift and Enter. Correct. Great. Remember this general structure because we have to comply with it if we wish to call any existing method in Python. Alternatively, the same result can be achieved by using the extend method. Let's invite George and Catherine in our group. First, let's invoke the extend method. Okay, good. This time, within the parentheses, we'll have to add brackets as we are going to extend the participants list by adding a list specified precisely in these parentheses. Execute through Shift and Enter, and you'll have the two pieces attached: the initial participants list and the extension. Thus, you still manage to enlarge your original list, right? A couple more things before we close this lesson. First, let me show you that lists' elements are directly treated as string values. After printing this command, we can see the first participant in our list is John. It was not necessary to put any quotation marks around the participants element to do that. Perfect. Finally, the len built-in function counts the number of elements in an object. For instance, if our word is dolphin, this function tells us it is composed of 7 letters. More importantly, though, this same function can be applied for obtaining the number of elements in a list. Applied to the list we have here, it shows us the list entails 6 members. Awesome! To summarize, observe how a built-in function takes the object participants as an argument, while when we are calling built-in methods, they are applied to the participants list with the help of the dot operator. The different syntax helps you distinguish between the two. By the way, lists can be sliced too, but more on that in our next video. Thanks for watching. In this lesson, we'll introduce you to another very important concept: slicing. In the future, when working in Python, you'll typically have to deal with data that is quite big. Many of the problems that must be solved will regard a tiny portion of the data, and in such cases, you can apply slicing. Imagine you want to use the participants list we saw earlier to obtain a second much smaller list that contains only 2 names, Leela and Maria. In Pythonic, that would mean to extract the elements from the first and second position. To access these elements, we will open square brackets, just as we did with indexing, and write 1:3. The first number corresponds precisely to the first position of interest, while the second number is 1 position above the last position we need. In our case, 2 + 1 = 3. Correct. We can say we just sliced our participants list to obtain a new one with the names Leela and Maria. I know this piece of syntax seems a bit strange, but it is not that illogical. Let's get the first 2 names from the list, John and Leela. In this case, you don't need a number at the beginning, and you can start by typing a colon. Okay, so by typing :2, we get exactly the first 2 elements. Very good. And how can I obtain the last 2? One way would be to indicate the 4th position, corresponding to George, and leaving nothing after the colon. This would mean we will extract all the elements from the 4th position included to the end of our list. Another way to obtain the same result would be to put a minus sign in front of the number 2. Thus, Python will revert the direction of counting, starting from the end towards the beginning. How many elements are we asking for? 2. Let's execute. And here's the output. We've obtained George and Catherine in a new list. Perfect. Okay, let's check out some additional methods that can be applied to lists. Assume you know Maria is in your list, but you don't know her position. In other words, you'd like to obtain the index of the element Maria from the participants list. Just call the index method and indicate the string variable of interest in parentheses. The machine tells us Maria is in the 2nd position. And it is. The next functionality is an interesting one. I will show you it is possible to create a list of lists. My goal will be to create a list called Bigger List, which contains the participants list and a new one I will call Newcomers. Let the latter enclose the names of Joshua and Brittany. Shift and Enter. Okay, we created Newcomers. All I need to do in the next cell is write the name of the variable Bigger List and cite within brackets the names of the lists I would like to include.
let's verify if this works. Yes, it does. The two lists are shown in the suggested order. Great! An important method that could order the names of your participants in alphabetical order is sort. As you can see, after applying it to our list, Catherine comes first and Peter is last. If within the brackets, we say we would like the names to be sorted in a reversed order by stating reverse equals true, Peter would be first and Catherine last. Naturally, if our elements were sheer numbers instead of people's names, this method would function without any problems. Observe how, in this example, I sorted the numbers from 1 to 5 from the smallest to the largest. And here, from the largest to the smallest. Wonderful! This was a very important lecture. Stay tuned for the next one, where we will discover what is a tuple. Tuples are another type of data sequences, but differently to lists, they are immutable. Tuples cannot be changed or modified. You cannot append or delete elements. The syntax that indicates you are having a tuple and not a list is that the tuple's elements are placed within parentheses and not brackets. By the way, the tuple is the default sequence type in Python. So if I enlist 3 values here, the computer will perceive the new variable as a tuple. We could also say the 3 values will be packed into a tuple. For the same reason, we can assign a number of values to the same number of variables. Do you remember we went through that a few lectures ago? On the left side of the equality sign, we just added a tuple of variables, and on the right, a tuple of values. That's why the relevant technical term for this activity is tuple assignment. In the same way we did for lists, we can index values by indicating their position in brackets. That's why we obtain the first number from the tuple x, namely 40. In addition, we can also place tuples within lists, and then each tuple becomes a separate element within the list. Tuples are similar to lists, but there are some subtle differences we should not overlook. They can be quite useful when dealing with different comma-separated values. For example, if we have age and years of school as variables, and I have the respective numbers in a string format, separated by a comma, hence the name comma-separated values, the split method with the proper indication within the parentheses will assign 30 as a value for age and 17 as a value for years of school. We can print the two variables separately to check the outcome. Everything seems to be correct. Awesome! Last, functions can provide tuples as return values. This is useful because a function, which can only return a single value otherwise, can produce a tuple holding multiple values. Check this code. I will input only the length of the side of a square, and as an output, the squareinfo function will return a tuple. The tuple will tell me the area and the perimeter of the square. This is how we can work with tuples in Python. Thanks for watching. Now that you know what lists and tuples are, you will more quickly understand what dictionaries are about. Dictionaries represent another way of storing data. Each value is associated with a certain key. More precisely, a key and its respective value form a key-value pair. In this example, we have 4 keys. Different names of animals are attached to each one of them. Pay attention that neither parentheses nor brackets will work in this case. You need curly braces. After a certain dictionary has been created, a value can be accessed by its key.
instead of its index. K1 can be used for cat, while K3, a mouse. Similarly, as we could do with lists, we could add a new value to the dictionary in the following way. The structure to apply here is dictionary name, new key name within brackets, equality sign, and the name of the new value. The value we'll assign to key number 5 is parrot. I'll press Shift plus Enter and we are good to go. Replacing a value follows the same syntax. Just let the new variable correspond to an existing key. From that moment on, attached to the second key, we won't see a dog anymore. Ha! It's a squirrel now. You feel a list should be able to take part in a key-value pair. And you are right. Let's turn to another example. Say, only Peter works in Department 1, but 3 people work in Department 2, Jennifer, Michael, and Tommy. Shall we verify? Right. Therefore, our second element is a list. There is another way to fill in a dictionary. I'll create a new variable and we'll use empty curly braces to indicate it'll be a dictionary. I will not place any keys or values within the braces. Instead, I will assign the keys and the values one by one. And, at the end, my dictionary will be full. Quite nice. And if I asked for the center, I will see Hector's name. Let me introduce you to an interesting Python feature. If the get method gives us the name of the small forward of a given team, the machine won't display an error if we ask for the name of the coach, whose name does not take part in my dictionary. None is the default value Python returns in cases where an object does not actually exist within a given dictionary. Now, you can imagine that dictionaries could do a great job, sometimes. For instance, when using companies' names as keys and their prices on the market as values, right? Bravo! You are going deeper into programming. Remember, things will remain quite abstract unless you take the time to practice and apply what you've learned in these lessons. So, roll up your sleeves and do the exercises attached to this lesson. Thanks for watching. Iteration is a fundamental building block of all programs. It is the ability to execute a certain code repeatedly. In this section, we will focus on a few examples of iteration processes in Python. To begin, we have prepared a list called even. It contains all the even numbers from 0 to 20. Imagine we want these numbers printed out, so we can write the following. For in and even, colon, which would mean for every element in the list even, do the following. Print that element. In this case, in is called the loop variable. It is not required to have called it in. Any other name would have worked fine.
The phrase print, open parentheses, in, close parentheses, acts as the body of our loop. Don't forget, it should be indented to run the loop properly. The operation in the loop body is performed once for each element in the even list. Now, let's go over the steps implied by this piece of code. The loop starts by taking an element in from our list. Then, the computer executes the body of the loop. In our case, it will simply print that variable. When the computer is done with this operation, called iteration or pass of the loop, Python will go back to the for statement and pick the next element in that is in the even list. It will then print out, and so on and so forth until the loop body has been executed for all available elements in the list. Right, let's apply this code to see the outcome. Exactly as expected, all numbers were stated in a column. What if we wanted to see them ordered in a single line? A comma after the element in the parentheses after the print function, and an in parameter with a value of an empty string will help us achieve that. Note that to specify an empty string, you need to type an empty space between a pair of double quotes by pressing the spacebar on your keyboard once. Thus, the comma and the in parameter will indicate every next element from the loop should be placed with a distance of one space on the same row. And if the elements you're about to print are too long, they will be displayed on multiple rows in the output cell. But you don't need to worry about that at the minute. This was a short but important introduction to the concept of iteration in programming.
See you in the next video, and thanks for watching. The same output we obtained in the previous lesson could be achieved after using a while loop instead of a for loop. However, the structure we will use will be slightly different. Initially, we will set a variable x equal to 0, and we'll say, while this value is smaller than or equal to 20, print x. But please be very careful, and I mean it. If you leave the code until here, you will run into an infinite loop, and your computer will crash. This is a situation you want to avoid, right? So, be very careful. Since x will always be smaller than 20, your loop will be infinite. It will iterate the same variable repeatedly. This is what we did here with x equals 0. And always is not what we want in an iteration. We want to get the loop to end. What is supposed to succeed the loop body in the while block is a line of code that specifies a change in x, or what has to happen to x after it is printed. In our case, we will tell the computer to bind x to a value equal to x plus 2. Let's see if it works. Awesome! This is much better. Actually, there is a term for what we just did. In programming terms, adding the same number on top of an existing variable during a loop is called incrementing. The amount being progressively added is called an increment. In our case, we have an increment of 2. Furthermore, the Python syntax offers a special way to indicate incrementing. X plus equals 2 shows we are incrementing the value of 2 on top of the base x, just as if we had typed x equals x plus 2. As you can see, the two outcomes are the same. To conclude, whether you will use a for or a while loop will depend mainly on your personal preferences. What matters is that your code does not crash and provides correct results. Right? Thanks for watching.
Later in the course, we will need to randomize data points and lists with data points, and that's when we'll be able to use Python's built-in range function. It can help us by creating a Python range object, which actually is a mere sequence of integers.
The syntax of the function is the following. Type range, and in parentheses, mark a start, stop, and step value. The start value will be the first number in the list. The stop value will be greater than the last value in the list. It is going to be equal to the last number plus 1. Just classical Pythonic logic, right? The so-called step value represents the distance between each two consecutive values on the list. The stop value is a required input, while the start and step values are optional. If not provided, the start value will be automatically replaced with a 0, and the step value would be assumed to be equal to 1. You could also remember the stop value as most important, the start value as less important, and the step value as least important.
For this reason, range of 10 will provide a sequence of 10 elements, starting from 0, implied after not indicating a start value, and ending at the 10th consecutive number, number 9. Python, however, will not display the sequence in the form of a list. Instead, it will show this as a range 0, 10, which stands for a range object with a start value of 0 and a stop value of 10. To display the sequence in a list, we can take advantage of the Python built-in list function, using this very same range function as an argument. In that case, we will obtain a list containing all integers from 0 to 9. The trick that was just introduced to you is something you will need to have under your belt if you are using Python 3 and want to check the values generated by a given range function. Also, remember that Python 2 will handle the situation in a different way. It will directly create and display the sequence as a list, as opposed to a range object. We will show how this can be done later in this lecture. And that's pretty much all you have to know about the range function in Python 2 or 3. That said, let's take a look at two other examples. In another cell, if for instance, in the range function, we declare as arguments 3 and 7, Python will accept 3 as a start value and 7 as a stop value of the range. So we obtain a list from this range function. We see that we have 4 elements, 3, 4, 5, and 6. Good. In another example, we may want to specify a step value in a range. To do this, we must choose the first 2 arguments as well. So let's obtain a list with all the odd numbers from 1 to 19 included. I will start with the number 1, and the list will end with number 19, which equals the stop value 20 minus 1. To state the odd numbers only, we must designate a step value of 2. As we execute this cell, we will obtain the corresponding range object. To see the values displayed in a list, we can use the same range function as an argument of the list function. Thus, we'll obtain the desired result, which means that we have worked correctly.
This is how we can create lists with Python's range function. In our next lecture, we'll see how it can be applied in practice. Thanks for watching.
Now that you know what the range function does, let's see it in a for loop. To print all the values from 2 to the power of 0, 2 to the power of 1, and so on until 2 to the power of 9, we can use the following code. For in range of 10, print 2 $n, written in parentheses. I will also have to insert a comma and specify an n parameter with a value of an empty string after n, because I would like to see the output on a single line. Good. I guess you can agree it was not necessary to designate the name of a list that exists in our code. Using a sequence of numbers generated by the range function is going to work too.
Now, let's be brave and create an iteration that includes a conditional in the loop body. We can tell the computer to print all the even values between 0 and 19 and state odd in the places where we have odd numbers. Let's translate this into computational steps. If x leaves a remainder of 0 when divided by 2, which is the same as to say if x is even, then print x on the same line. Else, which means unless x is even, or if x is odd, print odd. Lovely! This is an example of a combination of an iteration and a conditional in Python. There are 2 main ways to program a loop, and until this moment, we paid attention only to the first one. We have a list x that contains the numbers 0, 1, and 2. We saw we can print out each of its elements by typing for each item in the x list, print out that item. The second way finds its practical application in more sophisticated codes. Its structure takes advantage of the range and len functions in the following way. For each item in a range that goes through the elements from the list x, that is, len with an argument x, print out each item. If we do this, the variable item will loop through a new list created by range, and that has as many elements as the X list itself. Please note that in this situation, the second line of our code needs indexing to extract each item from the X list. In practice, we will print out the element at position 0 from the list X, then the element at position 1, and finally the element at position 2. To conclude, both approaches can lead to the same outcome. Although the second one looks unnecessarily complicated, in advanced coding, it might turn out to be a lot more useful. So, it is important you know both. Don't skip the exercises that come with this lecture, as they will reinforce what you've learned here. Thank you for watching. We use iterations when we have to go through variables that are a part of a list. In this lesson, I'll show you how to count the number of items whose value is less than 20 in a list. First, define a function that takes as an argument numbers, where numbers will be a certain list variable. The trick is to create a variable that, so to speak, departs from 0. Let's call it total. The idea is that when certain conditions are verified, total will change its value. This is why in such a situation, it is appropriate to call this variable a rolling sum. More technically, when we consider X in the numbers list, if it is smaller than 20, we will increment the total by 1. And finally, return the total value. This means that if X is less than 20, total will grow by 1, and if X is greater than or equal to 20, total will not grow. So, for a given list, this count function will return the amount of numbers smaller than 20. Let's verify if this function works properly. In this list, we have 4 numbers that are less than 20, right? Let's check that out. Great! Now, if I add 17, for example, somewhere in the list, the outcome will adjust accordingly. 5. Exactly. Perfect. By the way, look how the whole if statement is indented even more to the right. This allows us to separate it logically from the rest of the code in the cell that refers to this function. If you are eager to know how to iterate over a dictionary in Python, and I am sure you are, you will see this in our next video. Thank you for watching.
Hi there. Let's explore the capabilities of the Anaconda Assistant. This tool is so powerful that it can even help us start solving a particular programming problem if we find it challenging. To illustrate this feature of the Anaconda Assistant, let's click the plus sign in the top left corner of the screen to create a new notebook. Then we'll task the Anaconda Assistant with a clear and concise challenge. Create a function that takes a list object as a parameter and that counts the number of values in it smaller than 20. Wait for a couple of seconds, and brilliant! We obtain not only a solution, but also a suggestion for an argument value to use with the function. Let's run both pieces of code in the notebook. First, create the function that performs the required task, and then apply it to a list containing the values provided by the assistant. As you can see, it works correctly. Perfect! Now, let's compare the structure of the new function to the one we discussed earlier in our lecture on coding in Jupyter. In terms of structure and functionality, both functions are identical, right? Okay, right. This means we can be quite happy about the assistant's output and our own work. The only difference between the two functions is their variable and function names used within them. So let's use this as an opportunity to see how we can continue our conversation with the AI assistant in such scenarios. Remember, try to always be as precise in your communication with it as possible. Suppose our task now becomes renaming all object names from the piece of code we just obtained to match those used in our lecture. For instance, we can directly write and execute rename function to count. Good. What else do we need to do? Change the input parameter name from LST to numbers. Click Enter or the green button to submit the request. And again, we obtained a good response. In fact, I can address 2 necessary modifications with a single request. As usual, I'll try to be as precise as possible. I'll ask about changing the iterator variable name to X and the count variable name to total. Execute, and we end up with the code we used in the lecture. Did you notice how using the correct terminology helped us proceed with a single request? Let's run the last 2 cells we obtained to execute the function with the desired name and apply it once to a sequence called myList. Here's a moment in which we need to be very careful. This is also where our experience as programmers can play a key role. While we may generally be satisfied with our work in this Anaconda notebook, sometimes asking too many questions may lead the assistant to a point where it contradicts itself. To illustrate my point, I'll intentionally ask a vague and confusing question, contrary to the principle of concise and specific inquiries. I'll ask several times if the function just created was meaningful. If you check the responses attentively, you will notice that they are not identical, and that the AI tool might start having doubts. Therefore, we must carefully read what the assistant suggests and spot potential errors. If a mistake has been made, you can start a new chat or go a few steps back. To do the latter, press the bin icon associated with the questions you'd like to disregard until you get back to the point where you're comfortable continuing. After going back a few steps, I can ask the assistant if it could find an alternative solution to the initial task. Perhaps by using a while instead of a for loop. To do that, I'll type and execute the following request. Can you create a function that has the same purpose and structure, but uses a while instead of a for loop? Note that the models generated a function using essentially the same variable names as where we resume the conversation. For instance, the function name is count, the parameter name is numbers, and so on. Run the newly obtained code from the chat to confirm you're satisfied with the work. Great. This type of communication can be handy, mainly when dealing with large datasets or more complex and longer sheets of code. In such situations, you could remove parts of the conversation to return to a point when you were satisfied with the AI's output and proceed from there. To conclude, please remember that when used carefully, the assistant can provide solutions just in the blink of an eye, potentially saving you hours of work. As you can see, this is only possible if we ask the right questions. To do this effectively, we need a solid understanding of programming in general, and Python in particular. The more we know, the further the AI assistant can take us. Therefore, it's essential to acquire a broad range of Python skills and engage in as many exercises as possible to optimize the use of this prompt generator. To help you with the latter, you can download the guidelines we've provided as a resource for this video. This will do for now. Thanks for watching.
Let's look at something a bit more challenging, iterating over a dictionary. We have a couple of examples here. The prices of a box of spaghetti, of a portion of lasagna, and of a hamburger are stored in a dictionary called prices. Jan went to the supermarket and bought 6 boxes of spaghetti, 10 pieces of lasagna, and no hamburgers. This data was stored in a dictionary named quantity. Our problem is, how much did Jan spend in the supermarket? Well, it is obvious you'll need to multiply the quantity of each food by its price. You must have noticed our dictionaries have exactly the same keys. We should exploit this. The procedure to go to the box of spaghetti in the first dictionary and take the value of 4, then get the value of 6 from the quantity dictionary, and then multiply those two must be repeated for each food product. That must ring a bell. I am sure you probably think the same. We need a loop. Okay, that's clear. But what are we going to do with it? What is the loop's body going to contain? Before anything else, some variable must account for the amount of money spent, right? Let's implement a well-known trick. I'll create a rolling sum called money spent, which will initially assume the value of 0. So, we can start by iterating over each item in prices, I in prices for short. At every step of the loop, I would like the money spent variable to grow by the product of the price and the quantity of a certain good I. And that should be enough. Let's print the result to check whether we are working correctly. Apparently, yes. Wow! Such a simple problem in terms of mathematics required to connect knowledge on dictionaries, iteration, and creating a variable with an increment. So, from a programmer's perspective, the problem looks different. The good thing is that, at the end, this whole thing boiled down to a mere 4 lines of coding. As a side note, do you realize that if we put quantity instead of prices here, the outcome will remain the same? So, what is the conclusion? It does not matter if you loop through prices or through quantity, because the two dictionaries contain the same keys. And this is the reason this loop works correctly too. This section was a bit more complicated, wasn't it? The exercises you will find after this lesson will be more challenging, so it is quite important you solve them. Thanks for watching.
In this lesson, we'll explore another impressive functionality of the Anaconda Assistant. Rather than seeking code creation or debugging, we'll tackle this from the reverse angle. To begin with, we'll input a code snippet that's functioning correctly. It consists of 2 dictionaries, a variable, an iteration containing the 3 elements, and a print function. By clicking on the Anaconda Assistant icon at the top of the given code cell, we can select from 3 options. The first one offers to clearly explain the mechanics used behind each part of the selected code. This feature can be very useful if your colleagues have given you complex programs and you need to understand their work. Now, imagine you're in the opposite situation. You've already prepared a functional program to pass on to your colleagues. Suppose your code doesn't contain any comments, which is essential to add to your work when you're part of a team. In such a case, choose Add Comments to the selected code. If you're satisfied with the clarifications, click Replace Selection. This will immediately apply the generated comments to your notebook code cell. It's now clear how we can obtain explanations and comments. But we can also choose the Refactor the Selected Code option. What does that functionality stand for? It's similar to the code explanation we just obtained, but also includes suggestions about cleaning it of useless segments or simplifying it. In other words, this feature can be convenient if you want to improve your code's interpretability. But there's a hidden risk. You might obtain suggestions involving unfamiliar tools. In this example, the assistant suggested using list comprehension, a great Python tool we'll focus on later. So we'd better take it one step at a time. First, advance your Python skills before optimizing the use of this assistant, right? There's nothing wrong with consulting the Anaconda Assistant when you need an explanation of an error you've encountered, or if you're stuck in your coding. So feel free to use it whenever necessary. I hope you enjoyed watching this video. See you in the next one.
Hello and welcome to this Introduction to Natural Language Processing course. We'll be delving into the exciting field of NLP, and looking at techniques that enable computers to understand, generate, and classify human language. You won't need any prior knowledge on NLP to get started with this course, just some basic Python skills and maybe a little familiarity with machine learning. This first section of the course sets the stage for our exploration, where we'll be looking at what we mean by NLP and some applications in our everyday lives. We'll then move on to text pre-processing, which is arguably one of the most fundamental aspects of natural language processing. We'll work through each of the topics step by step and then add a practical lesson to allow you to practice your new skills. In section 3 of the course, we'll be looking to extract key components of our text through parts of speech tagging and named entity recognition. And in section 4, we move to understand the emotions in our text through sentiment analysis. We then move on to see how we can prepare data for further machine learning, and we'll cover text vectorization. Once we've done this, we're ready to move on to more advanced topics such as topic modeling and creating our own custom classifier for our text. Section A is a full practical case study where we'll take everything we've learned and apply it to a real-world business problem. You'll then have a notebook to add to your portfolio and show off your new NLP skills. The course concludes by discussing the future of NLP, and we'll cover deep learning and large language models, and talk about where NLP might be heading next. So let's embark on this exciting journey together. Let me introduce myself before we get started. My name's Lauren Newbold, and I've been a data scientist for several years, both at large organizations and small startups, working on a whole range of different problems. Most recently, I built a custom text classifier using state-of-the-art NLP technologies to classify text coming from interview data in developing communities. I've also spoken at several conferences about the benefits that NLP can provide for developing countries. I have a passion for getting people excited about data and the insights it can provide, so I'm thrilled that you decided to do this course with me. Now that I've introduced myself and the course, let's get started with our first lesson where we introduce what we mean by natural language processing. Natural language processing, often just abbreviated to NLP, is a field of AI that allows computers to understand, interpret, and generate human language data similar to how we would communicate with one another. There's a wide array of techniques used to process and analyze this data, involving statistics, machine learning, and deep learning. NLP came to life in around the 1950s, but early methods focused on rule-based systems, taking grammatical rules of the language and using this to try and process the text. However, if you've ever learned a language before, you'll know that trying to just learn simple grammatical rules isn't enough to be able to speak and have a conversation like you truly understand that language. More recently, we've had massive advancements in technology and the availability of large datasets for training our NLP models. This has led to now having things like ChatGPT that can really effectively understand and communicate with human-like language. For data scientists, NLP provides such a powerful set of tools for gaining insights from text data. This might have had to have been done manually before, or just not at all. So by leveraging NLP techniques, you'll be able to save massive amounts of time and uncover insights that previously might not have been uncovered. In our next lesson, we'll be looking at some examples of how NLP systems interact with our everyday lives. Let's illustrate how far NLP has come and how much it interacts with our everyday lives with a few examples. One key example is search engines that will use NLP to understand a user's query and provide relevant search results. NLP techniques are used to extract keywords, understand the intent of the user's query, and return relevant and matching web pages. Another great example is how your email account can automatically detect spam emails. Classification algorithms can be used to find patterns that differentiate between unwanted and legitimate emails. Customer support systems and chatbots also use NLP to understand customer queries. Data scientists can build conversational agents that can understand what the customer is asking for and provide relevant responses back. There are so many more examples that we can go through, and I encourage you to try and think of a couple more. At the end of this course, you'll have the initial building blocks to start building your own NLP solutions. Supervised and unsupervised learning are two fundamental approaches to tackling different types of NLP problems. Which you'll use will depend on the data that you have and the questions that you're trying to answer. The sections in this course will go through both supervised and unsupervised machine learning solutions for NLP. So before we do this, let's make sure we understand what we mean by supervised and unsupervised learning. Supervised learning involves training an algorithm to learn the relationship between the input, which would be our text data, and an output that we also provide. Say, for example, you have a data set of reviews. You have the review text, and then each reviewer also gives a review score out of 10. You can feed this into a supervised machine learning algorithm that will learn the relationship between the input text and the score to be able to make predictions about the score on new text data. On the other hand, unsupervised learning doesn't need labels. It can find patterns in the data without it. So for example, if you've ever done any clustering before or you've heard of clustering, this is a great example of an unsupervised machine learning technique. Unsupervised learning is great when you have unlabeled data but still want to be able to identify patterns or group similar items together. The choice between the two approaches depends on the availability of labeled data and the specific insights and questions that you're looking to answer. Now that we've got some understanding of what we mean by NLP and some of the techniques and approaches used, let's get started and put this into practice. In natural language processing, one of the most important factors that will determine the accuracy of any machine learning or insights that you're trying to get is the quality of data that you provide and how that data has been cleaned up. You might have heard the phrase garbage in, garbage out before. This essentially means that if you're feeding an algorithm with garbage data, so data that's not been cleaned up properly, it's not in the right format, there's loads of noise in there, then any kind of accuracy of your machine learning is going to be affected by this. There are a number of steps involved in pre-processing our text data and getting it ready for further analysis. The first step is just general cleaning, so taking our data set, getting it organized, tidying up the text, removing anything that might throw us an error, anything like that. The second step is removing noise from our data set. So if we've got aspects in our data that aren't adding any value and they're just taking up space in memory, we can remove these and we'll be left with a smaller, cleaner data set to work with. The third step is just getting that data in the right format for the machine learning algorithm we want to use. Reprocessing our text data will take it from looking something like this to this. We can see there have been a lot of transformations done here, and the lessons in this section are going to cover this step by step, taking you through each of the transformations required to get that data ready for any further analysis. With that said, let's get started now into our journey of natural language processing. Alright, let's now set up the NLP environment we'll be using in Python. To do that, we'll create something called a virtual environment. Think of it as a dedicated workspace for your project, which comes with its own Python version and its own set of installed packages. This setup has two key advantages. First, you can install the exact package versions required for this course. Second, you won't risk breaking other Python projects on your computer. We'll create and manage this environment using Conda, which is both a package manager and an environment manager. To get started, open the Anaconda prompt on Windows or the terminal on macOS or Linux. Once the window is open, you can type the following command for creating a new Python environment: conda create --name NLP course ENV. which will be the name of our new virtual environment, and the Python version we'll be using, which in this case is 3.11. We strongly recommend using this exact Python version, as it has been thoroughly tested and works smoothly with all the packages and dependencies required for this project. Once the environment is created, we need to activate it so we can work in it. So, type conda activate followed by the name of the environment we've just created. Then press enter. When the environment is activated, you'll see its name appearing before the next command line, like this. This means that any Python packages we install from now on will be added only to this environment and won't affect anything else on your system, unless we deactivate the environment or open a new Anaconda prompt. To install those packages, we'll use pip, Python's built-in package installer. Think of it this way. Conda is like setting up the room. It creates the environment itself. And pip is like bringing in the furniture, the libraries and tools we'll be working with. As we mentioned earlier, Conda can also install packages, but here we'll use pip because some packages are easier to get from PyPI, the official Python package index. PyPI often provides a wider selection of packages and faster access to updates than Conda alone. When using pip, the only difference is the command. Instead of typing conda, we simply type pip. For this course, we've prepared all the required packages, along with their specific versions, in a file called requirements. You can download this file from the resources section of the lesson. Then simply copy the entire command from the file, paste it into the terminal, and hit enter to install everything at once. Don't worry if this process takes a while. That's completely normal. Once the installation is complete, we can move on to downloading a language model from spaCy, a popular open-source library for advanced natural language processing in Python. We'll be using it throughout the course for various NLP tasks. Later on, you'll also learn how to download the model directly in Jupyter Notebook, but to save time, we'll do it here in advance. Type Python, followed by a dash before an M, then spaCy, download, and the name of the model. Perfect. The only thing left to do here is to register the environment as a Jupyter kernel. This ensures that we can select and use this specific environment directly inside Jupyter Notebook, so all the packages we've installed will be available when we start working on our NLP projects. Type Python, followed by a dash and M, then ipkernel, and finally the command to install it with the environment name we set up earlier. Good job! Now you're ready to start your NLP journey in Jupyter Notebook. But before writing any code, there's one more thing to check. Open Anaconda Navigator. Then select the correct environment from the drop-down menu right here. Next, install Jupyter Notebook in your new environment. Launch it, and make sure you've selected the right kernel as well. That's it. You're all set. See you in the next lesson. Typically, one of the first steps when working with text data is to convert everything into lowercase. We do that because we want our computer to treat words consistently. To a human, the words dog with an uppercase D and dog with a lowercase d obviously mean the same thing. But to Python, these are two different strings, simply because one starts with a capital letter. This can cause problems. For example, if you were counting how often a word appears in a text, Python might count both versions of dog separately. Lowercasing helps us avoid this issue by making sure everything follows the same format. It's essential, however, to note that sometimes capitalization does carry meaning. For example, US in uppercase usually means United States, while US in lowercase means you and me. So, depending on your project, you'll want to think carefully before lowercasing everything. Python makes lowercasing text simple with the help of a method called lower. When we call this method, it creates a new version of the string with all the letters turned into lowercase. Let's try it with a simple sentence. Her cat's name is Luna. I'll store it as a string in a variable called sentence and execute the cell to create it. To convert all the letters from this string to lowercase, we must apply the lower method to the sentence variable, like this. I'll store the result in another variable, which I'll name lower sentence. Now let's print it and see what we'll obtain. We see that the word her and the name Luna are converted to lowercase. Perfect. The lower method doesn't just work on one sentence, it works on any string. That means if we have a list of sentences, we can loop through each one and convert them all to lowercase. Let's demonstrate with an example. First, I'll store this list consisting of 3 sentences in a variable called sentenceList. Then, to apply the lower function to the list of sentences, I'll use simple list comprehension. In a separate variable, I'll create a new list for the sentences, but instead of typing out each one, I'll use the letter X. Here, X is just a temporary name Python gives to each sentence as it goes through the sentence list, defined by the for loop. Next, I'll apply the lower method to X. This way, I instruct Python to convert each sentence in the list to lowercase. By putting this inside square brackets, Python will automatically collect all those lowercase sentences and place them into a brand new list, which I'm calling lower sentence list. Let's run the cell. Yes, this is precisely what happened. The lower method is beneficial when working with text data, especially in natural language processing or machine learning, as it maintains consistency and simplifies the workflow. In the next lesson, we'll dive into more text pre-processing tricks. See you there. The next cleanup step we'll look at is removing stop words. Stop words are those little glue words like and, of, a, and to. They help sentences flow in everyday language, but in natural language processing and machine learning, they don't usually add much meaning. By removing them, we simplify the text and end up with a smaller, cleaner data set that's easier to process and often more useful for analysis. To handle stop words, we'll use a popular Python library for working with language data, NLTK, short for Natural Language Toolkit. It comes with a lot of helpful resources, like predefined lists of stop words in different languages, tools for tokenizing text, and even pre-built data sets for experiments. In our case, we'll use its built-in English stop words list to filter out the common words from our text. So let's import the package and download the list of predefined stop words using the nltk.download_stopwords command. If you haven't done this before, it may take a moment, but once it's on your system, you won't need to download it again. After downloading the list, we also need to import it so we can start using it in our code. Great. Now that we've got the stop words ready, we can load them into a variable and see exactly which words NLTK considers stop words in English. I'll create a variable called nStopWords and assign it the English stop words list from NLTK using the words method. Let's print these stop words out to see which words we are going to be removing from our text. As you can see, it's mostly short common words in English that don't add much meaning on their own. Now let's take a sentence and try removing the stop words from it. For this example, we'll use the sentence, "It was too far to go to the shop and he did not want her to walk." First, I'll create a new variable called sentence no stop words. After the equal sign, I'll write a space in quotes, then a dot, followed by the join function. The join function will glue words back together with a single space between them once we've filtered them. Inside the parentheses, we need a list of the words we want to keep. We'll build that list using a list comprehension once again. I'll open a square bracket and type word for word in sentence, meaning go through each word in the sentence variable and call it word. I'll use the split method, which will break the sentence into a list of words and put an if condition, so we only keep words that aren't stop words. So for each word in our sentence, if the word is not in the stop words list, it gets added to the new sentence. If the word is in the stop words list, Python will skip over it. Let's print out the sentence with no stop words. Yes, we see we're left with far, go, shop, want, walk. It might sound a little strange to us as humans, but to a computer, these remaining words actually carry the most meaning. Okay, but sometimes you might not agree with all the words in the default stop words list. In that case, you can customize it by removing certain words you want to keep or by adding new words you want to filter out. Removing words from the list can be performed with the remove method applied directly to the stop words list like this. For example, I'll remove the words did and not because I think they are rather important. Additionally, I'll use the append method to add another word to the list, which in this case is go. Okay, let's now use the same list comprehension from before and see what words will be left after our little modification of the list. Yes, the results have changed according to what we've done. The word go is now missing and the words did and not appear in the text. Regular expressions, or regex in short, are a special way of writing patterns to search through text. Instead of looking for just one exact word, regex lets you describe a rule, like any 3 numbers in a row or any word that starts with a capital letter. With regex, you can find, filter, and check text based on the pattern you define. In Python, there are many ways you can write regex patterns, so let's just jump in and get started with some examples. The first thing we will want to do is import the RE package, Python's built-in library for working with regular expressions. But before we get started with the regex code, let's first cover the concept of raw strings. Python recognizes certain characters to have a special meaning. For example, \n in Python is used to indicate a new line. However, sometimes these codes that Python recognizes to have certain meanings appear in our strings, and we want to tell Python that a \n in our text is a literal \n rather than meaning a new line. This is known as a raw string. To indicate that our text is just a raw string and not a special character, we can use the R character before strings. R means raw and tells Python to treat backslashes and special characters exactly as they are, instead of giving them a special meaning. Let's see this in action by printing some text without using the raw string indicator. Suppose we want to specify a file path. We create a variable called myfolder and set it to c/desktop/notes. Notice that inside this text we have a \n. When we print it, Python interprets that \n as a new line character. So instead of showing the file path as we wrote it, the notes part is moved onto a new line. Now, if we add a lowercase r in front of our string and print it again, Python treats the \/ literally. This time, the file path is displayed correctly just as we typed it. That's why raw strings are important in regular expressions. They make sure special characters like backslashes are read exactly as they are. Now that we've covered raw strings, let's look at the first regex function, the re.search function. The search function checks whether a specified pattern appears within a string. It takes two arguments. First, the pattern to search for. Second, the string to search in. If the pattern is found, search returns a match object. If not, it returns none. When we print the result, we see a match object. Now let's try a case where the pattern isn't there. When we print it, the result is none, because the pattern doesn't exist in that string. Next, let's look at the re.sub function. The sub function lets you search for specific text within a string and replace it with new content. It requires three arguments. First, the text or expression you want to find. Second, the text that will take its place. Third, the string in which the search is performed. Let's try an example. Our string is, Sarah was able to help me find the items I needed quickly. But here the name is misspelled. It should be Sarah with an H in the end. So we can use re.sub to replace it with the correct version. In a new variable called newString, I type re.sub. The first argument is the incorrect version of Sarah, the text we want to find. The second argument is Sarah with an H at the end, the correct replacement. And the third argument is our original string. When we print a new string, the output shows the name written correctly, using our replacement. Now let's explore a bit more of the power of regex syntax. Suppose we have 6 different customer reviews about our staff. We want to pull out only the reviews that mention Sarah, but remember, sometimes her name is misspelled as Sarah without an H. To handle both cases, we can write a pattern with a question mark after the R. The question mark means the letter H is optional. So this single pattern will match both Sarah with and without and H at the end. Next, we create an empty list called Sarah's Reviews. Then we loop through each customer review. Inside the loop, we use re.search with our pattern. If the pattern is found in a review, we append that review to the list. Finally, when we print Sarah's reviews, we see that only the reviews mentioning either Sarah without the H or Sarah with the H are collected into one list. Now, let's try something different and look for reviews that start with the letter A. We again create a list for these new reviews. We use a raw string to define our pattern. The carré symbol tells us to look at the start of the string. So the pattern carré A matches any string that begins with the letter A. Once again, we create our for loop to go through the customer reviews. For each string in our customer reviews, if the re search matches the pattern to find in the string, we take this string and append it to our A reviews list. Once we print this out, we can see that amazing work from Sardine has been correctly pulled for us. We can also search for reviews that end with certain letters. For example, let's find reviews that end with the letter Y. To do this, we use the $, which means end of the string. So our pattern is Y$, and it matches any string that finishes with the letter Y. Let's look at another useful regex operator, the pipe symbol. The pipe works like an OR. It lets us search for more than one word. First, let's create our empty list. The pattern to find here is open parenthesis, need, pipe, want, close parenthesis, ed. The parentheses are necessary here because they group the words need and want together. Without them, the OR would only apply to part of the pattern, and the result wouldn't work as we expect. So with this grouped pattern, we're telling Python, match either needed or wanted. Next, we loop through each customer review and add any matches to the list. Finally, when we print need-want reviews, we see only the reviews that contain either needed or wanted. Let's explore one of the most practical uses of regex, removing punctuation from text. This step is crucial in natural language processing because punctuation often gets in the way when we want to analyze words. Here's how we do it. We create a new empty list called no punctuation reviews. Then we define a pattern, raw string, open square bracket, caret symbol, \w, \s, close square bracket. Let's break that down. The square brackets define a set of characters we want to match. The caret at the beginning means not. /w stands for word characters like letters, numbers, and underscores. /s stands for whitespace characters like spaces. So together, the pattern means find anything that is not a word character and not a space. In other words, the punctuation. Now, let's use our pattern inside a loop. For each string in customer reviews, we create a new version of the review called no punctuation string. We do this with the re.sub function. The first argument is our pattern, anything that's not a word character or a space. The second argument is an empty string, which means we replace any punctuation we find with nothing, effectively removing it from the text. And the third argument is the text we want to clean, in this case, the current review from the loop. Each cleaned up review is then added to our no punctuation reviews list. When we print the no punctuation reviews list, we can see that all the punctuation has been removed. Regex offers many options, and it can take some practice to become comfortable with all its capabilities. But it's a handy tool for working with text, especially when you need to filter data or find pieces of text that match specific patterns. One of the most critical steps in natural language processing is breaking text into smaller units. This process is called tokenization, and the smaller units are known as tokens. The most common type of tokenization is word tokenization, where each word in a sentence becomes a token. But tokens don't have to be words. Depending on your use case, they could also be sentences, subwords, or even single characters. We use tokenization because breaking text into smaller parts makes it easier to analyze and understand. For example, looking at individual words can reveal patterns, like which words are most common or how often specific terms appear together. Now let's look at some examples of sentence and word tokenization using the NLTK package. First, we import the package and download punct tab. This is the punctuation table used to figure out where sentences begin and end. Then, from NLTK's tokenize module, we import two functions: word tokenize for splitting text into words and sent tokenize for splitting text into sentences. Okay, now let's create a string that contains two sentences. Her cat's name is Luna, and her dog's name is Max. We then use the sentTokenize function and place the sentences variable inside the parentheses to split this string into individual sentences. Let's execute. The output shows the text broken into two parts. The first sentence is, her cat's name is Luna, and the second is, her dog's name is Max. Next, let's try word tokenization. Take the sentence, her cat's name is Luna, and store it in a new variable. Then run the word tokenize function on it. Yes, the sentence is split into individual tokens, where each word becomes its own token. Now let's try this on a slightly longer text. We join the two sentences together. When we run the word tokenize function on this combined text, it breaks everything into tokens again. This time, we see all the individual words from both sentences listed out as separate tokens. Notice the difference in casing in the tokenized output. The first token is her with a capital H, while later tokens include her with a lowercase h. If we had converted all tokens to lowercase before processing, these would have matched. In frequency analysis or other text operations, capitalized and lowercase versions of the same word might be treated as separate entries. That's why, by converting everything to lowercase first, we can ensure consistency and get a much more accurate picture of our data. The next step in pre-processing is to standardize the text. This means making the text more uniform so that different forms of the same word don't confuse the analysis. One common way to do this is through stemming, where words are reduced to their base form. For example, words like connecting or connected will be reduced to the base form connect. Stemming works by chopping off endings or suffixes from words. The downside is that sometimes the result isn't a proper word or doesn't look meaningful. For instance, studies might be stemmed to something like stud. We standardize the text this way because it reduces the number of unique words in our dataset. Using fewer unique words reduces complexity and keeps the dataset smaller and easier to manage. By removing this extra noise, we make the data cleaner and simpler to process, which is an essential step in preparing it properly for machine learning. Okay, let's see how that works in practice. First, we'll import the porter stemmer from the NLTK package by typing from nltk.stem import porter stemmer. The porter stemmer is a classic rule-based algorithm that reduces English words to a simpler base. Next, we need a tool to handle stemming. We can achieve this by creating a porter stemmer object. Here's how we do it. We make a variable called PS and set it equal to a new porter stemmer object by writing open parenthesis, close parenthesis. This line creates a stemmer object and stores it inside the variable PS. From now on, whenever we want to stem a word, we'll use PS. Let's try it out with some example words. We'll start with a list of tokens based on the word connect, connecting, connected, connectivity, connect, and connects. Next, we loop through each token and run the stemmer on it. To do that, we use our PS variable. That's the stemmer object we created earlier. So for each token T in connect tokens, we print the token, followed by a colon, and then the stemmed version of that token using ps.stem. In other words, the code takes each word, stems it, and prints both the original word and its stem side by side. See? Let's try again with some different tokens. This time, we'll use words around the word learn. So our tokens will be learned, learning, learn, learns, learner, and learners. We can reuse the same code from above and replace our connect tokens with our learn tokens. We see here that the first few tokens, learned, learning, learn, and learns, have been stemmed to the word learn, whereas learner and learners have been stemmed to their base word of learner. Now, let's try one more example, but this time with the tokens likes, better, and worse. As you see, these words are very different from one another. When we print out the results, you'll notice that some words are reduced to stems that are not real words. For instance, worse is stemmed to wers, without an E on the end. This highlights one of the limitations of stemming. While it's fast and helpful for grouping related words, it has its drawbacks. The output isn't always meaningful. While stemming just chops off the end of a word, lemmatization reduces a word to a meaningful base form while preserving its intended meaning. Lemmatization is more sophisticated as it references a predefined dictionary to find the correct base form of a word. This way, it knows the context of the word and uses that information to reduce it to its proper base form. We usually end up with real, meaningful words. The trade-off, however, is that we may still have more unique words in our dataset compared to stemming. Now, let's apply lemmatization to our connect tokens, learn tokens, and likes tokens. To get started with lemmatization, we'll use the NLTK package once again. First, we need to download a resource called WordNet. WordNet is an extensive lexical database of English, basically a built-in dictionary that the lemmatizer uses to make sure the base forms it produces are real words. Then we import the WordNet lemmatizer from NLTK. Next, we create a lemmatizer by typing WordNet lemmatizer with empty parentheses. Let's now run our for loops again, this time taking our connect tokens, printing each one out, then lemmatizing them and displaying the results. Here, lemmatizer.lemmatize takes the token T and looks it up in the WordNet dictionary to return its proper base form. You can see that earlier, when we had completed our stemming, all these connect tokens were stemmed down to the word connect. In contrast, during lemmatization, all words remain unchanged. They have not been reduced to one single word. This is helpful because it preserves more of the word's meaning. But, as mentioned, it also means our dataset will be larger, since we're not shrinking multiple words into a single token. Let's try this again with our learn tokens. Here again, the only change is that the word learners has been reduced to learner. Everything else has been left as is. Finally, for our likes tokens, we can see a clear difference. The word worse remains unchanged, whereas during stemming, it was reduced to wers, losing the final E. This shows how lemmatization keeps the word in a proper, meaningful form, instead of cutting it down to a fragment. Another essential concept in text processing is the use of n-grams. N-grams help us analyze not just individual words, but also the relationships between neighboring words. An n-gram is simply a sequence of n tokens. The value of n tells us how many words are grouped. When n equals 1, we have single words, called unigrams. When n equals 2, we have pairs of consecutive words, called bigrams. When n equals 3, we have sequences of 3 words, called trigrams. For example, in the sentence, I love NLP, the unigrams are I, love, and NLP. The bigrams are I love and love NLP. The trigram is I love NLP. By working with n-grams, we can capture context that single words alone cannot. For instance, recognizing phrases like New York or credit card, which carry a different meaning together than the words do separately. To do this, we'll import 3 packages, NLTK, Pandas, and Matplotlib. You should already know that NLTK is the Natural Language Toolkit, which gives us functions for tokenization, stemming, lemmatization, and many other text processing tasks. Pandas is one of the most important Python libraries for data analysis. It's designed to make working with structured data fast and intuitive. The core feature in Pandas is the data frame, which works like a spreadsheet inside Python. A data frame stores data in rows and columns and makes it easy to filter, sort, group, or transform the data. This makes Pandas perfect for preparing text data for analysis, keeping it organized, and connecting it with other steps in our machine learning workflow. Finally, we'll use Matplotlib, which is the most common Python library for creating charts and visualizations. With Matplotlib, we can take the results of our text analysis and turn them into graphs, making it much easier to spot patterns and trends in the data. Okay, let's create some tokens for this example. These tokens have not yet been fully pre-processed. We'll cover that later in our next practical lesson. I'll copy our tokens over and then print them out to have a look at what we have. Now, we want to take our tokens and look at the unigrams that are present in this data. Remember, unigrams are single-word tokens. Examining them helps us understand the basic building blocks of our text, like which words appear and how often. This is often the first step in exploring text data because it provides a simple frequency count of individual words before we move on to bigger structures like bigrams or trigrams. To find the unigrams, we'll use both pandas and NLTK together. We start with the nltk.ngrams function. This function takes two arguments, our list of tokens and the value of n. Since we want unigrams, we set n to 1. This gives us a list of all the one-word sequences in our text. Next, we wrap that result inside pandas.series. A pandas series is like a single column of data in a spreadsheet. It lets us organize our unigrams into a structured format that pandas can work with. Finally, we call value counts on the series. This goes through all the unigrams and counts how many times each one appears. When we print this out, we can see the most common unigrams. In this case, these are our most common tokens or words. For instance, the word to appeared 7 times, of 6 times, the 4 times, and so on. You can imagine how much cleaner this output would look once we finish pre-processing and remove the stop words. Looking at raw counts is useful, but visualizing the data makes it much easier to spot patterns, and it's also great for presentations. Let's take our top 10 unigrams and turn them into a chart. First, we sort the values using .sort_values, so the bars will be in order. Then we call .plot.bar with an H in the end, which creates a horizontal bar chart. Next, we can customize the chart to make it more straightforward. For example, we set the color to light salmon, adjust the bar width, and define the figure size so the chart is easy to read. Finally, we add labels and a title, the 10 most frequently occurring unigrams. When we run the code, the result is a clean horizontal bar chart showing our 10 most common unigrams. This is a powerful way to summarize text data and present it to others in a clear visual format. Okay, now let's move on to bigrams. A bigram refers to the case where n equals 2. That is, we focus on the common occurrences of neighbouring word pairs that appear next to each other. It's the same piece of code. We just change n to 2 and rename the variable as bigrams. Here, we can see the bigrams that appear twice in our data. The rest appear only once, so we don't really need to plot this out, but of course we could also do that if we'd like. Finally, we can compute our trigrams. As you might expect, this refers to the case where n equals 3. In other words, we're examining sequences of 3 tokens that occur together. Here we see that these different trigrams only appear once. So again, we don't really need to plot this out. But when working with significantly larger datasets or data that has undergone more thorough pre-processing, this bigram and trigram analysis can give some exciting results. A quick note on terminology. We use the terms unigrams, bigrams, and trigrams for n equal to 1, 2, and 3. When n is any number greater than 3, we use the term n-grams to describe them. Now that we've covered this, let's jump into a practical example and put everything we've learned in this section together. So now that we've covered each of the steps of text pre-processing, let's put this all together in a practical lesson where we'll be running through each of the steps using a more realistic dataset. We'll start by importing the packages we need. So we want the NLTK package, and from NLTK tokenize, import word tokenize. From nltk.stem, we want to import the porter stemmer and the word net lemmatizer. Next, we import the stop words from the NLTK corpus. Finally, we also import the RE package and pandas as PD. We're now ready to load in our dataset. Let's create our data frame and read the TripAdvisor Hotel Reviews CSV file. So we type pd.readcsv and place the name of the file inside the parentheses. As you might have guessed, this dataset we are going to be working with is a set of hotel reviews. We can use data.info to see what we have. 109 rows and no null values. Perfect. Now let us use data.head to take a look at our data. We can see we have two columns, one for the text review and one for the rating associated with that review. Let us also take a look at the first review in more detail. To do this, I'll specify that I'm interested in row 0, like this. We can see it is talking about a nice hotel, expensive parking, got a good deal, just a typical hotel review. It looks like most of this data is already in lowercase, but let us run our lowercase function just to be sure. We will create a review lowercase column by taking the review column and applying the lower method on it. Let's run data.head to check. Yes, it worked. The next thing we are going to do is remove the stop words from this dataset. We will create our n stop words set from the English stop words using stopwords.words. I've also decided I want to make sure the word not is not within the stop words, so we can use the remove method to remove it from our list. Okay, let's create a new column called Review No Stop Words. This is where we'll store the version of each review after removing the stop words. Next, we use the apply function on the review lowercase column. The apply function is very useful because it lets us take one column and perform a custom operation on every value in it, in our case, on every individual review. You can think of it as telling Python, go through each review in this column and run the following set of instructions on it. Inside the apply function, we include what's called a lambda function. A lambda function is just a quick way to write a small function without having to define it separately with the def keyword. Here, it defines exactly what should happen to each review, step by step. The code inside the lambda function says, take each review, which we're calling x, and split it into individual words using the split method. This turns the review from one long string of text into a list of separate words. Then, for every word in that list, Python checks whether the word appears in our list of stop words, n stop words. If the word is not a stop word, it's kept. If it is a stop word, it's left out. The part for word in x.split, if word not in n stop words, is a simple list comprehension. It's a compact way of writing a loop that goes through each word, applies a condition, and builds a new list containing only the words that pass that condition. Once that filtered list is ready, the join function combines the words back into a single string with spaces between them, so the text looks like a normal sentence again. When you're pre-processing text, it is always worth making a new column for each of the steps in your pre-processing, so you can check it along the way. And if something messes up, you can just go back to the previous step in that relevant column. Let's check our working by looking at the first review we pulled earlier and seeing how it's changed. So this review is pretty clean to start with, but we can see that it has had a few words removed from it and everything's in lowercase. So we're perfect to move forward to the next step. Let's now tackle the punctuation in our text. We want to remove the punctuation, but we notice we've got a few reviews with the star symbol instead of the word star. We want to keep this as it might add meaning to the review. We can do this using regular expressions. Let's first create a new column, Review No Stop Words, No Punct. After the equal sign, we type data.apply, which, just like before, allows us to perform a custom operation on every row of our dataset. However, this time, instead of applying a function to a single column, we're applying it to the entire dataset. That's why the argument axis equals 1 is used. It tells Python to go through the data row by row rather than column by column. Inside the apply function, we use another lambda function to describe exactly what should happen for each row. The operation we're performing is handled by the re.sub function, which is used to search for specific text patterns and replace them with something else. In this case, the pattern we're looking for is the asterisk symbol inside the function. As you already know, the R before the quotation marks tells Python that this is a raw string, meaning the text should be treated exactly as it's written, without trying to interpret any special characters. The re.sub function then replaces every asterisk it finds in the text with the word star. Finally, xReviewNoStopWords tells Python that this operation should be applied specifically to the text from our ReviewNoStopWords column, the one we cleaned in the previous step. The resulting text, with punctuation handled, is then stored in the new column, ReviewNoStopWordsNoPunct. This should find all the occurrences of the star symbol and replace it with the word. So if you look at line 2 here, you can see that the 4 star is in the original review, but in the column ReviewNoStopWordsNoPunct, it's been replaced with the word star. Now that this has been taken care of, we can remove the rest of the punctuation by updating the same column. If you remember from the lesson on regular expressions, the regex syntax we want to use to remove punctuation is square brackets, caret, \w\s. So Python is going to be looking for anything that isn't a word or isn't a white space and replace it with nothing. Amazing! We can see that all the punctuation has been removed from our text. The next step is tokenizing this text. First, we will create a new column called tokenized. Then we'll take lambda x and word tokenize x followed by the column name ReviewNoStopWordsNoPoint. This way, we're tokenizing our cleaned data. Let's take a look at that first review again. We can see the text has been tokenized, the punctuation has been removed, and it is a nice clean data set. So the next step we're going to look at is stemming. Let's initialize our stemmer and name it PS. Then I'll reference the porterStemmer function. Next, we'll create our stemmed column. We'll then take our tokenized text from the tokenized column and apply a lambda function on the tokens. This way, we're going to run stem on each token in our tokens list. So if we now look at the data using data.head, we can see that the words have been stemmed. Let us compare this against lemmatization. We'll first create our lemmatizer using the WordNet lemmatizer function. We'll then create our lemmatized column, and similar to the code above, we'll be applying a lambda function over the tokens using the lemmatizer.lemmatized function. Let us take a look at that first review one last time to see how it has been lemmatized. We can see a lot of the words have retained their original form and have not been reduced as aggressively as with stemming. We now have a nice clean dataset that is in lowercase, has no punctuation, has been tokenized, and contains both stemmed and lemmatized versions. Let us see what this looks like now and get an idea of what is in our data by looking at the n-grams. But before we can do that, we need to prepare our text in the right format. Right now, each row in the lemmatized column contains a separate list of tokens. In other words, each review is stored as its own list of lemmatized words. To analyze all the words in the dataset together, we need to combine these smaller lists into one long list that contains every token from all reviews. We can do that using the sum function. At first glance, this might look a little strange because we usually think of the sum function as something that adds numbers together, like 2 plus 3 plus 5. But in Python, when we use sum with lists instead of numbers, it doesn't add them in a mathematical sense. Instead, it joins them together, one after another. Here's what's happening step by step. The code starts with the empty list, which acts as a starting point. Then it goes through the lemmatized column and keeps adding or concatenating each review's list of tokens to that empty list. After it's done, we end up with one big list that contains all the lemmatized words from all reviews combined. We store this result in a new variable called tokensClean. This single, flattened list makes it much easier to explore the words in our dataset. Let us now look at the most frequently occurring unigrams, the most common tokens in our dataset. To visualize them in a column, we'll create a pandas series. So we use pd.series and then use the nltk n-grams function. The first argument is our token, so we specify tokensClean. The next argument is the value of n. Here, because we're interested in unigrams, n is 1. Finally, we do the value counts of these different tokens to find out which are the most common ones. If we print this out, we can see that the most common words in our data were things like hotel, room, followed by great, not, and stay. Let's swap this out for bigrams now. So we change the name from unigrams to bigrams. Then we set the value of n to be 2 and print out our results. Here again, you can see there are quite a few occasions where phrases like great location appeared together, as well as names or terms like Space Needle and Hotel Monaco. This gives a nice idea of topics and themes that are coming up in the data without requiring difficult or time-consuming analysis. This is really useful to get a feel for what is in your data, to check your pre-processing, and to gain a good understanding of the dataset before moving on to any kind of advanced analysis. So, we've done some simple exploration of our data after pre-processing using n-grams. We can now extend this even further by adding tags to our text. There's two types of tagging that we're going to cover today: parts of speech tagging and named entity recognition. The first method we're going to try is parts of speech tagging. This is where we take each of our tokens and tag them with the associated parts of speech. And by parts of speech, I just mean whether that token is a verb, a noun, an adjective, etc. The second method is named entity recognition. So instead of going through each of the tokens and tagging them, this method searches through our text and pulls out named entities. And by this, I mean things like people, places, organizations, works of art, any kind of named entity that's easily recognizable by most people. These methods of tagging our text can be really useful for exploring our text and understanding what's in there. They can also be used to create additional features for machine learning algorithms, or they can be a really interesting standalone analysis in themselves. Our next 2 lessons will be taking each of these methods and see how we implement them in Python. Part of speech tagging is the process of labeling each word in a sentence with its grammatical role. For example, whether it's a noun, a verb, or an adjective. This helps us understand not only the meaning of the separate words, but how they function in a sentence. To perform part of speech tagging in Python, we'll use the Spacey package. Spacey is one of the most popular NLP libraries. It comes with pre-trained models that can recognize parts of speech, named entities, and other linguistic features right out of the box. We'll also use pandas, which you already know is great for storing and working with structured data. In this lesson, pandas will help us organize the tagged text into a clean format so we can analyze it more easily. Okay, the first step is to load a Spacey model. We start by creating a variable called NLP. Then, we use the function spacey.load. Inside the parentheses, we specify the model we want to use, ncore WebSM. This English core model is lightweight and fast, which makes it perfect for learning and for smaller projects where speed matters more than perfect accuracy. By loading it into the NLP variable, we now have a ready-to-use tool for processing English text. Next, we need some text to practice part of speech tagging. For this example, we'll use a passage from Emma by Jane Austen. Emma is a classic English novel from the early 1800s. It's often used in natural language processing because it's freely available as public domain text. For simplicity, the text has already been pre-processed a bit, punctuation has been removed, and all words have been converted to lowercase. However, we've kept the stop words, since part of speech tagging also applies to those common words like the and is. Now we'll create a Spacey document from our text. A Spacey document is an object that stores the text along with all the linguistic information Spacey generates, such as tokens and their part of speech tags. This single line of code takes the text from Emma and turns it into a structured document where each word is already tokenized and tagged. Okay, let's now create an empty data frame called posdf. We tell pandas that this table should have 2 columns, one named token and one named pos tag. Then we use a for loop to go through every token in our Spacey document. For each token, we grab 2 pieces of information, the word itself and its part of speech tag stored in a dictionary. We then turn that dictionary into a 1-row table using dataframe from records. Next, we join this 1-row table to our larger table, posdf, using pandas concat method. This process happens over and over, once for each token in the text. By the time the loop finishes, posdf has grown into a full data frame, with 1 row for each token and its part of speech tag. Once our table is ready, we can take a quick look at it. By running posdf.head, open parenthesis, 15, close parenthesis, we display the first 15 words of the text along with their part of speech tags. Nice! Let's dive a bit deeper. Say we want to find the most common tokens and their associated POS tag. To do this, we create a new data frame from the previous one and call it posdf counts. Inside this table, each unique token and its tag will be grouped, and we'll also count how many times they appear. Here's how it works step by step. First, we use the group by function on posdf, grouping by both the token and the part of speech tag. Then we use .size to count how many rows belong to each group. Next, we use reset index. This is important because after grouping, pandas uses the grouped columns as the index of the table. Resetting the index turns them back into regular columns, so our table looks clean and easy to read. We also give the new column the name counts. Finally, we use sort values with ascending set to false, which makes sure the most significant counts appear first. When we run pos.dfcounts.head, we see the 10 most common tokens, along with their pos tags and how many times they appear. For example, in our text, some of the most frequent tokens are of and her, together with their tags and occurrence counts. Okay, let's find out how many different words fall under each POS tag. We create a new data frame called pos.df_pos_counts. Here, each row will represent one part of speech tag, such as noun, verb, or adjective, along with the number of unique tokens that belong to it. Here's how it works. We use the group by function on pos.dfcounts, this time grouping only by the pos tag column. Then, for each group, we count the number of tokens using .count. This gives us the number of different words for each part of speech. Next, we use sort values with ascending set to false. This puts the largest groups first, so we can immediately see which part of speech tags are most common in the text. Finally, we obtain a list of the most common part of speech tags and their counts. Nice. Okay, let's get more specific. To look particularly at the most common nouns in our data, we can filter the pos.dfcounts data frame to include only pos tags that equal noun. From there, we select the top 10 nouns by their counts. When we print this out, we see that the top nouns are governess and friend, both appearing 3 times, followed by mother, daughters, sisters, and others. In this lesson, we'll learn about named entity recognition, or NER. Named entity recognition is the process of finding and labeling essential pieces of information in text, such as names of people, places, organizations, dates, or quantities. For example, in the sentence Emma lives in London, NER would tag Emma as a person and London as a location. But this goes beyond simply finding capitalized words to capture the names. NER uses a combination of rules and machine learning to discover the entities. While capital letters are one clue, the model also looks at the surrounding context, word patterns, and statistical probabilities. This way, Apple might be tagged as a fruit in one sentence, but as a company in another. This makes NER a powerful tool for turning unstructured text into structured information that can be searched, analyzed, or used in applications like chatbots, question answering, and recommendation systems. To perform named entity recognition in Python, we'll continue using the spaCy package, which comes with powerful pre-trained models for this task. We also import displacy from spaCy, which is its built-in visualization tool that lets us see entities highlighted directly in the text. Next, we import the tokenizer from spaCy, which breaks text into tokens so that spaCy can process it correctly. Finally, we bring in HTML and display from IPython, which will let us render visualizations inside our notebook. Okay, we start by loading our spaCy model, the engine that will process the text for named entity recognition. We create a variable called NLP and set it equal to spaCy.load, with the model name inside the parentheses. In this case, we're using the small English model ENCore Web SM. Now, the NLP variable holds our spaCy model, ready to process text and identify entities. The example text we will use is taken from the Google Wikipedia page. We assign it to the variable Google text and print it to have a look. Next, we create a spaCy document by passing our text into the NLP model. When we do this, spaCy breaks the text into tokens, analyzes the grammar, and looks for named entities. But creating the document alone doesn't show us the entities yet. To see what spaCy has found, we need to loop through them. spaCy stores all the entities it detects in an attribute called spaCydoc.ents. So we write a for loop that goes through each entity in spaCydoc.ents. Inside the loop, we print the text of the entity with word.text and its label with word.label. You might notice that this attribute has an underscore at the end. In Spacie, label, without the underscore, gives a numeric ID of the entity, while label, with underscore, gives the human-readable label, such as person or organization. Okay, let's run the cell. Yes, we can now see which parts of the text are detected as dates, which are identified as people, which are classified as organizations, and which belong to other categories. Let's go a step further and visualize the different entities directly within our text. To achieve this, we use the displacy.render function, which highlights entities and assigns each category a distinct color, making people, organizations, and locations easy to distinguish. Displacy.render takes our Spacie document and creates an HTML version of it with the entities highlighted. We save that into a variable called HTML. Inside the parentheses, we pass in 3 arguments. The first one is the document with the text that Spacie has already analyzed for entities. The second argument is style equals entities. This tells Spacie that we want to visualize entities specifically, since Displacy can also visualize other elements. The third argument is Jupyter equals false. This means instead of trying to display the visualization automatically in a Jupyter notebook, return it as HTML code. That way we can decide how and where to display it. All that output is stored in the variable HTML. So we wrap it with the HTML class to tell Python, treat this string as HTML content, not plain text. Finally, we pass it into display to see our text with the entities highlighted in different colors. Beautiful. We see the different entities grouped in separate colors. For example, all persons are in purple and all dates in green. Let's observe what happens to named entity recognition once we clean the text by removing punctuation and converting it to lowercase. We create a cleaned version of the Google text using the re.sub function to remove punctuation and then apply the lower method. Once we print this out, it looks a bit different. The punctuation is gone and it's all in lowercase. So we create a new Spacie document with our clean text and we name it spacie.clean. Again, we iterate through each word in our new Spacie document and print out each word and its associated entity tags. You can see that fewer entities are detected because of the lack of punctuation and capitalization. We can again use the displacy.render function to visualize the entities in the clean text. Yes, we see that there are fewer compared to our previous visualization. When we removed capitalization, the model lost a vital clue that helps it recognize names of people, places, or organizations. By removing punctuation, we also disrupted the sentence boundaries that depend on it to be recognized correctly. That's why it's essential to think carefully about when you perform named entity recognition in your data cleaning pipeline. As you see, if you clean the text too aggressively before running NER, for example, by removing punctuation or converting everything to lowercase, the model may struggle to recognize certain entities. One option is to run NER on the raw text first. Another one is to try some light pre-processing, then test NER again. In some cases, pre-processing can help the model pick up additional entities. The key takeaway is to familiarize yourself with your data, understand its content, and experiment with where NER fits best in your pipeline. That way, you avoid losing important information during cleaning. So let's take what we've learned about parts of speech tagging and named entity recognition and try it out through a practical lesson. We'll start by importing the packages we need. These are the same ones we've been using throughout the previous lessons, so nothing new here. Once that's done, we can move on to loading our dataset. In this lesson, we'll be working with a dataset of BBC News articles. We'll load it into Python as BBC data using the pandas read CSV method to import the data from a CSV file. Let's take a look at what the data looks like using bbc_data.head. As you can see, we have a column for the index, followed by the title of the article, the publication it comes from, some links, and a short description of the article. We can also run bbcdata.info to get more details about our dataset. This tells us that we have 1,000 entries, in other words, 1,000 rows of data. It also shows that there are no missing values, which means every column is completely filled in. It'll be interesting to see which parts of speech appear in these articles and what kinds of named entities we can identify, things like people, places, or organizations. For now, though, we'll focus only on the titles of the news articles. So let's extract those titles and store them separately. We'll start by creating a new variable called titles and use it to store only the title column from our BBC data frame. Then we'll turn this into another pandas data frame, so it has the same table-like structure we've been working with. To make sure everything worked correctly, we can run titles.head to look at the first few rows. Perfect! We can now see that we have a data frame with just one column containing the titles of the news articles. The next step is to clean up these titles. Since we already covered the text cleaning process in the previous lesson, we'll go through it fairly quickly here. First, we convert the text to lowercase using the .lower function. Next, we remove stop words, the common words like and, the, or is that don't add much meaning to the text. We use a predefined list of English stop words and remove them with a short lambda function that loops through every word and keeps only the ones that aren't in the stop word list. Then we clean up the punctuation. We use the re.sub function from Python's regular expression library to remove symbols such as commas, periods, or question marks. Next, we tokenize the text. In the first line, we take the original title column and apply the word tokenize function to each row. The lambda x part means for every row in our data frame, call it x and then tokenize the title inside it. This creates a new column called tokens raw, which contains lists of all the words in each original title, punctuation and all. In the second line, we tokenize the cleaned version of each title, the one without stop words or punctuation, and store that in a new column called tokens clean. Now, instead of long strings of text, we have lists of individual words that Python can easily analyze. Next comes the lemmatization step. Here we first create a lemmatizer object using WordNet Lemmatizer. Then we apply it to every list of cleaned tokens. The expression inside the square brackets loops through each token, or each word, in the list and replaces it with its base form. The result is a new column called tokens cleaned lemmatized, which stores the final, fully processed versions of our titles, lowercase, cleaned, tokenized, and lemmatized. Let's take a look at it using the head method. Perfect! Now that we've tokenized and lemmatized the titles, we'll combine all those tokens into a single list. Remember, each row in our data frame currently holds a list of words for that specific article title. To analyze all the words together, we need to merge these smaller lists into one. We'll repeat this process for both versions of our text, the raw and the cleaned one. Remember, when we did the tokenization earlier, we created two sets of tokens, one from the original titles before any cleaning, and another from the cleaned and lemmatized titles. So now we'll create two new lists, tokens raw list, which will come from the tokens raw column, and tokens clean list, which will come from the tokens clean lemmatized column. This will give us both the unprocessed and the fully cleaned versions of all the words in our dataset ready for comparison and analysis. Now we're ready to begin with part-of-speech tagging, or POS tagging for short. The first step is to initialize the spaCy model we'll be using. To do that, we create a variable called NLP and assign it the English language model from spaCy using the spaCy.load function. Let's now create a spaCy document to store the text in the right format. We'll need the join function and indicate empty spaces between the words like this. Once the text is in the right format, as a single string with spaces between words, we process it using our spaCy language model stored in the variable NLP. This step runs the model over the text and analyzes it linguistically. The result stored in spaCy doc is a spaCy document object that contains the text along with detailed annotations, such as each word's part of speech tag. Next, we'll create a new data frame to store the results of our part of speech tagging. We'll call it POSDF and set it up as a pandas data frame with two columns, one for the token, that is, each individual word, and one for its pos tag, which shows the grammatical category assigned by spaCy. In other words, this data frame will let us easily see which word belongs to which part of speech, all organized in a simple table format. To achieve this, we'll create a for loop to go through each token in our spaCy document and extract its corresponding part of speech tag. For every token in the spaCy document, we take the actual word stored as token.text and its part of speech tag stored as token.pos_. The FromRecords function creates a one-row data frame from these two pieces of information, and pd.concat then adds that new row to our existing table. By the end of the loop, the table contains two columns, one with each word from the document and one with its corresponding part of speech. The next step is to create a token frequency count. In other words, we want to count how many times each word appears in our document and which part of speech it belongs to. To do this, we create a new data frame called POSDF counts. We start by using the group by method. We group the data by two columns, the token column, which contains the word itself, and the pos tag column, which contains its part of speech. Next, we use the size method, which counts how many rows fall into each of those groups. In other words, how often each token tag pair occurs. Then we use resetIndex, because when we grouped the data, pandas automatically placed the grouped columns into the index, and the output is no longer displayed like a regular data frame with normal columns. To fix this, we call resetIndex, which removes those group labels from the index and turns them back into regular columns. This gives us a clean table again, where token, POS tag, and counts each have their own column. In the parentheses, name equals counts gives a clear name to the new column that holds the counts. Instead of just seeing unlabeled numbers, we now have a proper counts column. Finally, We sort the values so that the most frequent tokens appear at the top. And as you can probably tell, since we ran this on the raw data, the results aren't very clean. The output includes a lot of punctuation marks and stop words. But even though this dataset looks a bit messy, we can still find some useful insights by focusing on specific parts of speech. Let's start by looking at the most common nouns in our dataset. To do this, we'll take our POS-DF counts data frame and filter it so that we only keep the rows where the POS tag equals noun. Then we'll take just the first 10 rows to look at the top results. This gives us a quick view of the most common nouns in our dataset. For example, we can see that the word war appears 35 times, making it the most frequent noun. Next, let's do the same for the verbs and take a look at the most common ones in our dataset. Here we can see words like says, found, and win. And remember, this dataset comes from news articles, so it makes sense that we see action-oriented words like these. Even from this simple analysis, we can already get a quick overview of what's being talked about and the kinds of events or actions that appear most often in the news. We can also repeat this process for adjectives to see which descriptive words appear most often. In this case, we can see words like new, Russian, and final appearing frequently. These adjectives give us a sense of how the articles describe people, places, or events within the news dataset. Next, we'll move on to named entity recognition, but feel free to also pause this video and try doing some POS tagging on the cleaned up tokens and compare the difference between the two. Now let's move on to named entity recognition, or NER. The process is very similar to what we did for part of speech tagging. First, we create a new data frame called NERDF, which will hold each token and its associated named entity tag. Things like person, organization, or GPE for geopolitical entity. We initialize it with two columns, one for the token and one for the NER tag. Then we set up a for loop that goes through every entity in our Spacie document using spaciedoc.ents. Inside the loop, we use a small condition. The function pd.isNA checks if a value is missing. Here it's checking whether the token's label exists. The phrase is false simply means we only continue if the value is not missing. So together, this line says, if the token has a valid label, then process it. When that condition is true, we take the token text, which is the word itself, and the token label underscore, which gives us the human-readable version of the named entity tag. We then use from records again to create a one-row data frame from this information and concat it to our main NER data frame. By the end, NERDF contains a clear list of all the named entities that Spacie found in the text. Let's check that everything has worked correctly by using the head method to view the first few rows of our new data frame. Great, we can see that several tokens have been extracted successfully, including names and places. This confirms that our named entity recognition step is working as expected and is correctly identifying key entities in the text. Next, let's take a look at the most common named entities that appear in our dataset. We'll create a new data frame called NERDF counts. Just like we did earlier for the parts of speech, we'll use the group by function to group our data by two columns, the token and the NER tag. Then we'll take the size of each group to count how many times each entity appears. reset the index to turn it back into a regular table, and sort the values so the most frequent ones appear at the top. When we look at the results, we can see that Ukraine is the most commonly mentioned named entity in this dataset. Even with just this simple analysis, we're already gaining insight into the main topics and locations discussed in these BBC News articles. In this lesson, we explored how to use part-of-speech tagging and named entity recognition to gain deeper insight into our text data. These techniques help us understand what kinds of words appear in our dataset, what they represent, and how they relate to the topics being discussed. Now that we have a better grasp of the structure and content of our data, we're ready to move on to the next section, where we'll explore the exciting topic of sentiment analysis. Welcome back, and I hope you're enjoying the course so far. In this next section, we're going to be covering sentiment analysis. Sentiment analysis is a really popular technique in NLP for discovering the underlying emotional tone of the text, whether that be positive, negative, or neutral. This type of analysis is really useful when you're interested in getting a quick understanding of how people view certain things. So, for example, you might have seen an analysis of people looking at tweets or other social media data, and they're interested in looking at the sentiment towards different brands or products or people. Before we jump into the code, let's start with some definitions about what we mean by positive, negative, and neutral sentiment, so we're all on the same page. A sentence would be classified as positive sentiment if there's an expression of liking something, some enjoyment, or some other kind of positive emotion. So, for example, the sentence, "The music in the cafe made me feel really calm and relaxed." This would be an example of a positive sentiment sentence. Negative sentiment, on the other hand, is an expression of a negative emotion. So, for example, the sentence, "The smell was really bad and it made me feel sick," is expressing a negative emotion, so it would be classified as negative sentiment. There's also neutral sentiment. So if a sentence doesn't really appear to be positive or negative, it sits somewhere in the middle, we could say this has a neutral sentiment. For example, the phrase, "It was raining." There's no emotion expressed here about the rain, it's just a factual statement, so this would be a neutral sentiment. The lessons in this section are going to cover different methods of computing the sentiment. Let's start with our first lesson on rule-based sentiment. The first method of sentiment analysis we will look at is called rule-based or lexicon-based sentiment analysis. This isn't a machine learning method. Instead, it uses a set of predefined rules that connect words to emotions or attitudes. For instance, the word great is linked to a positive feeling, while the word sad to a negative one. Each word is assigned a polarity score, a numerical value that shows whether the word is positive, negative, or neutral. The score usually ranges from -1 to 1, where any number above 0 indicates positive sentiment. For example, the positive word great can have a score of plus 0.8, while the negative one, sad, minus 0.7. These scores are then combined across the entire sentence or text to calculate an overall sentiment score. This approach is easy to use and simple to explain, which makes it a common starting point, but it has clear limitations. It can't handle more subtle expressions such as sarcasm or irony, where the literal meaning of the words doesn't reflect the true sentiment. In this lesson, we will compare two popular Python packages that follow the rule-based approach, TextBlob and Vader. Each package uses its own lexicon, a collection of words paired with their predefined sentiment scores. Because TextBlob and Vader rely on different lexicons and slightly different scoring rules, they may produce different results when analyzing the same text. Let's try it out with these 4 sentences right there. First, we will use the text blob package. For each sentence, we will print out the sentence and then compute its sentiment score. Computing the sentiment score is straightforward. Use the text blob function and specify the text to analyze within the brackets. To see the polarity score, we use sentiment.polarity. Finally, we print the result to view the score. For example, the sentence, "I had a great time at the movie, it was really funny," receives a polarity score of 0.525, indicating a moderately positive sentiment. Sentence 2, "I had a great time at the movie, but the parking was terrible," receives a slightly negative score of negative 0.09. This score is close to neutral, reflecting the ambiguous nature of the text. Sentence 3 receives a positive score of 0.8, while sentence 4 comes with a polarity score of 0, indicating a truly neutral sentiment. This aligns with how most humans would interpret the sentence. Next, we will compare these results with the Veda package. To use it, we first import Sentiment Intensity Analyzer from Veda Sentiment module and then initialize it as Veda Sentiment. To compute a score, we call the function polarity scores and pass in the sentence as input. This function returns a dictionary with 4 values: negative, neutral, positive, and compound. The first 3 show the proportion of the text that falls into each category, while the compound score is the overall sentiment value, ranging from -1 to 1. You can see the output looks different from when we were using the text blog package. Here, we see the combination of different polarity values and the total compound score. The Veda package has given a higher positive score to sentence 1 compared to the text blog package. For sentence 2, Veda assigns an overall compound score of negative 0.4, which is more negative than TextBlob's score. Sentence 3 shows a significant difference. Veda assigns a negative compound score of negative 0.4, whereas TextBlob gave it the highest positive score of 0.8. This suggests that Veda may be more advanced at detecting nuance within the text. For sentence 4, both packages correctly identify the sentence as neutral. Neither package struggles with this neutral sentence. So, what's the key takeaway? When applying sentiment analysis, it's a good idea to test more than one package on a sample of your text. Different tools may interpret the same sentences in slightly different ways, and comparing their outputs helps you decide which one works best for your specific dataset and use case. Rule-based sentiment analysis is easy to understand and implement, but it is not always that accurate. Modern sentiment analysis often relies on transformer models, which represent a major step forward. Transformers are based on deep learning and are designed to capture how words influence and relate to each other, even when they appear far apart in a sentence. Transformers are crucial because they understand context. Instead of looking at words in isolation, they recognize how meaning changes depending on surrounding words. This allows them to handle complex sentences, subtle tones, and even sarcasm much more effectively than rule-based methods. Going into detail on how transformers work is a little out of scope for this course. For now, we will cover transformers at a high level and see how the code works. To apply transformer models for sentiment analysis, we start by importing the transformers library. From it, we bring in the pipeline function. This function provides a quick way to use powerful pre-trained models without needing to build them from scratch. We then call pipeline function with the argument sentiment analysis to return an object which will act as our sentiment analysis tool. By assigning it to a variable, for example, sentiment pipeline, we store this tool so we can reuse it to analyze any sentence we pass to it. When we run this code, you may see a message saying that no model was supplied and that a default model will be used. This is nothing to worry about. The pipeline automatically loads a reliable pre-trained model for sentiment analysis. The message is simply a reminder that in real-world applications, it's best to specify the model yourself. For our purposes, using the default works perfectly fine. You might also see the line device set to use CPU. This just means the model will run on your computer's processor instead of a GPU. It might be slower, but it will still work correctly. Okay, the next step is similar to what we've done with the rule-based sentiment analysis. We print the first sentence and call the sentiment pipeline object with the text as input to receive the score. We see that sentence 1 is identified as positive with a score very close to 1. This indicates that the model is highly confident that it's a very positive sentence. Transformer models return both a label, positive or negative, and a confidence score between 0 and 1, which shows how sure the model is about its prediction. So eventually you may see a positive score like the one here and a negative label, meaning that the transformer is very confident at that score. That's the case with sentence 2. Sentence 3 is also given a negative label with high confidence. Sentence 4, however, is labeled positive with a strong score. This is unusual because rule-based models typically see sentence 4 as neutral. In this case, the pre-trained transformer model has misclassified the sentence. Interesting, right? So, what can we do to improve the results? One option is to use a different pre-trained model. There are many models available, each trained on different datasets and with different parameters. For example, we can choose a model trained specifically on English tweets to see if it performs better on our sentences. To do this, we once again use the pipeline function, but this time we provide not only sentiment analysis as the task, but also the name of the model we want to use. Since a wide variety of models are available online, if the default model doesn't perform well, it is a good idea to try others listed on the Transformers website. When we run this code, you may see a message saying that the emoji package is not installed. This simply means the model cannot convert emojis or emoticons into text, which may slightly affect results if your data contains them. For our examples, this makes no difference, so you don't need to worry. If you ever work with text that includes emojis, you can easily fix this by installing the package as suggested. Once the specific model is created, the code to run sentiment analysis stays exactly the same. For example, printing sentence 1 and passing it through the model gives a positive score. Sentence 2 is classified as negative, but with lower confidence, showing some nuance. Sentence 3 is identified as positive, again, reflecting nuance in interpretation. Finally, sentence 4 is correctly recognized as neutral, with high confidence. So, by switching to a model that is better suited to our use case, we achieved more accurate results in sentiment analysis. Now let's see how our sentiment models perform on more realistic text. We'll use the same Python packages we worked with earlier, so let's start by importing them. For this example, we'll analyze a small dataset of book reviews. Each review expresses a different opinion, and we'll use our sentiment models to determine whether the tone is positive, negative, or neutral. Let's begin by loading our dataset into Python. we'll use readCSV from the pandas library to load the book reviews sample.csv file. As always, please make sure this file is saved in the same folder as your notebook so that pandas can find it. Okay, once the file is loaded, we'll use data.head to display the first few rows of the dataset. We can see that our dataset contains 3 columns. One is the index, one contains the review text, and the last one shows the rating score given by the reviewer. Let's take a look at one of the reviews to understand what the text looks like. We'll access the review text column from our data frame using square brackets and then indicate 0 to select the first entry in that column. Remember, Python starts counting from 0, so 0 in brackets gives us the very first review in the dataset. As usual, we'll start with a bit of text cleaning. We're not going to remove stop words or perform lemmatization or stemming here. That's because, for sentiment analysis, small words like not or very can completely change the meaning of a sentence. If we removed or altered them, our sentiment results could become inaccurate. We can usually leave punctuation in, but for our example, we'll simply remove it to keep things clean and consistent. So first, we create a new column called Review Text Clean. We take the original review text column and apply the str.lower method, which converts all the text to lowercase. Next, we remove punctuation. We use the apply method to go through each row in our dataset and apply a small lambda function. Inside it, we call the re.sub function, which will search for punctuation marks and replace them with an empty string. Finally, we run data.head to display the first few rows again, so we can make sure the text looks clean and everything ran correctly. We can now see that our new column, Review Text Clean, contains text that's all in lowercase and free of punctuation. This cleaned version will work perfectly for our sentiment analysis. Now we're ready to start applying our first model, Veda sentiment. As you already know, Veda is a rule-based method of sentiment analysis, which means it uses a predefined set of rules and a built-in dictionary of words to determine whether the text expresses a positive, negative, or neutral emotion. Let's start by initializing the sentiment analyzer. We create an object from Veda's Sentiment Intensity Analyzer class and store it in a variable called Veda Sentiment. Notice that the parentheses are empty. We don't need to pass in any arguments here because Veda already comes with a predefined sentiment lexicon, a built-in list of words and their sentiment scores. In other words, everything it needs to analyze text is already included. This object contains all the built-in rules and word scores that Veda uses to calculate sentiment. Note that if we were using TextBlob, this step would look different. TextBlob doesn't require a separate analyzer object. Instead, we create a text blob for each piece of text we want to analyze by placing the text inside text blob's parentheses. Okay, now let's use the Sentiment Intensity Analyzer instance we just created. We'll apply it to our text data to calculate the sentiment scores for each review. Next, we'll create a new column in our data frame to store the sentiment scores. We'll name it Veda_sentiment_score. To fill this column, we'll take the review text _clean column and apply a lambda function to it. For each review, that is, for each row in our dataset, we'll use our Veda sentiment analyzer and call its polarity scores method. The method will return the dictionary of sentiment values, negative, neutral, positive, and a combined compound score. We only need the compound score, which summarizes the overall sentiment of the review on a scale from -1, most negative, to +1, most positive. That value will be stored in our new column, giving us 1 sentiment score per review. Once we've created this column, we can use the head method to preview the results. You'll see that each review now has a corresponding VEDA sentiment score, a quick and useful way to understand the overall tone of each review. Next, we'll convert these numerical scores into positive, negative, or neutral categories. To do that, we'll create a few bins. These are the value ranges that define how the scores are divided. We'll set up 3 bins, from -1 to -0.1. This range will represent negative reviews. From -0.1 to +0.1, this will be for the neutral reviews. And from +0.1 to +1 for the positive reviews. We'll store these cutoff points in a list called bins and the corresponding category names in another list called names. Then we'll create a new column called VEDA sentiment label in our dataset. To assign the right label to each score, we'll use Panda's cut function written as pd.cut. Now, let's break down what pd.cut does. The first argument is the column we want to divide into ranges. The bins parameter defines the numerical boundaries of those ranges. Each bin represents an interval of scores. The labels parameter specifies the names we want to assign to each bin. So, in our example, pd.cut looks at every sentiment score, figures out which interval or bin it falls into, and then assigns it the label negative, neutral, or positive that corresponds to that range. After running this, our dataset will have a new column that neatly classifies each review as negative, neutral, or positive, making the results much easier to interpret than raw numbers. We can even make a nice bar chart to make it clearer. Start by indicating the column we want to visualize, VEDA sentiment label, which contains the sentiment classification for each review. Next, we call the value counts method to count how many times each label, positive, neutral, or negative appears. Finally, we add plot bar to create a bar chart from those counts. The plot part calls Panda's built-in plotting feature, which works together with Matplotlib, a popular plotting library in Python. The bar part tells Pandas to draw a bar chart instead of another type of plot, such as a line or pie chart. This way, each bar in the chart represents one sentiment category, and the height of the bar shows how many reviews fall into that category. Nice. Let's now move on to using pre-trained transformer models for sentiment analysis. We start by initializing a transformer pipeline using the pipeline function from the transformers library. For now, we'll use the basic sentiment analysis pipeline, but you can easily explore other models later to see how they perform. Next, we'll create an empty list called transformer labels to store the sentiment labels predicted by the model. Then, we use a for loop to go through each review in our cleaned text column. For each review, we perform the following steps. First, we pass the text into our transformer pipeline, which runs the pre-trained model and returns a list of results. Next, we extract the label value from the result. This will typically be positive or negative. And finally, we append that label to our transformer labels list. After collecting all the predictions, we create a new column in our dataset called Transformer Sentiment Label and store all the labels there. We can visualize the results with another simple bar chart. We start by indicating the column we want to visualize, Transformer Sentiment Label, and then call the value counts method followed by the bar method to display the results. This gives us a clear bar chart showing how many reviews were classified as positive or negative. In this case, you might notice slightly more positive than negative reviews. We don't see any neutral category because the default transformer model we used only returns two labels, positive or negative. If you'd like to include a neutral option or try other pre-trained models, you can explore the wide range of available models on the Hugging Face Transformers website. I hope you enjoyed getting stuck into some NLP using sentiment analysis. Before we go any further, we need to cover vectorizing our text. If you think all the way back to section 2, we covered text pre-processing, and I mentioned there was 3 different steps to this. The third step was getting the data in the right format for machine learning. This is where text vectorization comes in. Passing clean text into an algorithm isn't enough. We need to convert this into a numerical representation that the machine learning algorithm can understand. There's a few different ways to do this, and we're going to cover 2 of the most common methods, the bag of words model and term frequency inverse document frequency, often just shortened to TF-IDF. The bag of words model is a really simple method. It just counts which of our words appear in which of our documents. It's simple and easy to understand, but you do lose a lot of context. TF-IDF captures a little bit more of that context. It calculates the importance of that word for that particular document and takes into account how that word also appears in each of the other documents in our data. We'll cover the specific calculation of TF-IDF in that lesson, but for now, let's jump straight in and start creating our bag of words model. Let's demonstrate how to work with a bag of words model. To do this, we'll import pandas and use the Count Vectorizer class from scikit-learn's Feature Extraction text module. Scikit-learn is a powerful machine learning library in Python, and Count Vectorizer is one of its tools for text processing. It transforms a collection of text documents into a matrix of token counts. In other words, it breaks the text into words or tokens and counts how often each word appears. This gives us the numerical representation we need to apply machine learning techniques to text data. Exactly what we need. The data that we will be using for this example consists of 6 random sentences stored in a variable called data. Creating a bag of words is straightforward. The first step is to initialize the Count Vectorizer class. We'll store it in a variable called countVec. At this stage, we're not passing any parameters, so we just use empty brackets. This sets up Count Vectorizer with its default settings ready to learn the vocabulary from our text data. The next step is to apply Count Vectorizer to our text data. To do this, we call the fit_transform method on our variable countVec. Fit means that Count Vectorizer looks through the text and learns which unique words appear in the data. Transform then converts the text into numbers by creating a matrix that counts how often each word occurs. By using fit_transform, we combine these 2 steps into one line of code. Now the variable countVecFit holds our bag of words representation, a numerical version of the text. To visualize this representation as a table, we'll convert it into pandas data frame. So we initialize a new variable, and after the equal sign, we use pd.dataframe. In the parentheses, we apply the toArray method on our countVecFit variable to obtain a regular two-dimensional array of numbers which can be placed in a data frame. This way, every row will become a document and every column a word from the vocabulary. The entries will show the word counts. To label the columns, we use the method getFeatureNamesOut from our count vectorizer. This method returns the actual words in the vocabulary that count vectorizer learned during the fit step. These words become our column headers, so each number in the table can be clearly linked to a specific word. We can then print out this bag of words and see what it looks like. For each of the rows, this represents a different piece of text within our data. For example, row 0 is the text. Most shark attacks occur about 10 feet from the beach, since that is where the people are. We can see here that the words 10, about, are, attacks, beach, where are all present within this text. The next row down is just the next piece of text within the data. Each row relates to each piece of text in our data, and each column relates to one of the individual words. The values show the frequency of occurrence of each word in the document. By the way, if we want the table to indicate only whether a word is present or absent without actually counting how many times it could be found, we can do that too. Count Vectorizer has a parameter called binary. By setting binary equals true, every non-zero count becomes a 1, which gives us the simple word exists or not version of bag of words. The bag of words method is quick to build and straightforward to understand, but it has an important limitation. It only counts words. It doesn't consider their order or how important a word might be compared to others. So, while useful as a first step, it loses much of the context of the text. In the next lesson, we'll explore the TF-IDF vectorizer. This method still represents text as numbers, but it also considers how common or rare a word is across the whole dataset. Using TF-IDF to vectorize text can be a stronger approach than the bag of words model because it keeps more of the context behind each word. TF-IDF stands for term frequency inverse document frequency. In simple terms, it measures how important a word is within a collection of texts. It does this by looking at two things: how often the word appears in a single document and how common it is across all documents. Before we break down how TF-IDF is calculated, let's first define the two parts separately: term frequency and inverse document frequency. Term frequency refers to how many times a word appears in a single document. Here, a document means one piece of text, such as a row in your dataset or an item in a list. This gives us a relative frequency. In other words, how important that word is within that specific document. Inverse document frequency, or IDF, looks at the bigger picture. Instead of looking inside just one document, it looks across the entire collection of documents. Once calculated, common words will have a lower score because even though they appear often, they don't help distinguish one document from another. Less common words will have a higher score because they carry more weight in showing what a specific document is about. This helps retain context about how words are used and which words are important to specific documents and to the dataset overall. Thankfully, the sklearn package provides a TF-IDF vectorizer that performs these calculations automatically. So let's import it from the sklearn feature extraction text module. What follows is pretty much the same as what we did with our bag of words. First, we initialize the vectorizer and store it in a separate variable. Then we do the fit transform and reference our data. Next, we create our data frame and use the TF-IDF vec_fit, converted to an array, which can go into a table. Finally, we collect the column names using the get feature out method. Let's print this out. Instead of just ones and zeros, we now see a range of numbers. Each number reflects how important a word is in a specific document. Thus, the TF-IDF representation keeps more of the context. It captures not only whether a word appears, but also how it is used differently across documents. As a result, when we apply machine learning, we give our models more nuance to work with, helping them better understand patterns in the text. Now that we're comfortable vectorizing our text, we're ready to jump into the really exciting field of topic modeling. Topic modeling takes a set of documents, and by documents, I mean individual pieces of text. So this could be rows in a data frame with your text in, it could be items in a list, anything like that is just referred to as documents. Topic modeling will scan each of our documents to identify patterns. We can then group similar documents together into our topics. If you take your mind back to section 1, you'll remember we discussed supervised and unsupervised machine learning. Topic modeling is an example of unsupervised learning. We don't need any labels in our data to find these topics. The algorithms work by just identifying key patterns. The algorithms work by identifying similar word patterns throughout these different documents. From there, these word patterns are used to identify what each piece of text is talking about, and once the algorithms understand this, they can group similar documents together really easily. Let's illustrate what these different topics might look like with an example. Let's take the following piece of text. AI is now able to create videos and audio that are hard to distinguish from the real thing. Recently, a number of celebrities have been impersonated, and journalists need to take extra care verifying sources before going to publication. You don't need any special hardware to work with AI. Governments are discussing bringing in regulations and policy. So when you look through this text, you might see that there are a couple of different themes that come out. One of the topics could be around equipment, so you've got the words video, audio, and hardware that you could bring together into one topic. You then have words like celebrities, journalists, publication that could form the second topic around media. There's also some words around government, so you've got the words government, regulations, policy. This could form a third topic. This is a really basic example of how topic modeling essentially works. It looks for key themes within our text, and then once it knows these key themes, it can give an overall theme to the document and identify similar documents together. Topic modeling is a great resource for any NLP data scientist. It can work quickly and identify key themes and patterns in our data. It can also take a large amount of text and find patterns that humans just might miss if we were to do it manually. There are a number of different algorithms in the topic modeling field, but we'll be focusing on the two most common today. The first, latent Dirichlet allocation, and then moving on to latent semantic analysis. Now let's move on to our next lesson and start putting this into practice. Before we go into our practicals, let's go through some examples of where you might want to use topic modeling depending on the kind of data that you've got and the work that you're doing. One really great way of using topic modeling is grouping things together such as news articles or research papers under different topic headings. If you've been on a news website, you'll often see that articles are grouped together under topics of what those articles are about. These topics can either be created manually by editors and curators, or we could implement topic modeling to identify themes in the text and group them together under those topics, thus speeding up the process and meaning a lot less manual work. Another example is where you have customer feedback or reviews data coming in. Most companies just don't have time to manually go through all of these reviews and this feedback and see what their consumers are saying. This is where topic modeling can jump in and save you so much time and energy, going through all these reviews and pulling out key themes about what customers are saying. Topic modeling can also be used for social listening, where we monitor social media data around our brand or our product or our company and be able to quickly pull out key topics that people are talking about in relation to our brand. These are just a few examples of topic modelling, but there's absolutely loads of applications you could put this in. And hopefully this lesson has given you some ideas of where you can implement this in your work. Let's now discuss latent Dirichlet allocation and exactly how this algorithm works. Let's take an example from the last lesson. We have a collection of news articles we want to classify into different topics. So this could be politics news, sport news, business news, etc. How do we decide which document is about which topic? Well, we can look at the words they use. So for example, words such as ball, player, match, game. If these words appear many times in the document, we can probably take a guess that this article is going to be about sports news. Some words are going to be more relevant to the topic, and some words can occur in more than one topic. So for example, the word crash could be related to traffic news or financial news. We say that the topic is latent within the document. We must examine the words within it to discover the topic of that piece of text. A document can obviously contain words from more than one topic, but we make the assumption that it's mainly focused on a single topic with only a few words relating to other different topics. This is our Dirichlet distribution. So we have an understanding of what we mean by latent topics and our Dirichlet distribution. LDA then works as an iterative process, where we first specify the number of topics that we want as k. The first iteration of the algorithm is where words in the document are randomly assigned to one of the k topics. We then move to the second iteration, where we go through each individual word in the document. We assume that all of the words are correctly assigned to a topic, and we try to correct the current words we're looking at's topic assignment. LDA corrects the assignment by looking at the proportion of words in the current document assigned to a topic, and the number of times that this word is assigned to a specific topic in other documents. The algorithm iterates through this process multiple times until it reaches a steady state. It then gives us the final topic assignments for us to investigate. Now let's go to our notebook and see what this looks like in code. Topic modelling helps us uncover the main themes that run through a collection of documents. In this lesson, we'll use the latent Dirichlet allocation algorithm to find topics in a set of news articles. To do this, we'll first prepare the text, build the structures the LDA expects, and then train the model with GenSim. GenSim is a Python library designed for text analysis. It's lightweight, fast, and built to handle large collections of documents. In our case, we'll use it to create the dictionary and corpus that LDA needs, and then to train the model itself. Let's see how that goes exactly. First, we'll import the required libraries: pandas for loading and working with the news articles, RE for cleaning up the text, NLTK tools for removing stop words, splitting text into tokens, and stemming words, and finally, GenSim and GenSim.corpora for building the dictionary, the corpus, and training the LDA model. With these in place, we're ready to load our dataset and start preparing the text. So let's use pd.read.csv to load the file named newsarticles.csv and store its content in a new variable called data. Don't forget to download the CSV file in advance and place it in the same folder as your notebook document, or otherwise you'll get an error. Okay, when we run data.head, we see that the dataset has 3 columns: an ID, a title, and the article content. The content column holds the full text of each article, while the title column contains the article headlines. Next, using data.info, we confirm that the dataset has 100 rows and no missing values. That means every article is complete. Since our focus is on the text itself, we'll extract just the content column and work with it in the steps ahead. So we create a variable called articles and assign it the content column from our dataset. This gives us direct access to the full text of all news articles. Once we have the articles, the next step is to clean the text so it's ready for LDA. This includes converting text to lowercase, removing punctuation and stop words, tokenizing, and stemming, steps we already covered in the course so far. Let's quickly go over the code so it's clear what is going on. To keep it short and focused, we rely on Lambda functions and the apply method once again. Let's look at the first line of code. First, we take the content column in the articles variable and use the string.lower method to convert the text to lowercase. After that, we call the apply method to perform identical operation on every article. The operation itself is described with a Lambda function. In our case, the Lambda function says, take the input x, which here represents a single article, and return it after applying the re.sub function with our regular expression for removing punctuation. On its own, the Lambda handles just one article. By placing it inside apply, Pandas takes care of running that same Lambda function on every article in the column. Then we keep working with the articles variable, applying each processing step to it one after another. This way, the text gets progressively cleaner and more structured at every stage. So, in the next line, you can see how we remove the stop words and then we tokenize the text. Here, the Lambda applies the word tokenize function, which splits each article into a list of words. Finally, we stem. The Lambda applies the porter stemmer, reducing each token to its stem, just as we practiced before. Stemming is chosen here instead of lemmatization because we have a large amount of text, and this approach will speed up processing by reducing word forms. That said, if preferred, lemmatization can also be used instead. So, in short, we are using the same operations you've already seen in previous lessons, but now we apply them efficiently to the entire dataset by chaining apply with Lambda functions on the articles variable. Cool. After finishing the cleaning process, we can display the articles to inspect them. We see that there are 100 items, each representing one cleaned and tokenized article. The next step is to create a dictionary, which will map every unique word in our dataset to a unique ID number. We build it using corpora.dictionary and we pass in our articles dataset to it. This way, each word in the articles gets its own ID, which will later allow the LDA model to work with the text in a structured way. Print in the dictionary shows that we have 8,693 unique tokens, representing the number of unique words in our dataset. Next, we create a document term matrix. This is simply a table that shows which words appear in each document and how often. It's the same idea as vectorizing text in earlier lessons, but here we're using a method provided by the Gensim package. That method is doc2bow, standing for document to bag of words. It takes a single article, looks up each word in the dictionary, and returns a list of word IDs together with their counts. So we use list comprehension to apply this to every article in the list and collect the results into the variable doc term. This way, instead of plain text, each article is represented as a bag of words vector, which is the exact format the LDA model needs. Print in the document term matrix shows that the text has been fully vectorized into numerical representations. To begin modeling, we first decide how many topics we want the LDA model to extract. For this example, we'll set the number of topics to 2. We then create our LDA model with gensim.models.LDA model. This function needs 3 key arguments: the corpus, which is our document term matrix, the ID to word dictionary, which maps word IDs back to actual words, and the number of topics we want the model to find. Together, these inputs give the model everything it needs to start discovering recurring themes in our articles. Once the model is trained, we can inspect the results. We do this by calling LDA model print topics, where we specify how many topics to display and how many words we want to see for each topic. The output shows us the most important words that the model has identified for every topic. These words give us a sense of what each topic is about. Since we are analysing news articles, these topics are not very informative. This suggests that we may need to adjust the number of topics, clean the dataset further, or explore the data more to find meaningful topics. In the next lesson, we'll move on to a different method of topic modelling that might help us extract more interesting insights. Latent semantic analysis rests on two ideas. The first is the distributional hypothesis, which states that words with similar meanings appear frequently together. The second idea is singular value decomposition, which will abbreviate to SVD. SVD recreates text documents into different vectors. Each vector expresses a different way of looking at meaning in the text. The vectors can be expressed by the following equation. M is our document term matrix, where our rows are each individual document and our columns are our terms. The values just express whether this term is in this document. U is a document topic matrix, so instead of our terms, our columns are our topics. Sigma is a vector, where the values express how much each latent topic explains variance in the overall data. And VT is our terms document matrix, where our rows are our topics and our columns are our terms. The small t just means this is transposed. SVD is a method of dimensionality reduction. The vectors can be used to identify similar words and documents via clustering and similarity scores. So let's see what this looks like and open up our notebook. In this lesson about latent semantic analysis, we are going to use the same notebook as with our LDA model. To run this new model, we must first import the class we need. From Gensim models, import LSI model. Please note that LSI and LSA are often used interchangeably. In Gensim, the class is called LSI model, so you'll often hear me call it this way when I refer to the code. We then create our model. The code is very similar to what we did in the previous lesson. Inside the parentheses, we first reference the corpus, which is our document term matrix. Then we specify the number of topics, which we set earlier to 2, using the parameter numTopics. Finally, we set our ID to word mapping, which is our dictionary. After running the model, we display the topics using LSA model.print topics. Here we have 2 topics. We can see that they differ slightly from when we ran the LDA model. Okay, let's now move on to how we can optimize the number of topics. See you in the next lesson. To figure out the optimal number of topics, we can use coherence scores. A coherence score tells us how meaningful the top words in a topic are when grouped together. Higher scores usually mean the topics make more sense to humans. To calculate these scores, we import the coherence model class from Gensim. We also import Matplotlib's pyplot module, giving it the alias PLT, so we can plot the coherence scores and compare different numbers of topics. Okay, how do we proceed? We're going to create a for loop where we'll iterate through different numbers of topics and put these coherence scores into a list for inspection. The first step is to create 2 empty lists, one for our coherence values and one for our models. We then specify the minimum and maximum number of topics we want to run. Here, the minimum is 2 and the maximum is 11, but these can be any numbers you choose. Next, we create the for loop to iterate from our chosen minimum number of topics up to the maximum, for num topics in the range from minimum topics to maximum topics, +1 to include the maximum number. Within the loop, we create a model where the number of topics changes for each run, starting with the minimum and going up to the maximum. Let's break it down. First, we create an LSI model with the LSI model class. This gives us a new model object that we can work with. Inside the parentheses, we pass the inputs the class needs. DocTerm, which is our document term matrix we created earlier, the number of topics specified by the loop variable numTopicsI. Each time the loop runs, numTopicsI will increase by 1, starting from the minimum until it reaches the maximum. The dictionary to map IDs back to words. A random seed which makes sure we get the same results every time we run the code. Next, we append this model to our empty model list in case we want to check it later. We then run a coherence model, which takes several arguments. Our model, the original text, our articles, our dictionary, and the coherence type. Here we use CV as the coherence measure. CV combines several statistical ideas to measure how often the top words of a topic actually appear together in the documents. It's one of the most widely used choices because it often matches human judgment of what coherent topics look like. Finally, we calculate the coherence score. The method getCoherence gives us a number showing how coherent the topics are. We add this value to our list of coherence scores so we can later compare results for each number of topics. By the end of the loop, we'll have a full list of coherence scores, one for each number of topics we tested. This makes it possible to plot them and see which number of topics works best. We use plt.plot to create a line chart. On the x-axis, we have the number of topics we tested, from the minimum up to the maximum. On the y-axis, we have the coherence scores we calculated in the loop. This gives us a curve that shows how the quality of topics changes as we add more of them. When we read the plot, we look for the point where the coherence score is the highest. In our case, the peak is at 3 topics. That suggests the model with 3 topics gives the most meaningful grouping of words. We then create our final model using 3 topics by setting final num topics to 3 and creating another LSI model with this number. We can print out the results and inspect how the different words for each topic appear. It is important to note that sometimes the most mathematically accurate number of topics is not always the most valuable for your business. For example, if we set the number of topics to 11, it might also have a high coherence score, but 11 topics could be difficult to explain to stakeholders. Sometimes it is worth manually checking how the different topics look when using different numbers of topics. You can use coherence scores as well as your intuition, knowledge of the project, the business, and the people you are working with to influence the number of topics you decide to use. If you choose a value that is not the most optimal in terms of coherence score, but makes more sense to you and your business, that is absolutely fine. No one will challenge you on that unless the model is really incoherent. It is about finding the right balance. Once you have run this process a few times, you will get the hang of where that balance lies. This section is going to cover a really powerful aspect of natural language processing, and that's classifying text using your own custom labels to create a custom classifier. This is a supervised machine learning problem using different classification algorithms. The algorithms we'll be using for the lessons in this section are logistic regression, naive Bayes, and linear support vector machine. We won't be covering in too much detail how these algorithms work. We'll just be using them for text data. But if you're interested in learning more about these algorithms or how to tune specific hyperparameters, I can definitely recommend checking out the relevant courses on the 365 Data Science platform. For now, let's get started building our own custom text classifier using logistic regression.
Even though it's called regression, logistic regression is actually a classification algorithm. This means that its goal is to predict categories, also called classes. An example for such prediction can be whether a student will pass or fail an exam. This is different from regression algorithms, where the objective is to predict a continuous value like someone's exact exam score. Logistic regression is a strong starting point when building a text classifier. You can use it on its own or as a baseline model to compare against more complex approaches later. Let's begin by building a logistic regression model to classify our text data. To get started, we need to import a few Python packages. First, pandas will help us handle and organize the data. Then, from scikit-learn, we'll import only the specific tools we need: count vectorizer, train test split, logistic regression, accuracy score, and classification report. For this exercise, we'll use a sample dataset of sentences paired with their sentiment labels. Each sentence is marked as either positive or negative. Our goal is to build an algorithm that can learn from this data and then classify new sentences by their sentiment. As you've seen in earlier lessons, there are already many pre-trained sentiment analysis models available. However, sometimes their accuracy may not be high enough for your use case, or you might have very specific data that doesn't work well with existing models. In those cases, building your own custom model is a great solution. So let's do that. Here, we're creating a pandas data frame with two columns: text, which is the actual sentence, and sentiment, which is the label, either positive or negative. This dataset will serve as the training ground for our logistic regression model. The next step is to shuffle the dataset. This makes sure we have a good mix of positive and negative sentences throughout, instead of having all the positives grouped first and all the negatives grouped later. For this purpose, we'll use the sample function from pandas with the fraction set to 1. Setting frac equals 1 means we're taking 100% of the data, but in a randomized order. After shuffling, we reset the index so the rows are numbered neatly again. The argument drop equals true tells pandas not to keep the old index as a separate column. Next, we prepare the inputs for our algorithm. X will hold the text data, the text column. Y will hold the target labels, the sentiment column. The next step is text vectorization. As you remember, this means converting our sentences into numbers so the machine learning model can work with them. Here, we'll use the bag of words approach with scikit-learn's count vectorizer function. So each word in our dataset becomes a column. Each sentence is represented as a row, and the values show how many times each word appears in that sentence. That said, although we're using bag of words here, feel free to experiment with other methods we covered earlier, such as TF-IDF vectorization. Okay, we'll start by creating a count vectorizer object that we'll call countVec. Then we run fit transform on our X data, which both learns the vocabulary and transforms the sentences into numbers. We'll call this result CountVec fit. Finally, we'll convert the bag of words matrix into a pandas data frame. For the column names, we use getFeatureNamesOut, which returns the words from our vocabulary. Printing the data frame shows us the bag of words representation. Each row corresponds to a sentence. Each column corresponds to a word. Now that we've turned our text into numbers, the next step is to split the data into training and testing sets. This is a key step in machine learning. The training set is the portion of data the model uses to learn. The testing set is kept aside until the end. It helps us check how well the model performs on data it hasn't seen before. When we split the data, we separate it into features, the input data, and labels, the answers we want the model to learn. Features, in our case, the bag of word sentences. Labels, the sentiment for each sentence, either positive or negative. That's why we create 4 variables: xtrain, which are the training features or sentences in bag of words form; xtest, which are the testing features; ytrain, which are the training labels or sentiment values; and ytest, which are the testing labels. We set test size equals 0.3, which means 30% of the data is used for testing and 70% for training. A split like this gives the model enough data to learn from, while still leaving a significant portion aside to evaluate performance. And you'll often see test sizes between 20% and 30% in practice. We also add random state equals 7, so the split is reproducible. We'll always get the same train test split each time we run the code. With this setup, xtrain and ytrain will be used to train the logistic regression model, while xtest and ytest will help us evaluate its accuracy. Good. Now it's time to train our logistic regression model. We'll call it LR and create it using the logistic regression function. Next, we train the model with the fit method. The fit method takes in our training data and teaches the model to find patterns. It looks at the bag of words features in xtrain and learns how they are linked to the correct labels in ytrain. Next, we want to see how well our model does on data it hasn't seen before. This is where the testing set comes in. We use the predict method on xtest to generate predictions. Then we save these results in a variable called ypredLR. Okay, let's now measure the performance of the model. The first metric we'll check is accuracy. Accuracy tells us the percentage of sentences the model predicted correctly. To calculate this, we compare the true labels with the predicted labels. We can see our model isn't performing well. However, as mentioned, this is a really good baseline model to use before you move on to anything more complex. Finally, we'll print a classification report. This gives us more detail than accuracy alone. It shows how the model performed for each class, positive and negative. The report includes some additional metrics. Precision. Out of all the sentences the model predicted as positive or negative, what proportion were actually correct? Recall. Out of all the sentences that were truly positive or negative, what proportion did the model correctly find? F1 score, a single number that combines precision and recall into one measure, balancing the two. At this stage, don't worry if the results are rather low. That's expected because we're only using a very simple baseline model. The goal here is to have a starting point. Later, we'll try more advanced methods to improve these results. Let's try to improve the low accuracy score from the previous lesson by using naive Bayes. Naive Bayes is a simple classification algorithm that works using probabilities. For example, if we want to separate positive from negative reviews, naive Bayes looks at how often certain words appear in each group. Then it uses these counts to estimate the probability that a new review belongs to each group. Each word acts like a clue. Words such as great or amazing point toward the positive class, while words like boring or terrible point toward the negative class. Naive Bayes collects all of these clues, combines them mathematically, and then predicts the most likely class. It's called naive because the algorithm assumes each word in a review is independent of the others. That's not always true in real life, but this method still works surprisingly well for many text-related tasks, such as spam detection or sentiment analysis. Okay, to begin, let's import the multinomial naive Bayes classifier from the scikit-learn library. Next, we create our algorithm instance and call it NB. We instantiate it using the multinomial NB constructor with empty brackets. We then train the model by calling the fit method and inputting our training data xtrain and ytrain directly in the same line of code. After training, we create predictions on our test dataset by using the predict method from sklearn. We then compute the accuracy score by comparing our predicted labels yPredicted against the true labels yTest. We can see here the accuracy has improved slightly, however, it still has not worked very well. The naive Bayes model shows some improvement as it can classify both positive and negative classes. However, there is still room for improvement. We can try one more model to see if we can push this accuracy further. The last algorithm we'll test is called a linear support vector machine, or linear SVM for short. The main idea behind this algorithm is to find the best possible boundary that separates the classes, in our case positive and negative sentences. When we have only two features, this boundary is a straight line on a 2D graph. The algorithm tries to place that line so that the distance between the line and the closest points from each class is as large as possible. These closest points are called support vectors, and they are what define the position of the boundary. If our data has more than two features, which it usually does, the same logic still applies. Instead of a straight line, the boundary becomes a flat surface, like a plane, or even a hyperplane in higher dimensions. But in simple terms, the SVM always tries to find the best possible straight separation between classes, no matter how many features the data has. Linear SVMs are especially effective for text, so they're a strong choice for sentiment analysis. Let's try it out. The first step is to import the package we need. From sklearn.linearmodel, we import sgd classifier. There are a few different classes in scikit-learn that can run a linear SVM. We'll use this one in our lesson. If you look at other tutorials, you might see a different class name, but under the hood, they are all applying the same algorithm. Next, we create our model and train it on the data. We start by instantiating the SGD classifier class. We then call the fit method on our training data. As usual, this will teach the model to recognize patterns in XTrain and the correct labels in YTrain. After training, we create predictions and store them in YPred SVM. We use the predict method of the SVM model on our XTest dataset to generate these predictions. Let's now calculate the accuracy score to see if we have improved from other models used previously in these lessons. We are still getting a result that is not that great. What can we do about it? Well, we might need to revisit our data, clean it up further, or add more data to try and improve the accuracy score. This is a common scenario in machine learning projects. You do not always get the best outcome on the first try. It is necessary to run the models, evaluate their performance, and then potentially go back to your data or problem formulation to make changes upstream in your workflow to increase accuracy. In the upcoming lessons, we will cover a full practical example where we will revisit these algorithms and try them out on a different dataset. See you soon.
In this section of the course, we're going to be running through a practical example, taking one dataset and running through all the steps that we've covered in this course in a real-life business setting. Let's set the scene. So imagine you're working for a social media company and the company is concerned with the growing amount of fake news circulating on its platform. They've assigned you as a data scientist to investigate how fake news can be recognized and create a method of identifying it. Let's work through this problem together, first by exploring and cleaning the data, and then working to classify fake versus factual news stories. We'll also create some plots of our outputs and discuss how we will communicate our findings to stakeholders. So the first thing we're going to want to do is import the necessary packages. So you'll recognize these from our previous lessons. We're using the pandas package for data manipulation, matplotlib and seaborn for plotting, spaCy, ARI, NLTK, gensim and sklearn for all the different types of analysis that we want to do. We're also going to set some plot options to get started. So we're going to be setting the figure size as 12:8 to make sure all our charts are printed in a nice size, and we'll also specify a default plot color to use. So now that we've got all that set up, let's import our data. So we're going to create data and use pd.readcsv and read in fake news data.csv. Let's have a look at what this data looks like with data.head. We've got the title of a news article, the text contained within the news article, the publication date, and then a tag of whether this is fake news or factual news. We can then use data.info to get some more information about this dataset. So you can see we've got 198 entries, so 198 rows in our data, and we haven't got any null values, so we don't need to take care of this. Before we move on to any kind of comparison between the fake and factual news articles in this dataset, we need to make sure we've got an appropriate number of rows in each group. So let's plot this out and see what it would look like. We want to take our fake or factual column from our data frame and then use value counts and plot. Within the plot function, we specify we want this to be a bar chart, and for the color, we can include the default plot color. We'll also include a title, so the count of article classification. So we can see now from this chart that we've got equal numbers of fake and factual news articles, which is perfect to go forward in our analysis. If we did have significantly different numbers of rows in each group, we would need to take some steps to make this a balanced data set. In our case, we're fine to continue with our analysis. So let's go forward to our next lesson and start exploring this data a little bit. So before we get started with any text pre-processing, let's explore our dataset a little bit more. We'll start with some POS tagging. So the first thing we're going to want to do is initialize our spacey model. So we'll do this with NLP equals spacey.load and then reference the model we want to use. Because one of our tasks is to determine the differences between fake and factual news, we want to split out the dataset into fake news and factual news, and then we can compare the POS tags that occur between each of the different datasets. We'll create our fake news dataset, just taking our data frame and splitting it out where the column fake or factual equals fake news. We'll then do the same for fact news and take our data frame and filter it to where fake or factual equals factual news. From this, we can then create our two separate spacey documents. So first we'll take our fake dataset and create fake spacey docs. Because we're working over a data frame, we'll want to use nlp.pipe over our fake news text column, and then make this a list. We'll then do the same for the factual news, so fact spacey docs equals list nlp.pipe over our fact news text dataset. We then want to create a function to extract the tags for each of the documents in our data, so each of the rows in our data frame. So we create our function extract token tags that takes the argument doc spacey.tokens.doc.doc. It will then return text, the ent type, and the POS tags for each item in the document. You'll notice here we're not only extracting the POS tags, but the ent type for named entity recognition, which we'll come onto later. So now let's get stuck in and start tagging our dataset. First, let's take the fake dataset. We'll create an empty list called fake tags df. And then we'll specify the column names we want to use. So we've got token, ner tag for the named entities, and POS tag. We then want to iterate through each of the documents, so each of the rows in our data frame, and pull out the relevant tags. So we'll create our for loop for ix doc in enumerate fake spacey docs. We'll take the tags by using our extract token tags function that we created earlier, and the argument we provide is the doc. We then convert these tags into a data frame and give the column names as the columns we specified earlier. We'll then append these tags onto our fake tags df. Once we've run through each of the documents and we've populated our fake tags df, we'll then use pd-concat to get it into the right function and assign this back to fake tags df. So we'll do the exact same thing for our factual dataset, so we'll create fact tags df, and then we can just copy the code down and switch it out for the relevant dataset that we need. Let's see what this looks like. We'll take fake tags df.head. And we can see here this dataset has been broken out into the individual tokens, named entities have been pulled out where appropriate, and each token has been given its relevant POS tag. If you remember from our earlier lesson, the next thing we'll want to do is take a token frequency count. So we'll create our POS counts fake, and then fake tags df.group by, and we'll group by the token column and the POS tag column. We'll then take the size of this group and reset our index. We'll then use the name argument to name the index as counts. Next is .sort values, and we want to sort by the counts, and ascending equals false. Once we've done that, we can take POS counts fake.head and we'll specify we want 10 rows to be returned. So essentially what we're being shown here is the most frequently occurring tokens, their associated POS tag, and the number of times this token occurs within our dataset. So because we haven't cleaned our dataset yet, you can see that this is just punctuation and stop words. This isn't super interesting, obviously, from an insights point of view, but it definitely helps when you come to removing your stop words, you can reference this list and make sure that any kind of really frequently occurring words that you don't want in your dataset are properly included within the stop words. We'll then do the exact same thing for our factual dataset, so we can copy this code across and switch out the datasets from the fake dataset to the factual dataset. We'll run this, and again you can see the most frequently occurring tokens. Again, it's just punctuation and stop words, but it's really good to be able to see this, to visualize it, get an idea of what kind of words you want to remove later on in the process. The next thing we want to look at is the frequencies of individual POS tags, so how many nouns occur, how many adjectives occur, things like this. It'll be interesting to compare this between the fake and factual dataset to see if different types of tags are coming up more frequently. So to do this, we take our POS counts fake that we just created and use the group by again. Here we're just grouping by the POS tag and then we're taking the token. We'll then count these tokens and sort the values. Again specifying ascending equals false to get the most frequent first. So we can see here nouns have the most unique values, followed by verbs and proper nouns. Let's compare this now against our factual dataset. Again, we'll just copy that code across and switch out the appropriate dataset. And when we compare this, we see that the two datasets do kind of follow a similar pattern, with nouns, verbs, and proper nouns being the most frequently occurring tags. You could then ask yourself, okay, well, if this is similar, are the specific nouns that are being used also similar, or do they vary quite a lot between the different datasets? Let's investigate this by doing a deeper dive into the nouns used by each of the datasets. So from our POS counts fake, we want to filter this to where POS counts fake.POS tags equals noun. So we're essentially just taking our dataset, filtering it to where the POS tag equals noun, and then we're giving the top 15 results. These will give us the top 15 nouns used in our fake news dataset. So we've got the top 15 printed out now, and we can see that the most popular nouns are words like people, president, women, time, year, etc. Let's see if this is the same for our factual news dataset. Okay, so we can see that even though nouns are really common in both datasets, the words they use do differ quite a lot, or at least have different places in the frequency of how they're used. So we can see government is the top noun in our factual dataset, but in our fake news dataset, this is way lower. We also have words included in the factual dataset such as bill, administration, election. Election does occur in the fake news dataset, but again, it's much lower down. So it's interesting to compare these two lists and see, okay, even if the frequencies of POS tags and how often they occur is quite similar, the different words that fall under each category can differ quite a lot. If you want to, feel free to pause this video now and take a look through some different POS tags and see how the words vary between each of the two datasets. And if you're ready to move on, let's move to our next lesson where we look at the named entities between these two groups. So now we're going to be looking at the named entities in this dataset. And you'll remember from our earlier lessons that it is better to do this before you do any kind of text pre-processing. So that's why we're doing it now, to give our models the best chance of pulling out those interesting named entities before we go in and do any kind of pre-processing and cleaning of the data. Because we already pulled out the named entity tags in our last lesson when we did the POS tagging, we don't have to do that step again. We can just jump straight in and start looking at what's been pulled out. So we want to start by pulling out the top entities in our fake news dataset. So we'll start by creating our top entities fake, and this is going to be our fake dataset filtered to where the NER tag column is not blank. So this means going through and taking any token that has been recognized to have a named entity in there. We then want to group by the token column and the NER tag column, take the size, reset the index, name it counts, and then sort our values by these counts in descending order. We then want to do the same thing for our factual data, so we'll copy this code over and just swap out the correct data sets. So we're swapping our top entities fake for top entities fact, and our fake tags df for our fact tags df. I then want to create some nice plots of the named entities that have been pulled out so that we can use this in presentations or take it to stakeholders. So the first thing we want to do is create a color palette to make sure that both plots are in the same colors for the different named entity tags. So for example, if we've got different people being pulled out of the different data sets, we want to make sure that's going to be represented by the same color in both of our plots, so it looks nice and is easy to understand. We can then go on to use the Seaborn package to create some really nice looking plots. So we're going to start with sns.barplot. We specify our x and y, so our x is going to be the counts and the y is going to be the token. We then specify the hue, which is the color to use for each bar. So here we're wanting to color by the NER tag, and the palette we want to use is our NER palette that we created a step earlier. We then specify our dataset, so we're taking our top entities fake, and we just want the top 10 entities for this plot. We then change it to a horizontal bar chart using Orient equals H, and we specify Dodge equals false to get the bars in the right format. We then also set our title to the most common entities in fake news. We can see here the most common named entities that have been pulled out are people, and this is really clearly demonstrated by the colours we chose to use. I wonder if in the factual news dataset, similar names are coming up just as often. So let's copy this code over and have a look at what this chart would look like when we run it over our factual news dataset. So you can see here people's names are much less common. In fact, Trump is the only name that occurs once we look at the top 10 entities pulled out of our factual news dataset. Here, organisations and place names seem to be much more common, and there's less of a focus on people. So if you remember when we set up this problem, one of the aims is to investigate how fake news can be recognised. So you can potentially take from this that more names might be used in fake datasets and less so in factual news. This is something you could then do a deeper dive in and explore this more and really get into the data to answer that question for your stakeholders. Let's jump into our text pre-processing and start cleaning up this data for some more advanced analysis. So far, we've loaded in our dataset and explored it a little using parts of speech tagging and named entity recognition. Now we're ready to start pre-processing our text data. We've covered this a few times now, so I'm hoping you'll be an expert in cleaning up this data. First, let's run data.head just to refresh our memories on what this dataset looks like. So you can see we've got the title column, the text column, the date, and the fake or factual tags. We want to clean up just our text column. You'll notice some rows in the text data have a location tag at the start of the text. So for example, in the bottom two rows, you'll see Washington and Belfast. There's also the router's name in there, followed by a hyphen. We want to clean this up and remove it because it feels like it might impact our analysis a little bit. So how can we do this? Well, we can do it using regular expressions. The aim of this regular expression we're going to create is to look for this hyphen and remove everything before that first hyphen. So we want to create our new column, text clean, that's going to contain all of our cleaned up text. We'll then use data.apply to apply our re sub function over the rows in our dataset. So we'll specify lambda x and then use re sub and a regular expression. This regular expression is probably going to look a little complicated, but essentially what it does is look for the first hyphen in the text and remove the hyphen and everything before it. If you do struggle with creating a regular expression for your problem, I definitely recommend having a Google because there's usually someone who'll have the same problem and will have provided a solution for you. There's also some great regex generators online that you can use to help create the regular expression syntax you need for your problem. So we specify the regular expression syntax and we want to replace this with blank. So essentially we want to remove it from our text. We then specify we want this to run over the text column and our axis equals 1. So if we go back and run our data.head again, we can see that our text clean column has been added and those location tags have been removed. Our next step, as I'm sure you'll remember, is converting our text into lowercase. So we take our text clean column and then we just apply .str.lower. We then want to remove our punctuation, so this is the same code as we used before for our regular expression, except we're just switching out the syntax. This syntax will be the one you recognise that we've used to remove punctuation in our other lessons. It's basically looking for anything that isn't a word or a space and just removing it. So again, we'll run data.head and we can see that our text clean column has been nicely converted into lowercase for us. We'll then move on to removing our stop words. So we'll specify the stop words we want to use, we'll create en stop words, this equals stopwords.words, and we'll specify the language of the stop words that we want, so English. We'll then print these stop words out and have a look at what's in there. So when we did our POS tagging, you'll remember I said it was important to compare those frequently occurring tokens against our stop words list. So here you can see we had the really common tokens that were mostly stop words, so the, of, a, and. So it's really important to go back and sync that up with your stop words list and make sure that all those really commonly occurring words that you can remove are in that stop words list to be removed. So I know that these tokens we want to remove are in the stop words list, so we can go forward and just straight up remove them. Again, let's check our pre-processing by rerunning our data.head. So when we look at our text clean column and compare it to our text column, we can see that stop words have been removed. Now let's jump into tokenizing this text. This will go through each of the rows in our dataset, take the text from text clean and convert it into our word tokens. And our final step in pre-processing is going to be lemmatizing. We're going to be using lemmatizing instead of stemming because I want to use this more intelligent method to keep a lot of the context and meaning of the words where possible. Our dataset isn't too large, so it shouldn't take too long to run and won't cause too much of an issue later down the line. We've specified our lemmatizer as our WordNet lemmatizer, and then we use lemmatizer.lemmatize and in the brackets specify our tokens, for token in tokens. Let's check this last bit of pre-processing. And great, you can see that text clean has been tokenized and lemmatized successfully. Now that we've cleaned that up, let's see what our most common n-grams look like after we've done this pre-processing. So we'll create a list of our clean tokens and then go on to look at the unigrams. So we create unigrams and then we want to create a PD series and we'll use nltk.ngrams over our tokens clean. We specify the value of n as 1 because we're just interested in unigrams. We then want to take the value counts. And we can print this out up to the top 10 to get our top 10 most frequently occurring unigrams. So we can see this is much more interesting after we've done our pre-processing. It's not just stop words anymore that are coming up as our most frequent tokens. We've got much more interesting words coming out here. So let's turn this into a plot so we can put it into any presentations or discussions we're doing with non-technical people. We'll use the Seaborn package, so we'll use sns.barplot. We'll specify our x and our y. We want to specify the orientation as horizontal, so we use H. And for our palette, we're just going to be using the default plot color we specified at the start of our notebook. Of course, we also want to add a title, so we'll name this chart Most Common Unigrams After Pre-Processing. And once we've run that, it's given us a nice chart we can use of the most common unigrams in our dataset. Let's see if analysing the bigrams give us similarly interesting results. So we'll copy this code over and just switch it out to bigrams, making sure to remember to change the value of n from 1 to 2. So here again you can see we've got some really interesting bigrams coming out, such as Donald Trump, United States, White House, etc. So now that we've cleaned up our dataset and got it all in a nice format, let's move forward with some additional analysis. So in this lesson, we're going to be trying to answer the question, does sentiment differ between the different news types? So for example, does factual news have a more positive or more negative skewed sentiment as compared to the fake news dataset? Let's work through some sentiment analysis and try to answer this question. We're going to be using the Vader sentiment calculation to get our sentiment analysis. So we'll start by initializing the sentiment analyzer. So we create Vader sentiment, and this equals our sentiment intensity analyzer. We then want to create a column for our sentiment score. So within our data frame, we create the column Vader sentiment score. We then take the data.text column. So we're going to be using the raw data to calculate this. We apply the lambda function and take our Vader sentiment polarity score from our text. We then want to just take the compound from this output. If we now print out the first few rows of our dataset, we can see our Vader sentiment score with the relevant sentiment score for each of our documents. We want to classify this into positive, negative, and neutral sentiment. So first we want to specify the bins. So we create our bins from -1 to -0.1. This is going to be our negative classification. From -0.1 to positive 0.1, this is going to be our neutral sentiment. And anything from 0.0.1 above up to 1 is going to be our positive sentiment. We then create our Vader sentiment label column. and use the pdcook function. This function takes our Veda sentiment score column, chops it up by the different bins, and gives them the labels that we specified in our names above. Again, let's just run data.head to check our working. Perfect, so you can see here all the sentiment scores that are less than minus 0.1 have been classified as negative, and there's a few positives in there as well that have been correctly categorized. Let's now see if we can use this to answer the question of whether sentiment differs between the two different types of news articles we have. We want to create a bar chart of the different labels in each of the data. We'll first start by just looking overall how many positive, negative, and neutral sentiments we have across the whole data set. So we'll use data Veda sentiment label .value counts .plot .bar, and the color will be our default plot color. So from looking at this chart, you can see that overall we've got a few more news articles with a positive sentiment as opposed to a negative sentiment. And we've just got a few neutrals in there. Most of them have been classified as positive or negative. Let's now look at how this varies between the two types of news articles we have. So we want to use sns.countplot. Our X is our fake or factual column. Our hue, so our color, is our Veda sentiment label. And the color palette we're going to use is the SNS color palette HLS. We also want to set the title, so we're going to call this Sentiment by News Type. So let's look at this plot and what it tells us. When looking at the fake news, we can see there's a pretty even split between positive and negative sentiment, and a few neutrals in there, but there isn't really a massive skew to one or the other. In our factual news dataset, if you just look behind the legend, you can see that positive does skew more in this dataset. So we have a few more positive articles as opposed to negative in the factual news dataset. There's also a lot less neutrals in this. So the differences aren't drastic. So I don't think you could say at this moment that factual news skews more positive and fake news is a little bit more evenly distributed. It would require a bit more of a deep dive. One thing we could also do is try to change the method we've used of determining sentiment. So we could experiment with different rule-based models, or we could implement the pre-trained transformers that we're now comfortable in using. Now that we've had a look at our sentiment analysis, let's move on to exploring topics within this dataset. So in this lesson, we're trying to address the question of what topics appear in our fake news. We're interested to see if any particular topics come up that might help us identify a fake news article. For this, we're going to obviously be using topic modelling, and we're going to start by using latent Dirichlet allocation. The first step for us is going to be vectorising our text. We want to convert our text into numbers that can be fed into the LDA algorithm. So let's start by creating our fake news text, which is just going to be our dataset filtered to where fake or factual equals fake news, and then we're just taking our text clean column and resetting our index. This is just going to leave us with the cleaned up text from any article that's been classified as fake news. We then want to create our dictionary. So to do this, we use corpora.dictionary and then reference our fake news text. And finally, we want to create our bag of words. So we create our document term fake, and then from dictionary fake, we take doc to be of words over our text for each of our texts in fake news text. So we're going to jump straight into generating coherence scores to determine the optimal number of topics. So we create an empty list for our coherence values, and we create an empty list for our models. We also specify the minimum topics we want to test, which we'll set at 2, and the maximum topics we want to test, which we'll set at 11. Let's now create a for loop to run over each of the iterations of this model. So for num topics I, in the range from the minimum topics to the maximum topics plus 1, so from 2 to 12. We then create our LDA model, feeding it our doc term fake. Our number of topics will be specified to the num topics I for each of the iterations of our for loop, and ID to word is our dictionary fake. We then want to take this model and append it to our model list. From this, we can then create a coherence model for the model we're using in this for loop. So we use coherence model, model equals model, text equals fake news text, dictionary equals dictionary fake, and coherence is C_V. We then append coherence model get coherence to our coherence values. So what this loop will leave us with is a list of all our models in models list and a list of the coherence values put into our coherence values list. Let's now plot these coherence values to see what they look like for each of the iterations of our model using a different number of topics. We're going to use plt.plot, and we're going to be plotting the range from our minimum topics to our maximum topics plus 1 against our coherence values. We add a label to our x-axis for the number of topics. We use plt.ylabel for our y-label axis, which will be the coherence score. And we add a legend for our coherence values and specify the location. So we can see the coherence scores are highest when the number of topics was set to either 2, 7, or 11. For our example, we feel like 2 topics might not give us enough interest, whereas 11 topics is going to be too difficult to explain to different stakeholders and get an understanding of what those topics are around. So let's create our final LDA model with 7 topics. We specify the number of topics that we've chosen to be 7. We then create our LDA model. We use gensim.models.lda model as we used before and reference our doc term fake, our dictionary, and our number of topics we want to use. We can then use LDA model.print topics to print out the words that occur with each topic. We specify the number of words as 10. We want to see the 10 most common words for each of the topics. When we look through these topics, we can see that there is quite a lot of overlap. So for example, the word Trump is a really frequently occurring word in all of the topics, as is the word said, and other words throughout there as well also appear in a number of different topics. In our next lesson, let's try some different techniques to pull out some more interesting topics and hopefully get some more insightful analysis. Because a lot of the topics in our last lesson came out to be really similar, let's try some different methods. The first thing we can change is using the TF-IDF vectorization of our text, as opposed to just the bag of words model. We're going to be using latent semantic analysis, as opposed to latent Dirichlet allocation, to see if that gives us different results. For this lesson, we're going to be creating a couple of different functions. The first thing we want to do is define a function to create our TF-IDF corpus. So we start by defining this function, TF-IDF corpus, and the argument it should receive is a document term matrix. The next step is to create the TF-IDF model. This takes the arguments of the corpus, which is our document term matrix, and normalize equals true. We then create our corpus TF-IDF, which is the TF-IDF doc term matrix. Our function will then return this corpus for us. We then want to create a function to get the coherence scores, so we can find the most optimal value for a number of topics. So we define the function getCoherenceScores, and the arguments it wants to receive are the corpus, the dictionary, the text, the minimum number of topics, and the maximum number of topics we want to test. We'll then create an empty list for our coherence values and an empty list for our models list. We then create our for loop, so for num topics I, in range min topics to max topics plus 1. We create our model using the LSI model, which takes the arguments corpus. The num topics will be set to the num topics I for that iteration of the for loop, and the ID to word will be our dictionary. We then append this model to our model list. The next step is to create the coherence model, which will take the argument of the model, the text, the dictionary, and the coherence, which we set to C_V. We then append the coherence model.getCoherence to our coherence values and create a plot. The plot will be plotting the number of topics against the coherence values. We also add the appropriate X label for the number of topics, the Y label for the coherence score, the legend, and we want to include PLT show to make sure our plot is printed out correctly. So now that we've defined our functions, let's create our TF-IDF representation of the text. So we create our corpus TF-IDF fake, and this equals TF-IDF corpus, which is the function we created earlier, and then we provide it with our doc term fake, which is our document term matrix. From here, we can get the coherence scores using our getCoherenceScores function. The corpus is the corpus TF-IDF fake, our dictionary will be dictionary fake, our text will be fake news text, and we'll use the same arguments as our last lesson. So our minimum number of topics will be 2, and the maximum number of topics we want to try will be 11. Now we have our coherence scores, we can see that the optimal number of topics looks like it will either be 10 or 7. Let's now create our final model. So we specify our LSA model, and we use the LSI model function. We feed it the corpus TF-IDF fake, our dictionary fake, and we set the number of topics to 7. So our first topic seems to have the words Trump, Clinton, and Hillary. The second topic, boiler, ARC, room. The third topic, Flynn, immunity, Nana. And again, if you read through the topics, you can see there's a lot more differences here compared to when we ran it in the last lesson. These are much more interesting topics to discuss, and dig into what these differences are around the different topics and what that might mean. So when you're presenting this back and answering the question, what are the different topics appearing in fake news? This is something that you can present and talk about the different themes that are coming out of this text and the different things that are being discussed. Welcome to this last lesson of our practical session. In this lesson, we're going to be covering, can we create a custom classifier to accurately classify fake news versus factual news in our dataset? So before we jump into this, let's just refresh our memory on our data. So let's run data.head. We can see here we've got our text clean column that's been appropriately tokenized, lemmatized, converted into lowercase, stop words have been removed, so we're ready to move forward in creating our classification model. We want to create our X and Y variables to split into training and test data. We'll start by creating our X. This is going to be our clean text that we're then going to go forward and vectorize and give to our algorithm as its input. Our Y value is just going to be our fake or factual tag. Now let's move on to text vectorization. So we'll create our count vectorizer as we're going to be using the bag of words model to vectorize this text. Once we've initialized the count vectorizer, we can create countVec_fit and use countVec.fitTransform on our X dataset. We then want to create our bag of words as a pandas data frame. So we use pd.dataframe and we want to convert our countVec and convert it to array. The column names of our data frame can be obtained by using countVec.getFeatureNamesOut. So this will have successfully vectorized our text and it's ready to be split into training and test data. To do this, we want to create our X-train, X-test, Y-train, and Y-test. To split up our training data, we'll be using train-test-split. We want to split our bag of words dataset and our Y vector. We also specify the text size to be 0.3, so 30% of the data is going to be going to our test dataset and won't be used for training. We want to start creating our classifier with just a simple logistic regression to see how this performs and use it as a baseline for other models we may want to try. So we create our LR and use the logistic regression function, and then we want to use .fit and reference our X-train and Y-train. Our logistic regression model has now been created, and we want to use this to predict our test dataset and compare this to our actuals. So let's create ypred_lr and then use lr.predict on our X test. We can then use this to compute the accuracy score. So we'll be using the accuracy score function and comparing the accuracy between ypred_lr, the predicted labels from our logistic regression model, and comparing this to our actuals in y-test. You can see here we've got some really good accuracy at 96%. Let's dive into this a little bit further using the classification report. We can see here the model has done amazingly well at predicting fake and factual news. This model is perfectly fine on its own, the accuracy seems really good, but out of interest, let's just see what it would look like if we used an SVM, support vector machine. We create our model using the SGD classifier, and then we reference .fit and our X-train and Y-train. As our model has now been created, let's again run our predictions using this new model. We create our ypred SVM and then use svm.predict on our test dataset. Again, let's have a look at the accuracy of this model and see if it's improved anymore from our logistic regression. So we can see here this model has actually not performed as well as the logistic regression. This is why it's really important to try simple models first before moving to anything more complex. We print out this classification report again, and we can see here that it's done pretty well. The model has worked well, and it's giving us 90% accuracy across the board. However, the logistic regression has seemed to work better. So to answer the question, can we create a classifier that can classify different news as fake or factual? The answer is yes, and it seems to be quite a good problem for these algorithms. They seem to work with really good accuracy. So I hope you've enjoyed working through this practical lesson as we run through each step by step, with the same data and see what that process would look like as a full NLP project. You've now got a really good project to put in your portfolio and show off your new NLP skills. Welcome back, and I so hope you've enjoyed working through the different topics on this Introduction to Natural Language Processing course. Of course, the field of NLP is huge, and there's always new things evolving and new things being developed. In this last chapter of the course, we'll be discussing deep learning, its applications, and where we think NLP might be going in the next decade. Before we start discussing how deep learning has impacted the field of NLP, let's first clarify what we mean by deep learning. This is just going to be a high-level introduction. We're not going to do any code, but if you are interested in creating your own deep learning models, there's a great course on the 365 data platform that I would definitely recommend. So let's get started. Unlike traditional machine learning algorithms, deep learning, also known as neural networks, are built to simulate the human brain and its structure and function. These neural networks consist of interconnected layers that aim to analyze data and uncover patterns. Neural networks consist of input layers, hidden layers, and output layers. Each layer receives its input, applies an activation function, and then passes it on to the next layer. Each layer consists of individual neurons, and the strength of the connections between these neurons, known as weights, determines the impact of these neurons on the final prediction. By adjusting the weights between these neurons through our model training, neural networks can learn from data and use this to improve their performance. There are several different types of deep learning architectures, each suited for different types of tasks and data. For example, convolutional neural networks excel at image and video processing by exploiting spatial correlations. On the other hand, recurrent neural networks use connections that can process feedback loops, so these excel at processing sequential data such as language for NLP. Training a deep learning model involves optimizing these individual weights of the neurons to eventually minimize the difference between the predicted output that our algorithms are giving us and the actual output that we're looking for. Deep learning has made remarkable strides over the past few years and really pushes the boundaries of what we thought would be possible. With the advancements of hardware capabilities, deep learning has become much more complex, able to handle massive amounts of data. It's a super interesting field and especially has amazing implications for natural language processing. So in our next lesson, we're going to be discussing how this relates to NLP and the advancements that have been made in deep learning with NLP over the last few years. So now you have at least a basic understanding of deep learning, let's discuss some of its applications for NLP. One of the most famous examples at the moment, and maybe the reason that you reached out to look for this course, is ChatGPT, an advanced language model built by OpenAI. At its very core, ChatGPT uses a neural network architecture called a transformer. And if you think back to our lesson on sentiment analysis, you'll recall that we used one of these pre-trained transformer models to discover sentiment in our text. More generally, ChatGPT is an example of a large language model. Large language models are designed to understand, process, and create human-like text by learning from a vast amount of data. These large language models are trained on vast amounts of diverse data, from books to websites, articles. Loads of different text data is fed in to allow the understanding of human language, of patterns, semantic relationships, and grammar, so that human-like text can be generated. These models have demonstrated significant advancements in the field of NLP and have found use cases across the board in chatbots, in content generation, in language translation, so many different applications for these large language models. As we continue to refine and advance these models, the potential for more interactive and more sophisticated advanced human-computer interaction becomes more attainable. So it's a super exciting time to get started in the field of NLP, and I'm so happy that you decided to start your journey with me in this course. As we've been working through the practicals in this course, you may have noticed we often reference the language we want to use. For example, when we were creating our Spacey model, we specified an English language model, and when we're using our stop words, again, we specified we wanted these to be in English. This course has focused on using NLP with English language data, but there are loads of developments being done in other languages that mean NLP solutions can start being used for a global audience. However, it is quite challenging as some languages just don't have the large amounts of easily accessible data required to train these kind of natural language models. Even the way we pre-process text needs to be adapted for each individual language to take into account different grammatical rules and sentence structures and contextual information contained within the written language. So if you're wanting to work with non-English data, what do you do? Well, the first thing I'd recommend is checking out the documentation of the packages we already used and see what kind of languages they support and whether you can just switch out the language models that we used, but continue to use the same code. The other option is to check for additional packages that have been developed with your language in mind. So, for example, the INLTK package has been developed for the Indic languages such as Hindi and Tamil. Expanding the language capabilities of NLP is a key aspect of future development to help ensure we create inclusive solutions for a global audience. So, in our next and final lesson, we'll look at some of the advancements of NLP and where we think it might be heading in the future. The field of NLP is expected to continue to evolve rapidly, with technological advancements and the increasing availability of large-scale datasets for training. Here are some ways we can expect NLP to evolve over the next few years. The first is that NLP is expected to gain a deeper contextual understanding, so getting better at understanding semantics and general word knowledge, and even being able to have reasoning capabilities behind its decisions. The second is multimodal understanding. So NLP will be fed not only with text data, but with images, videos, and audio, so that the language model can get an even better understanding of how language works in the different contexts it can be used. As the demand for faster, more interactive NLP solutions increases, we'll also see advancements in the optimization of model architectures, as well as the technologies required to deliver more real-time solutions. We're also going to be hearing more conversations around ethical considerations, biases, and privacy concerns to ensure we keep fairness, inclusivity, and transparency at the forefront of any new NLP development. As you'll have seen going through this course, NLP has so many amazing applications for our everyday lives. I truly hope you've enjoyed going through this course with me, getting an introduction to natural language processing, and hopefully you're ready to start building some NLP solutions of your own. Hello and welcome to this introductory course into the fascinating and exciting topic of large language models. This course has been designed for those who want to expand their natural language processing capabilities by learning how we can harness the amazing power of large language models. By the end of this course, you'll understand how these models work and how to start applying them to your own project. I'm thrilled that you've chosen to take this course with me. Let's first go over what you can expect to learn and what skills you'll leave this course with. The first section of the course will introduce the concept of large language models. We'll cover what they are, what they can do, and start to look at how they work. Section 2 of the course will do a deeper dive into the workings of an LLM as we introduce the concept of transformers. Transformers are the breakthrough architecture that has allowed the rise of LLMs in recent years. Once we understand this transformer architecture, we can start to experiment with LLMs. And in Section 3 of the course, we'll start working with GPT models. We'll also look at how we could integrate our own custom data with these models using LangChain, a powerful and exciting new framework for working with large language models. Being able to add your own data to a language model is going to give you so many options for working with them. Next, we'll move on to introducing the Hugging Face package. This is a key Python package for working with large language models. The final 2 sections of the course will put all of this together into some practical lessons, where we'll experiment with 2 other types of language models, so you'll have loads of examples to add to your portfolio. So let's embark on this journey into large language models together. First, let me introduce myself. My name is Lauren Newbold, and I've been working as a data scientist for several years, for large organisations such as the BBC, as well as small startups using natural language processing in unique and innovative ways. I'm passionate about getting people excited about data and the opportunities it can provide us. Now that I've introduced myself and a little bit about the course, let's get started with the first lesson and look at what we mean when we talk about large language models. In recent years, it's been hard to escape large language models, as they've been all over the global news. One of the most famous models in this realm is OpenAI's ChatGPT, which has dominated the news with its ability to write poetry, essays, social media content, code, and so much more. GPT and similar models have even been employed to translate languages in real time during international events and aid in disaster relief efforts by quickly translating vital information into multiple languages. Large language models have also found their way into the world of healthcare, aiding in medical research and diagnosis. Whether you're an experienced NLP developer or not, it's been hard not to have heard of LLMs. But what exactly are they, and why are they causing such a stir? To put it very simply, imagine you give a computer access to the entire internet and tell it to learn everything it reads, as well as using this as a method to learn the structure and grammar of language. This isn't exactly how an LLM works, we'll come on to that later, but the outcome is the same. You're left with a machine that has great general knowledge. And not only that, but the machine can actually talk to you about what it knows. You can ask it questions or give it a language-based task, and the machine will understand your question and be able to give you an appropriate response. Large language models represent a transformative breakthrough in the field of artificial intelligence and natural language processing. These models are a testament to the remarkable progress made in machine learning, enabling computers to understand and generate human language at an unprecedented scale and complexity. At the heart of these large language models lies deep learning, a subset of machine learning that mimics the human brain's neural networks. However, what really led to the massive innovations we see today is a type of model architecture known as a transformer. This is a novel way a machine can learn the complexities of language, and transformers are the reason the models we see today have such amazing results. There are 3 main features to a large language model which makes them unique. The first aspect, as you might have guessed by the name, is that large language models are, well, large. Compared to other models we've seen before, these models are massive in size. Their size is one of the aspects that allows for the amazing results we've seen from large language models. The second aspect of LLMs is their general purpose, and the third is that they're able to be pre-trained and fine-tuned. Now, let's move on to our next lessons where we go over each of these features in more detail. As I mentioned in the last lesson, Large language models are characterized by their immense size. By size, we're not talking about physical space. The size of an LLM is measured by the number of parameters it has. But what does having a large number of parameters mean? Imagine you're teaching a robot how to play a really complicated game. To do that, you need to give it lots of instructions and rules on how to play the game. Each of these rules is like a piece of information that the robot needs to remember. Now, think of the parameters in a large language model like those instructions and rules. They are tiny bits of information, kind of like building blocks, that help the model understand and generate language. But here's the thing. Large language models have a huge number of these tiny building blocks, like millions or even billions of them. The more parameters a model has, the better it can understand and work with language. It's like having a bigger and more powerful brain for language tasks. So, when we say a model has lots of parameters, we mean it has a massive collection of these little pieces of information that make it smart when it comes to understanding and using language. The most famous LLMs contain millions to billions of parameters. For instance, BERT, a large language model developed by Google, has 345 million parameters, and GPT-4 gets even bigger at 1.7 trillion parameters. Large language models are also trained on huge amounts of text data. The more text a machine is given to read, arguably the more successful it's going to be at learning the complexities of language. So, LLMs are trained on massive amounts of text data from the internet. It's like they read the entire internet itself, but just really, really fast. This text data includes things like books, so large language models will read tons of books on all sorts of topics, from adventure stories to science textbooks. They also go through websites like news articles, blogs, and even social media posts to see how people talk online. They study Wikipedia articles to learn about facts, history, and general knowledge. They also look at how people chat with each other online to understand how language is used in everyday communication. There's also a few other bits that they'll go through, so like recipes, movie reviews, and scientific papers. By taking in all this text data, large language models learn the patterns, grammar, and vocabulary of human language. It's like how we learn to speak by listening to others and reading books, but large language models do it on a much larger scale and much, much faster. The second aspect of a large language model is that it's general purpose. When we say that an LLM is general purpose, we mean that the model has been trained on a wide variety of text data from the internet, and it's designed to understand and generate human language in a broad and versatile manner. It's not specialized for just one thing. It's a multi-talented language tool that can assist with many different jobs involving words and communication. If you've worked with much machine learning before, you'll be familiar with training a model for a specific task, such as classification or clustering. But with LLMs, the initial goal is to give the model a general understanding of knowledge and how language works, so that it can be applied to more specific tasks later on. We pre-train the model to understand general language and solve many general-purpose problems. Then we can fine-tune it to work on specific tasks or industries. Now, let's do a deep dive into what we mean into pre-training and fine-tuning these models. So, what exactly do we mean when I say that we pre-train and fine-tune a large language model? Well, think back to when you were in school. To start, you learn a broad range of subjects and topics to get a base understanding of the world around you. However, later, as you choose your career, you'll have focused your attention to more specific subjects focused on that career. You still reference what you learned in those early years at school and build on it to understand new knowledge related to your specific field. It's kind of the same concept with LLMs. They're pre-trained to solve a variety of language problems and then can be fine-tuned to work in specific fields such as media, finance, transport, etc. In the pre-training phase, the large language model is exposed to a massive amount of text data from the internet. It learns the basis of language, like grammar, vocabulary, and common sense by predicting what words come next in sentences. This is similar to you learning how to speak, write, and get some general knowledge in your early school years. Once the model has a good grasp of the basics, it can be customized for specific tasks. For example, you might want it to be really good at answering medical questions or helping with customer service inquiries. In the fine-tuning phase, the LLM is trained on a smaller, more specialized dataset related to the specific task that you want it to do. It takes the skills that it learned during pre-training and it gets better at the specific task you want it to do. You can almost think of it like you taking this course now. You'll still kind of reference that very early stuff that you learn in school, but we're really specializing your skills now with this course. Because large language models have been pre-trained on such large amounts of data, they can often even do well on tasks without any additional industry-specific data. They can be used for what is known as few-shot or zero-shot scenarios. A few-shot scenario is where we use minimal data to train a model, and zero-shot is where the model can recognize things that it's not been explicitly taught in the training before. So in some cases, you're able to use an LLM straight out of the box without any additional data. So now that we have an idea of what LLMs are, let's have a look at some applications. The novel thing about large language models is that one model can be used for a variety of tasks. Because they have been trained on such large datasets with so many parameters, they're able to learn a lot. Let's run through some examples of the kind of things large language models excel at. The first is content creation. Large language models can write articles, blog posts, or even creative stories. They generate text that reads like it was written by a human author, making them handy tools for content creators. LLMs can also translate text from one language to another. You can type in a sentence in one language, and the model will provide a translation in your desired language. Many translation apps on your phone will use a large language model behind the scenes to provide real-time translations when you travel or communicate with people who speak different languages. LLMs are also great at answering questions for you. You can ask a model questions on various topics, from historical facts to solving math problems, and they'll do their best to provide accurate answers based on their extensive knowledge. You can also use LLMs to create chatbots and virtual assistants that can hold conversations with users and customers, answering common queries and assisting with tasks like setting reminders or finding information online for you. LLMs can even analyze text. So, for example, they can pull out the sentiment of a text, determining whether a piece of writing is positive, negative, or neutral in tone. This is a useful skill for businesses to gauge customer feedback or for tracking public sentiment on social media. Furthermore, large language models can take long articles or documents and generate concise summaries, making it easier to understand the main points without having to read the entire text. Another thing LLMs can do is content recommendations. They power recommendation systems suggesting movies, books, articles, or products based on your preferences and past interactions. For programmers like ourselves, large language models can also assist by generating code snippets for specific tasks, helping with debugging, or explaining complex programming concepts. In healthcare, these models can assist doctors by analyzing medical records, suggesting possible diagnosis, and even staying updated with the latest medical research. In the legal field, these models can review documents, contracts, and case histories to provide lawyers with quick insights and help identify relevant information. And if you work in marketing, LLMs can analyze customer data to help businesses create personalized marketing campaigns, recommending products or services based on the individual customer preferences. These examples showcase the incredible versatility of large language models. They are like the Swiss Army knives for language-related tasks, able to assist in a wide range of fields, from content creation and customer service to healthcare and beyond. In the early days of coding, we had to hard code rules that would distinguish one class from another. For example, if you've been in machine learning a while, you're probably familiar with the famous iris dataset, which contains information on different types of flowers. In the old days, we would just hard code rules to determine the species of the flower. Say, for example, if the petal size was smaller than 1 centimeter and the sepal length less than 5 centimeters, we can create a rule to classify this as Iris setiza flower. But we've come a long way from there, and now we have machines where we can show a picture of a flower and ask what type of flower this is. In terms of natural language processing, we can build generative models capable of having conversations about flowers, where we could discuss different aspects of the flower and ask the model to identify our flower that way. So, what led to these advancements which now provide us with such powerful models? Large language models are based on a transformer architecture, a type of neural network that was developed by Google Brain researchers in 2017. Transformers are a subset of deep learning. So before we jump into learning about transformers, let's quickly recap what we mean by deep learning. Deep learning is a type of model architecture that can excel at finding patterns in complex data due to its network structure. It begins with input data, such as text or images, and this input is then passed through layers of interconnected neurons, forming a neural network. Each neuron applies a mathematical operation, including adjusting the strength of connections or weights between the neurons. These weights are continually updated during a training phase to minimize the difference between the predicted output and the actual output, a process known as optimization. Through iterative adjustments and learning from vast amounts of data, the neural network gradually fine-tunes its weights to make increasingly accurate predictions or classifications, ultimately producing an output that can include anything from text generation and image recognition to complex decision-making, classification, and problem-solving. Different types of neural networks have been built to excel at different types of problems. For example, convolutional neural networks are designed to mimic the way the human brain processes vision, and so these models excel at vision classification tasks. Neural networks seem to do pretty well at analyzing images, but often still struggle to analyze language. Before transformers, the best thing we had for language was recurrent neural networks. Let's say we want to translate a sentence from English to French. A recurrent neural network would take one word of the input sequence at a time, process it, and then sequentially give the translated output one word at a time. The sequential aspect of this process is important. If you shuffle words around in a sentence, you can often change the meaning of the sentence or remove any meaning from it whatsoever. So being able to preserve the word order by dealing with words sequentially is important. But recurrent neural networks really struggled when the input text was long, such as an entire essay. Once they get towards the end of the piece of text, they'd forgotten what had been said at the beginning. This is a real problem, as it will miss important context from earlier in the text that may be important throughout the whole input. For our language models to work effectively, they need to have some sort of memory of what was said earlier in the text. Take, for example, the following sentence. The New York Times is a daily newspaper. It was first issued in 1851. In the second sentence, it refers to the New York Times from the first sentence. But we would only know this if we were able to keep in memory what was mentioned in the first sentence. If we were only able to look at each token at a time, or tokens that are very close to each other, then we would not be able to truly understand the meaning of the second it, and thus the meaning of the whole text may be lost or misunderstood. By also processing words sequentially, it means that recurrent neural networks couldn't parallelize well. If we break up a piece of text to run in parallel, the recurrent neural network has no way of passing important contextual information
within the text between itself. This means that training would often take a very long period of time, and it limited the size of the datasets that could be used for training. Recurrent neural networks would not be able to handle the size of the training data we see used for large language models today. It would just take too long. This is where transformers come in. Not only do transformers work in such a way that we can utilize parallelization, but they also have a novel way of being able to pay attention to the most important words in the text required for context. This means that transformer models can have a superior understanding of contextual information in the text. You might notice I said that transformer models are able to pay attention to the most important words in a piece of text. Attention is the name given to the technique that allows the transformer to pay attention to specific words. Let's now move on to our next lesson, where we cover attention in more detail and see how it's enabled the incredible language models we see today. In 2017, a paper was released titled "Attention is All You Need," where the researchers introduced the concept of transformers along with the attention mechanism that formed a fundamental part of these models. The attention mechanism enables a model to weigh the importance of different words or tokens in an input sequence when producing an output. The key idea behind attention is that instead of processing the entire input sequence at once in a fixed manner, the model can selectively attend to relevant parts of the sequence at each step of processing. This is achieved by assigning a weight or an attention score to each token in the input sequence. Tokens with higher attention scores are considered more important for the current step, and the model uses these scores to compute a weighted sum of the input tokens. This weighted sum is then used to generate the output. This mechanism is what enables transformers to manage long-range dependencies in data. It's fundamentally a weighting scheme that allows a model to focus on different parts of the input when producing the output. The paper gives an example of the importance of attention during language translation. Suppose we want to translate the following phrase from French to English. A simple translation model could take each word in the text and translate it to English each token at a time. However, this would be incorrect, as the order of words in French versus English differs. So the following phrase would be translated to area economic European rather than the correct version in English, which would be European Economic Area. A simple word-to-word translation is not good enough. We also need to be able to look at or pay attention to other words in the text. This chart is from the 2017 paper, and it shows which words are being paid attention to during translation. You can see that it's not a simple one-to-one relationship. Relevant tokens are being paid attention to at each point to ensure the correct translation. When dealing with transformers, you'll also hear the phrase self-attention. Self-attention is a term for a specific type of attention mechanism that computes relationships within a single input sequence, allowing the model to capture contextual information and dependencies between input elements effectively. So, now we have an idea of how powerful transformers can be, let's take a deeper look into their architecture. This diagram gives an overview of the transformer architecture. This can look quite complicated at first, but we're going to go through each step and break it down so you can understand what's going on before we start using these transformers ourselves. Let's think back to our example of translating between French and English. If we chose to use an RNN, a recurrent neural network model for this, each word would be passed as an input one at a time. In a transformer, however, we're able to feed all the input words into our model at once and deal with them simultaneously. This is such a powerful aspect of transformers. But how is it possible? The transformer uses an encoder-decoder architecture, which we'll go through in more detail now. Let's first look to the encoder block and see what's going on there. The first step in a transformer's architecture is creating the input embeddings. If you're familiar with natural language processing, you'll know that we can't feed text directly into a model. We need to first convert it into a numerical representation. Let's go through the process of creating these input embeddings together. The first step is to break down the input text into tokens. So if you're not familiar with tokens, these can be words or subwords or even characters of the text, depending on the specific tokenization strategy used. For example, the sentence, "I love natural language processing," might be tokenized into the following. Each token is then mapped to a unique identifying number based on a predefined vocabulary. This vocabulary is typically built from a large corpus of text and contains all the tokens the model can recognize. For instance, I might be mapped to number 34, love to number 56, and so on. Once tokens are mapped to their respective indices, the model retrieves its pre-trained word embeddings from an embedding matrix. This embedding matrix contains vector representations, often called word embeddings, for each token in the vocabulary. For example, the embedding for I might be a vector like this. These vectors encode semantic and syntactic information about the tokens because the words that are similar to one another in meaning are mapped close to one another in the vector space. However, the same word can have different meanings depending on how it's used in a sentence. This is where positional encoding comes in. Positional encoding is essentially where we give each token a number, recording the position of the token in the sentence. This means we can keep the information of the order of words within the input data itself, rather than having to deal with one word at a time in sequential order. To ensure that all input sequences have the same length, padding or truncation may also be applied. Padding adds special tokens or zeros to the embeddings of shorter sequences, while truncation removes tokens from longer sequences. This is required for certain models, and we'll look into this later when we get to our practical lessons. The embedding process captures the contextual and semantic information of the input text and represents it in numbers. This is a crucial component in the success of large language models. The resulting input embeddings for all tokens in our input sequence are then fed to the encoder block of the transformer. Once we have our input embeddings and our positional encodings, we're now ready to pass this data onto the encoder block, where it goes through a multi-headed attention layer and a feed-forward layer. One of the core components of the encoder block is the multi-head attention layer. It allows the model to weigh the importance of different tokens. This layer gives us attention vectors that capture contextual information between every token in the text. Let's go through the steps to how these attention vectors are calculated. For each token in the input sequence, we create 3 vectors: a query vector, a key vector, and a value vector. For each token in the input sentence, a query vector is calculated. This query vector represents the tokens in question about the other tokens in the sentence. It's kind of like saying, how much should I pay attention to each of the other tokens? To put it simply, you can think of the query vector as the currently attended to token in the input sequence. The key vectors, on the other hand, hold information about all the other tokens in the sequence. Each key vector corresponds to a different token and contains information that helps determine how much attention should be given to that token. Value vectors are associated with each token in the input sequence. Think of them as information containers that hold the actual content or knowledge about each token. When the query token, the token currently being attended to, asks questions about attending to other tokens, the value vectors provide the answers. The values for these different vectors are what's learnt through training our model. The next step in the process is that we calculate the similarity between each query vector and all key vectors using dot products. This produces a set of similarity scores, one for each token in the sentence, indicating how much attention each token should receive from the currently attended to query token. To ensure numerical stability, we scale the similarity scores by dividing them by the square root of the dimensions of the key vectors. This scaling factor helps control the magnitude of the scores. Next, we apply the softmax function to the scaled similarity scores to obtain an attention weight. The softmax function normalizes the scores so they sum up to 1, effectively turning them into probabilities. So, now we have an attention weight for each token in the sequence, indicating how much attention the query token should give to each other token. We then calculate the weighted sum of the value vectors, using the attention weights. This step aggregates information from the entire input sequence, giving more importance to tokens with higher attention weights. The resulting attention vector represents the combined information from the input sequence, focusing on relevant tokens based on the attention mechanism. We say that this layer of the transformer architecture is multi-headed because transformers will try multiple different iterations of query, key, and value projections, known as heads. Each head learns a different set of weights, allowing the model to focus on different aspects or patterns in the data. The attention vectors from each head are concatenated and transformed to produce the final output of this layer. After the multi-headed attention mechanism, the output is passed through a feed-forward neural network. The feed-forward network learns to capture and model complex, nonlinear relationships within the input sequence. The feed-forward layer in the transformer encoder block is a key component responsible for processing and transforming the information captured during the self-attention mechanism. It's designed to enhance the model's ability to capture complex patterns and relationships within the input sequence. Let's break down what actually happens in this feed-forward layer. The input to this feed-forward layer is the output from the self-attention mechanism. After self-attention, you have a set of context-aware representations for each token in the input sequence. Each of these representations contains information about how the token relates to other tokens in the sequence. The first step in the feed-forward layer involves a linear transformation for each token's representation. This means that a learned weight matrix is applied to each representation, essentially reshaping and projecting it into a new space with potentially higher dimensions. This transformation is usually followed by an activation function, which introduces nonlinearity into the model. Another linear transformation is then applied. This transformation reshapes and projects the data further, often reducing the dimensionality. This step can be seen as compression or simplification of the information. The output of this second linear transformation is the final representation for each token. This representation is more abstract and compact than the input into the feed-forward layer, but it's designed to capture complex patterns and relationships learned during the self-attention step. In summary, the feed-forward layer acts as a set of neural network operations applied independently to each token's representation. It helps the transformer model capture and encode complex, nonlinear relationships between tokens in the input sequence. And because these operations are applied independently to each token, we can run them in parallel, really speeding up the process. Once we've done this, we can move on to the decoder block. The desired outputs we want our model to learn are fed into the decoder block. Think back to our example of French to English translation. The French words would be fed to the encoder block, and we would feed the English words to the decoder block. These outputs go through similar embedding transformations and get their positional encodings before being fed to the decoder block. However, we don't feed all output embeddings to the decoder block at once. They go through the masked multi-head attention layer. This is similar to the multi-head attention layer we saw in the encoder block, but we say it is masked because we need to hide some of the information on the outputs at this stage to make the model learn. We allow the model to see all the French input words, and when I say words, I really mean the intention vectors for these words. But the model will only see the English words that have come before the currently attended to word in the sentence. The model then has to learn what the correct next word would be, rather than just looking at the next word in the given outputs. We call this the masked multi-head attention because words later in the output text are masked or hidden from the model at this point. The multi-headed attention layer in the decoder block receives inputs from both the encoder block and the masked multi-head attention layer. In addition to self-attention, the decoder's multi-head attention also calculates attention scores between the current output token and the encoder outputs. This step helps the model determine which parts of the input sequence are relevant when generating the next token for the output. The encoder outputs are weighted by these attention scores to create a context vector. This context vector represents the relevant information from the input sequence that should be considered when generating the current output token. The feed-forward layer again just makes the output more digestible for the next step in the process. The linear layer is another feed-forward neural network used again to manipulate the output into a useful format. And the softmax layer transforms the output into a probability distribution. This probability distribution is then used to predict the next word in the output sequence. The whole process of this decoder block is repeated for each token in the output sequence, with the previously generated tokens being included as input for each subsequent step. So there you have it. You now have a good overview of how transformer models work, and we are ready to start using these models. ChatGPT has taken the field of NLP by storm with its amazing ability to generate content, code, have interesting conversations, and more. This is a state-of-the-art LLM developed by OpenAI. The GPT in ChatGPT stands for Generative Pre-trained Transformer. Let's break down what we mean by this. We say the model is generative because it can generate human-like text. Given a prompt or context, ChatGPT can continue the text in a coherent and contextually appropriate manner. This makes it really useful for tasks like text completion, dialogue generation, and content creation. The pre-trained aspect of GPT is crucial. Before fine-tuning for specific tasks, GPT undergoes a pre-training phase where it learns from massive amounts of text data. This process equips the model with a deep understanding of language, grammar, and a broad vocabulary. And of course, the transformer in the name is a reference to the transformer architecture we discussed in the last section of this course. There have been several iterations of different GPT models, so let's take a look at how this LLM has developed over the years. The development of ChatGPT represents a remarkable journey in the evolution of large language models, marked by a substantial increase in scale, performance, and applicability. Let's explore how we got here. The first GPT model, GPT-1, emerged in 2018 as a product of OpenAI's efforts to build a general-purpose text generation model. GPT-1 was trained on a modest dataset of 40 gigabytes of text from the internet, comprising of a wide variety of sources. It had 117 million parameters, making it one of the largest language models at the time. GPT-1 demonstrated its capabilities in text completion and generation tasks, but had limitations in understanding context and producing coherent long-form text. GPT-2 was released in 2019, and it was a watershed moment. It featured a significant increase in scale with a staggering 1.5 billion parameters. GPT-2, trained on more extensive and diverse data, demonstrated remarkable advancements in generating coherent and contextually relevant text. In 2020, we got to GPT-3. This had 175 billion parameters and was trained over a vast data set encompassing a significant proportion of the internet. Few-shot learning capabilities were also developed with this model. By 2022, we were at GPT 3.5, and now in 2023, we have GPT-4. GPT-4 is absolutely massive in scale at 1 trillion parameters and represents the pinnacle of OpenAI's research in large language models, at least at the time of creating this course. ChatGPT is a version of a GPT model specifically fine-tuned for conversational interactions. It's optimized to provide more natural and engaging responses in a chat or dialogue format. It's undergone additional fine-tuning to make it more suitable for chatbot and virtual assistant applications. Getting started with GPT models is pretty simple. OpenAI developed an API to allow you to easily interact with their models and start creating your own custom solutions. So to get started using the API, the first thing we're going to need to do is create an API key from the OpenAI website. So you'll want to go to platform.openai.com and either log into or create your account. Once you're in your account, this is the screen you'll see. You then want to go to your account settings on the top right of the screen and go to View API Keys. You'll see here I already have a few API keys that I've already created, but let's create a new one to show you how it's done. We'll click on Create New Secret Key. You then want to give this secret key a name. In this case, we'll just call it LLMs course. The secret key has now been generated for us, and we need to store this somewhere safe as we won't be able to view it again after this time. So make sure to copy this secret key somewhere safe. To use your API key in your code, you can either drop it straight into the code or you can add it into a config file. Some organizations might also have other ways of hiding these API keys from the code. This is important to make sure your secret key is kept a secret for only you. So I've created this file config.py, and then I'll create my API key and paste the secret key I got from the OpenAI website in this file. In our notebook, we can then import the OpenAI package and the config package. We create our API key and then we can reference our config file, so we do config.api key. We then want to initialize the OpenAI client, so we run openai.api key equals our API key. And that's it, our API key is now all set up for us to start playing with these models. Let's just make a quick note on pricing. So the different models that OpenAI makes available to us through this API come at different prices. Prices are set per 1,000 tokens. So have a look through this website if you're going to be using these models through the API, and just check the different prices of the different models available. Of course, the more expensive models are the more recent models. Let's now move to our next lesson where we can start interacting with this API. Remember how we talked about the G in GPT standing for generative, because it can generate human-like text? Well, we can test this out by creating a simple function for text generation using a GPT model via the API. So we'll create a function. We'll define our function generate text, and the input to this function will be our prompt. A prompt is essentially just the text you provide to the model. It can be a sentence for the model to complete, a question to answer, or a set of instructions to follow. And then within our function, we want to call the OpenAI.completion.create function. Within here, we specify the model we want to use. Here we'll be using DaVinci 2, which is one of the base models, but feel free to use whichever model you like here. The prompt for our model will be the prompt from the input of this function, and we also have a few arguments here, such as the maximum number of tokens and the temperature of our output. We'll come on to what these mean in our next lesson. We then want our generate text function to return the response.choices.text.strip to get our output in an appropriate format. Let's now create a prompt to pass to this function. Here we want to try sentence generation, so we'll give the model a prompt of a sentence to complete. Let's give it the phrase once upon a time and see what it comes out with. We then want to create our generated text, and then we can use our generate text function we created with our prompt as the input. We then want to print our prompt alongside the generated text. So we can see the model has given us an output here. Obviously, this isn't a perfect output, but in just a few lines of code, you've been able to interact with the GPT model directly in our notebook. I told you we'd come back to discuss the different options for the function we created. The max tokens and temperature arguments are things we can change in order to get a different outcome from our model. Max tokens refers to the number of tokens we want the model to return. If we set this to a higher number, we'll get back a longer output. Let's experiment with some different values for these arguments. We'll take our generate text function from above, and instead of setting the max tokens within the function itself, we can create it as one of the arguments for our function. We can then create our generated text, but instead of just providing the prompt to our generate text function, we'll provide the prompt and the number of max tokens. Here we'll set it to 5. We've been given once upon a time, this spring, every. Let's now change this to a larger number and see if we can get a full sentence. We'll change the number of max tokens to 20 and print out our generated text. So you can see here the output that's been given is much longer. And you can play around with the number of max tokens depending on what your use case is. You can even just make it a really large number to allow the model to give whatever output that it feels would be relevant. Let's now look at the temperature argument. The temperature controls the randomness of the response, with 0 being less random and 1 being most random. So let's adapt our function, again taking the temperature out of being hard-coded within the function itself, instead an argument we can pass to our function. We'll then generate our text, so we'll give it the prompt, the max number of tokens is 20, and the temperature of 0. Let's compare this to where we give it the same prompt, the same number of max tokens, and a temperature of 1. So you can see with a temperature of 0, the response is quite kind of simple, it's not particularly random, it makes sense. Where the temperature is 1, it will be more random, but because we've limited the number of tokens, it's quite hard to see that. So let's up our number of max tokens to 50. So when we allow the max tokens as 50 and the temperature of 0, we get the following response. Once upon a time, there was a little girl who was born with very special gift. She could see things that others could not. She could see the future and she could see the past. She could see the present and she could see the future. Let's compare this now to where the max tokens is again 50 and the temperature is 1. Here we get the response, once upon a time, I was told everything. I'm guessing this might be in reference to how it's always been a strange position to be in because he doesn't really give much back when anyone does anything for him, but we don't get a perfect view of those. So you can see here the response is a little bit more random, it doesn't make as much sense, it's not quite as clear. So this temperature argument is really interesting to play around with and see what kind of different responses you can get. There are other customization options available, so do check out the documentation. You can also experiment with these on the OpenAI API Playground, where you can test out different models and settings. Next, we're going to learn how to create a function that can be given a large chunk of text and summarize it by picking out the keywords. Because the model is able to understand language, it is then able to pick out the most important words and phrases for us. We create our function and provide messages to the model with instructions and examples of how we want the model to respond. There are 3 roles that can be used for messages. The first messages are system messages. These messages provide instructions to the model on what you want it to do and how it should respond and behave. The second type of message is a user message. This is an example of a user input. So in this case, the user input would be the block of text we want to summarize. The third type of message is an assistant message. This is an example of the correct output to the user input. So here we have keywords that have been pulled out from the block of text provided by the user. These assistant messages serve as an example of how the model should respond. So you can see in the code here we've created a function which we're calling text summarizer. And this function takes our prompt as an input. We use the openai.chatCompletion.create function and specify our model and our messages. This is where we include the system, user, and assistant messages. Our system message we've set to be the following. You will be provided with a block of text, and your task is to extract a list of keywords from it. We then provide an example user message. Here it's a large piece of text about a flying saucer. The next message is the assistant message. So this will be how we want the model to respond in response to the user message above. So you can see here this assistant message has picked out keywords from the text in the user message, such as flying saucer, guest house, etc. We then give another example in these messages. So we provide another user message, which is another large piece of text about Sri Lanka, and an assistant message which pulls out the keywords from this text. Here we're just showing the model how we want it to behave in response to certain inputs. The final message we give will be where we provide our prompt. So we set it as a user message, and then the content of this message will be the prompt that we provide. We set the number of temperature and the max tokens and return the model's response. Let's now give a new prompt to this function. We can print this prompt out for you to read. We'll then create our generated text and reference our text summarizer function and provide it the prompt. When we print this generated text out, we can see that it's the keywords from our piece of text above. In this lesson, we've seen how we're able to provide messages to our model in order to get it to work with different tasks. Not only can we specify a system message to create a keyword text summarizer, we can also use it to create so many different types of outputs. Let's create a function for a chatbot with a twist. Let's create a chatbot that gives a poetic output. We'll define our function as poetic chatbot, and again our input to this function will be our prompt. We again then use the OpenAI.chatCompletion.create function. We specify the model we want to use, and in this case, we'll be using GPT 3.5. We then specify the messages we want to provide to this model that will dictate how it responds and behaves. We'll first create our system message. This provides instructions on the overall purpose of our chatbot. So the content of this system message will be the instruction, "You are a poetic chatbot." We want to include some examples of how the model should respond to different types of prompts. So let's do that with some user and assistant messages. The first user message will be a question, "When was Google founded?" We then want to give the model an example of the response to this. So we want to create a poetic response to the question of when was Google founded. Thankfully, I've already created these example outputs for us. So we can see in our assistant message the example response does give the answer, the correct answer, of when Google was founded, but it does it in a poetic manner. This is exactly how we want our chatbot to behave. Let's give it another example. We'll give a user message with the content, "Which country has the youngest president?" And again, we then need to assume the assistant role to provide the desired response. Again, I've already created this for us, so we can copy this response across. We then specify the final message, which will be from the user, and it will just be the prompt that's provided to our function. We also set the temperature as 1 to allow for some randomness in our poetic responses. And we set our maximum tokens to 256. So now we've created our poetic chatbot function, selected the model we want to use, and provided some instructions and examples of how we expect this model to behave. We can now test this out. So let's give a prompt. We'll give the prompt, "When was cheese first made?" We then want to create our generated text and run our function poetic chatbot with our prompt. Let's then print out this generated text and see the poetic response we received. Perfect, so we can see our model has behaved exactly as we would expect. It's given us a nice poetic response of when cheese was first made. So in this lesson, we've managed to create a chatbot and we've given it a personality. It'll give nice poetic responses to different prompts made by the user. In the last lesson, we were able to code a poetic chatbot. However, the model will only be able to answer questions based on the general knowledge it has from the data it's been trained on. Let's see what happens when we ask a more specific question to this model. So we can create a new prompt that asks, what is the next course to be uploaded on the 365 Data Science platform? You can see that the model has given a response, but there's no actual answer in this response. The model isn't able to tell us which course will be uploaded next onto the 365 Data Science platform because it just doesn't have this data available. GPT models have been trained on a lot of data, but this data only goes as far as 2021, so they might not have the most up-to-date information. But there is a solution. Using LangChain, we are able to import our own data and have this read by our language models. Our language models can then reference this when creating a response using the LangChain framework. So let's have a look at what LangChain is and what it can be used for. LangChain is an open source framework that allows developers to combine large language models with external sources of computation and data. Its popularity has soared in 2023 as large language models have evolved and developers are looking for ways to integrate them easily into their applications. LangChain allows you to build end-to-end applications powered by language models. There are going to be use cases where your language model needs to be able to access and understand data related to your business area or some other area of knowledge that it doesn't have currently. Say, for example, you want to use ChatGPT to help you study. We know that this model has some general knowledge, but you can improve on this by giving the language model access to the entire course syllabus you want to learn. You'd then be able to discuss the syllabus with the large language model and learn much more effectively. We can also use an example with business-specific data. Say you want to create a chatbot for your business to assist customers on your website. Unless you're working for a large, well-known corporation, the language model likely won't be aware of your company, or the information could be out of date or need some further context. You can provide your language model with all the information it needs to know about your company so it can effectively help your customers. So, how is LangChain able to ingest our data and have it read by our large language model? The first step is to load in our custom data and break it into chunks, as language models generally have a limit to the amount of text they can deal with at once. We then create numerical embeddings for each chunk of text. This helps us find similar chunks of text within the data, which is useful when our language models are trying to find which parts of text are important when answering a given question. Finally, these embeddings are loaded into a vector store. Vector stores help us find the most similar chunks in the embedding space quickly and efficiently. LangChain can also help you with follow-up actions, such as sending emails based on the response given by your language model. There is so much functionality with this framework, and I encourage you to check out the documentation. For this course, we'll just be focusing on how we can integrate our own data with our large language model. If this is something you're interested in learning more about, check out the dedicated LangChain course on 365 data science.
The first thing we need to do to work with LangChain is load our custom data and create a LangChain document object. LangChain has a number of different data loaders for different types of inputs. We can use a data loader to read in information from text files, PDFs, HTML, and so much more. There's a great community around LangChain working to build data loaders for a whole range of different inputs. For our use case, we want to read in the latest information from the 365 Data Science website. So we'll want to use a web-based loader to read in information from a website. So we'll specify the URL of our website. In our case, it's 365datascience.com/upcoming courses. We can then use the web-based loader from LangChain to load the information from this web page. We now need to create a LangChain document object. We can create our raw documents and then use loader.load. This will load the text from our URL and convert it into a LangChain document. The next step is to take our data and chunk it up into small pieces. This is necessary in order to make sure we only pass the smallest, most relevant pieces of text to the language model. So we'll create our text splitter and then use the recursive character text splitter. We can then create our documents. So we'll use textsplitter.splitDocuments over our raw documents. This will take the text from our URL and break it up into small pieces for us. Once we have these smaller chunks, we can create our embeddings for each piece of text and store them in a vector store. To create our embeddings, we'll use OpenAI embeddings, and then we need to specify our API key. We can then create our vector store. We'll use from documents, and then we want to store our documents and our embeddings in the vector store. We can now create a memory object, which is necessary to track the inputs and outputs and for the model to hold a conversation. So to create our memory, we use conversation buffer memory. We'll give the memory keys as the chat history, and specify return messages equals true. We can now initialize the conversational retrieval chain. This chain first combines the chat history and the question asked to the model into a standalone question. It then looks up the relevant documents from the retriever and finally passes those documents and the question to a question answering chain to return the correct response. So let's set up our chain. We'll use conversational retrieval chain.from LLM. We then provide our OpenAI API key. And specify the temperature of the response. If you remember, the temperature just controls how random the response is. We then pass our vector store as retriever and pass our memory. And that's it, we're now ready to ask our model questions based on this text we provided from the 365 Data Science website. So we can ask our model again, what is the next course to be uploaded? We then want our result, so we'll use our QA chain and we'll pass our query to our chain. To get our results, we just need to access the answer from the results. And you can see here the model is now able to answer this question. It's correctly identified the next course to be uploaded at the time of creating this course. It's as easy as that to work with LangChain to bring in your own custom data and start to create chains that will power your own large language model applications.
Welcome back, and I hope you enjoyed getting started with coding your first large language model solutions using GPT models. However, GPT models aren't the only large language models out there. There are lots of different types of language models we may want to use depending on our use case. We'll cover more on some of the other models later, but for now, let's just look at how we can start to interact with these other LLMs. Whilst GPT models can be accessed by OpenAI's API, there is another very popular way to interact with other models developed by Hugging Face. Hugging Face, named after the popular emoji, was founded in 2016 and is an open source organization that focuses on natural language processing and deep learning. They provide various tools and libraries to make it easier for researchers and developers to work with state-of-the-art NLP models, including pre-trained models and tools for training your own models. The most well-known package from Hugging Face is the Transformers library, which is widely used for working with large language models in Python. The Transformers package provides a wide range of pre-trained NLP models, including BERT, GPT-2, Roberta, and many others. It offers a simple API for loading and using pre-trained models. You can easily load a model, tokenize text, and make predictions or generate text within just a few lines of code. You can fine-tune pre-trained models on your own data for specific tasks like sentiment analysis, named entity recognition, or text classification. Hugging Face provides tools and examples to help you with this process. Hugging Face has a vibrant community of developers and researchers contributing to their projects. They offer extensive documentation and tutorials on how to get started with different projects and models. The Transformers library also seamlessly integrates with popular deep learning frameworks like PyTorch and TensorFlow, making it accessible to a wide range of developers. The Transformers package makes working with large language models simple. In our next lessons, we'll get familiar with working with the Transformers package before moving on to our larger practicals in sections 5 and 6 of this course. We can easily get started using the models available to us through the Transformers package by using the Transformers pipeline. This pipeline makes it easy for us to connect to a language model, give an input, and receive our output, all in just a few lines of code. So the first thing we want to do is import the packages. So from Transformers, import pipeline. The first example we're going to look at is a pipeline for sentiment analysis. To do this, we create our sentiment classifier. Then we can use the pipeline function. Within the pipeline function, we provide the type of pipeline we want to run. In this case, it's sentiment analysis. We can then run our sentiment classifier over a new piece of text. So let's take the phrase, "I'm so excited to be learning about large language models." We can see that just this one line of code has given us the output for the sentiment of this piece of text. It's given us the label as positive and the associated confidence score. You might also notice that when we ran the pipeline function, we were given a message that said that no model was supplied, so this pipeline has defaulted to the default model used for this pipeline. For each pipeline, there is a default model associated, but we can also specify which specific model we want to use. Let's test this out and create a new pipeline for named entity recognition. We again use the pipeline function, specify the pipeline as NER for named entity recognition, and we can select the specific model we want to use. Let's now run this pipeline over a new piece of text. We'll take the phrase, "Her name is Anna, and she works in New York City for Morgan Stanley." And we can see our output here. Our named entity recognition pipeline has correctly identified the named entities within this piece of text. The pipeline is able to abstract away a lot of the tasks for us, such as pre-processing our text input and providing an interpretable output. The Hugging Face Models Hub has information on all the different models we can use. You can search for specific models, or you can filter by specific tasks. Let's try some zero-shot classification. Remember what we mean by zero-shot learning from earlier in the course? It's where the model is able to perform a task without any additional training. The general knowledge it has learned is enough for it to complete the task. Let's see if a language model can classify some text without being explicitly trained on the classifications. We create our zero-shot classifier, we create our pipeline, and we want to use the pipeline zero-shot classification, and then we want to use the Facebook model we found on the Models Hub. If it's your first time using this specific model, the pipeline will download this model for you, but because I've used it already, we don't need to do that step. For zero-shot classification, we need our sequence that we want to classify, and we need our candidate labels. These are the labels that we're going to classify our sentence into. So we'll take the phrase, "One day I will see the world," and ask our language model to classify this as either travel, cooking, or dancing. We can then run our zero-shot classifier over our sequence to classify and the candidate labels. You can see we've been given three objects in our output: the sequence, the labels, and the scores for each label. Our model has identified that the phrase "one day I will see the world" is most likely going to be about travel. So we've done no explicit extra training for this model, it's just able to use what it knows about the world to do some classifications for us. You can see just how easy it is to start working with language models using the transformer pipeline. There are lots of different pipelines we can use for different types of tasks, so do spend some time looking over the documentation for more information on the pipelines available. Using the transformer pipeline makes it quick and easy to start working with language models. Let's now do a deeper dive into what this pipeline is actually doing and try to understand the steps a little better. The first step of the pipeline is to tokenize our input text. So to do this, we want to import the auto tokenizer from the transformers package. Next, we need to specify the model we want to use. This will ensure the tokenizer tokenizes in a way that is suitable for our intended model. Different models will have slightly different ways of creating their tokenization. So we're going to be specifying our model, and we'll be using BERT-based uncased. We'll cover more of this model in detail in the next section of this course. We then want to call the pre-trained tokenizer for this model. So we create our tokenizer and then use autotokenizer.fromPretrained and our model. Let's see how this tokenizer works by running it over a sentence. We'll take again the sentence, "I'm so excited to be learning about large language models." We then want to call the tokenizer on this sentence. So we'll create our input IDs and then use the tokenizer over our sentence. Let's now print out these input IDs and inspect them. We can see three things have been generated here: input IDs, token type IDs, and an attention mask. The token type IDs are used for some models where we want to distinguish one sentence from another, or an input sequence and its relative classification. We can use numbers to distinguish one sentence from another, where tokens with the type ID of 0 would belong to the first sentence, and token types with ID of 1 would be the second sentence or the classification. We'll come on to this more when we look at specific models in more detail later in this course. The attention mask essentially tells the model which words are important to pay attention to. Again, we'll cover this later in the course. For now, I just want to focus on the input IDs. The first thing our tokenizer does is break out our sentence into tokens. We can call this step directly using the following. So we want to create our tokens, and then we can use tokenizer.tokenize over our sentence. We can then print these tokens out and see that this sentence has been converted into tokens for us. These tokens are then converted into a numerical value based on a predefined vocabulary specific to the model. Let's have a look at these. We'll create our token IDs and then use tokenizer.convert tokens to IDs over our tokens. Let's then print out these token IDs. We can see that for each token, this has been converted into a numerical representation. We can decode these token IDs back into tokens to check this. So let's create some decoded IDs and use tokenizer.decode over the token IDs. When we print these decoded IDs out, you can see that we're back to our original sentence. Let's look again at the token IDs. You'll notice that the token IDs are present in the input IDs we were given when we ran the full tokenizer. However, if you look at the input IDs again, you'll see there are some additional numbers that haven't been printed when we just look at the token IDs. So, what are these? We can decode them to check their meaning. Let's run tokenizer.decode 101. This has printed out a token of CLS. Let's now run tokenizer.decode 102. And we can see we have another special token here, which is SEP. These are special tokens added by our tokenizer and our next lesson will cover exactly what each of these special tokens mean. The tokenization process does change depending on what model we want to use, as each model has its own unique requirements for the input data in terms of its format, tokenization strategy, and use of special tokens. Let's look at how XLNet, another large language model, differs in its tokenization. So let's specify our model as XLNet base cased, and we'll create this as our model 2. We then create our tokenizer 2 and use autotokenizer.fromPretrained model 2. This will load up the tokenizer for the XLNet base cased model. Let's now call this tokenizer on our sentence. Again, we've been given a list of input IDs, token type IDs, and an attention mask. But you can start to see some differences here. The numerical values given to each token are different, and the token type IDs now contain more than just zeros. Let's first look at how this model tokenizes differently to the BERT model above. We'll run tokenizer2.tokenize over our sentence. When we print this out, you can see that even just the way that this model has tokenized the text looks very different to what we saw above. We can then convert these tokens to their ID values. So we'll use tokenizer2.convert tokens to IDs over our tokens. And when we print this out, you can see that the numbers given to each of the tokens differs again from the BERT model above. You might also notice that where the BERT model started the input IDs with this CLS special token, XLNet doesn't begin the input IDs with this special token at all. Instead, we see 2 extra numbers at the end of our input IDs. Let's decode them and see what they mean. We'll run tokenizer2.decode, and we want to decode the number 4. We can see that again we've been given the SEP special token, just in a slightly different format. And if we run tokenizer2.decode over the number 3, we can see again this CLS token, again just in a different format. But what are these special tokens, and why are they added to our input sequence? Let's move to our next lesson to discuss this in more detail. Special tokens are a fundamental concept in the world of large language models. Special tokens are specific placeholders or markers that help the model perform various tasks and handle specific tasks or instructions within the text. They are like signposts or markers that help the model understand the structure and context of the input text and guide its behavior in various tasks. This ensures the output of the tokenization is in a format that your model of choice will understand. Let's talk through some key types of special tokens and their purposes. The first are the CLS and SEP tags. The CLS tag is a classification tag, and SEP stands for separator. These special tokens are commonly used in tasks like text classification and sentence pair classification. In a typical scenario, you might have a sentence or text passage and you want the model to classify it into a category or determine its relationship with another sentence. The CLS token is usually placed at the beginning of the input and the SEP token is used to separate different segments of text. The mask token is used in tasks related to masked language modeling or text generation with a blank to fill in. For example, you might provide a sentence with a word replaced by mask, and the model's task is to predict the missing word. This is commonly used in tasks like text completion. Depending on the specific task you want the model to perform, you may introduce custom special tokens. For instance, if you're using the model for translation, you might have a special token like source and target to indicate the source and target languages respectively. These tokens help guide the model's behavior during the translation. When you feed multiple sentences of varying lengths into the model, you may need special tokens for padding, which is where we add extra tokens to make sure all the inputs are the same length. Or we might want to use truncation, which is where we shorten longer inputs to a specific length. These tokens ensure that the inputs are consistent and align with the model's architecture. Each model will have different requirements and uses when it comes to special tokens. That's why it's important that we specify which model we are going to use when we're working with a tokenizer, so it can ensure that it processes the text in the correct format for that model. Hugging Face makes it simple for us to work with PyTorch and TensorFlow workflows. This is useful when integrating large language models into existing machine learning solutions you may already have. And it allows us a method for fine-tuning any models. Here we will introduce how to start working with Hugging Face and PyTorch. If you'd like to work with TensorFlow, the code is very much the same. You'll just want to use the TensorFlow specific classes. Usually these are just the same class names with TF added to the name. So from transformers we want to import the pipeline, auto tokenizer and the auto model for sequence classification. We'll also import the torch package. We already have our sentence and our input IDs from earlier, so let's print these out and refresh our memory. To get our output in the correct format for PyTorch, we need to specify we want the input embeddings to be returned as tensors. Let's update our tokenizer for this. So we'll create our tokenizer and then use autotokenizer.fromPretrained and specify the model we're going to use. This is a fine-tuned model from the Hugging Face models page that can classify text as positive or negative. We'll then create input IDs PT, and we'll use our tokenizer over our sentence, and we want to specify return tensors equals PT. This will return our input IDs as a PyTorch tensor. We can print these out to check it has worked. And yes, you can see the output is the same, but it's now formatted within a PyTorch tensor. Let's now create our model. So we'll use auto model for sequence classification, .from pretrained, and again we'll specify our model. We're now ready to use PyTorch on our inputs to do some inference of our own. So with torch.nograd, we obtain the logits by running the model over our input IDs PT. We then want to return the label of positive or negative for our input text. So we'll get our predicted class ID, and to use this we'll take argmax.item, and then we take our model.config.id to label of this predicted class ID. This is essentially looking at the dictionary mapping of the numeric scores to the classification labels. So it's looking to see whether it should return positive or negative. And once this is printed, we can see it's been returned as positive. So let's see what our sentence was. I'm so excited to be learning about large language models. So yes, a positive classification seems appropriate here. These steps are essentially what is happening under the hood when we use the pipeline function. But being able to work with PyTorch, TensorFlow, and Hugging Face together in this way means we have so many options to customize our models and understand what is happening when we use more abstract methods such as the pipeline. Let's say you've been working on a model and now you want to save it for future use so you don't have to retrain it with your data each time. Hugging Face allows us to do this easily. We first want to set our model directory where we want to save our models. So we'll create a folder called MySavedModels. We can then save our model and tokenizer by using the save pre-train method. We just need to provide the model directory of where we want to save the tokenizer and where to save our model. We can then reload our models using from pre-trained. So if we want to load up the tokenizer we just saved, we can load up my tokenizer and then use autotokenizer.fromPretrained and specify the model directory where the tokenizer is saved. It's the same with our model, so we can load up my model and then use automodel for sequence classification.fromPretrained and again specifying the model directory where our model is saved. So far in this course, we've covered what large language models are, what they can do, and how they work. We've discussed the transformer architecture and started to experiment with creating our own large language model solutions using GPT models via the OpenAI API. GPT models are fantastic at being able to generate text in response to a prompt. However, there are other types of NLP tasks where other large language models excel. In the next two sections of the course, we'll be looking at two models in particular, BERT and XLNet. You might remember these names from when we covered different methods of tokenization through the Hugging Face package. We'll look at the architecture of these models, how they differ from one another, and work through a practical exercise using these new models. So let's get started by introducing the BERT model. BERT stands for Bidirectional Encoder Representations from Transformers. Similar to GPT models, BERT is a pre-trained model that uses the transformer architecture to process and understand natural language. It was developed by Google in 2018 and has quickly become a go-to model for developers working in the field of NLP. Like GPT models, BERT was trained on a massive amount of text data, including the books corpus dataset, which contains over 11,000 books, as well as a large text corpus from Wikipedia. BERT was originally implemented in the English language in two model sizes. The first being BERT Base, which has 110 million parameters, and BERT Large, which reaches 340 million parameters. What makes BERT unique and powerful is its bidirectional context understanding. GPT models are autoregressive, meaning they generate text by predicting the next word in a sentence based on the preceding words. On the other hand, BERT uses a pre-training process where it learns to predict missing words in a sentence by considering the entire context, both words to the left and right of the target word. This bidirectional approach helps BERT to grasp the nuances of language and understand the meaning of the words in a more contextually relevant way. Because of the differences in how these models learn to understand context and meaning, they excel at different types of tasks. GPT models do exceptionally well when used for conversational AI and chatbots, whereas BERT is primarily used for tasks such as sentiment analysis, question answering, and named entity recognition. Whilst BERT is based on the transformer architecture we discussed earlier in the course, it introduces some modifications and has a specific pre-training methodology to make it effective for a wide range of NLP tasks. Let's discuss BERT's architecture in more detail. Think back to our lessons on the transformer architecture. You'll remember we had an encoder block and a decoder block that process the inputs and outputs when training our model. A main difference in BERT's architecture is that it only employs the encoder part of the transformer. This is because it's primarily used for pre-training on large text corpora, rather than from sequence-to-sequence tasks. Other models based on the transformer architecture, like the GPT series of models, are designed with decoders for tasks that involve text generation or sequence-to-sequence tasks. BERT, in contrast, is primarily used for encoding and understanding text, and it's proven highly effective in this role. The BERT architecture consists of a stack of identical encoder layers. The number of layers depends on the specific variant of BERT. BERT Base has 12 encoder layers, and BERT Large has 24 layers. The deeper architecture of BERT Large captures more complex patterns and relationships between our tokens. BERT's input is tokenized text, and each token is represented as an embedding vector. For each of the input tokens, BERT converts this into 3 types of embeddings. The first is token embeddings. These are the standard word embeddings for each token to convert them into a meaningful numerical representation. The special tokens, CLS and SEP, are also added at the beginning and end of sentences. The second type of embeddings are segment embeddings. BERT can accept pairs of sequences or text segments as an input. Segment embeddings help the model distinguish between different segments. And finally, BERT takes the positional embeddings. These embeddings encode the position of each token in the input sequence. BERT's pre-training objective is focused on understanding and representing language bidirectionally. The model is pre-trained using 2 primary objectives. The first is masked language modeling. In this objective, a fraction of the tokens in each input sequence are randomly masked, and the model is trained to predict the masked word based on the context provided by the surrounding tokens. The goal of this model training is to try and figure out which words fill in the masked tokens. This forces the model to learn bidirectional context, as it is allowed to see all unmasked words from either side of the masked token. The second is next sentence prediction. BERT is trained to predict whether 2 sentences in a pair are consecutive in the original text or not. During this training phase, 50% of the input sentences are paired with their next sentence in the original input text. The other 50% are paired with a random sentence from the text. The goal is for BERT to accurately predict whether the 2 sentences are paired with their next sentence or not. This objective helps the model understand relationships between sentences. These pre-training tasks do not involve generating text, so a decoder is unnecessary for the initial stage of pre-training. The lack of a decoder makes BERT more adaptable for a wide range of downstream NLP tasks such as text classification, question answering, named entity recognition, and more. After pre-training, BERT can be fine-tuned for these specific tasks by adding a task-specific layer on top of the pre-trained encoder. The new output layer we create formats the output to be relevant for the task. So for example, if we wanted to do sentiment analysis, the final output layer would transform our output into sentiment labels. This flexibility and adaptability are key advantages of working with BERT. To get started using the BERT model, we'll want to import the relevant functions from the transformers package. So we'll do from transformers, import BERT for question answering, and we'll import the BERT tokenizer. We'll also want to import the torch package for later on. The next thing is to load the model and the tokenizer for the model we're interested in. So we'll specify our model name. In this case, we're using BERT large uncased, and we're using a fine-tuned version based on the squad dataset for question answering. The uncased part just means it treats uppercase and lowercase words the same. We can then load our model, so BERT for question answering .from pre-trained, and we reference our model name. Same with the tokenizer. We'll load BERT tokenizer from pre-trained and specify again the model we want to use the tokenizer for. Let's now move on to create some embeddings using this tokenizer. Let's look at BERT's architecture again, this time using an example. We'll provide a question to BERT along with the text containing the response. We can then walk through the steps BERT takes to find the answer to this question. So we have the question, when was the first DVD released? We then have a piece of text containing the answer, which we'll put in our answer document. The first step is to create the embeddings for our question and answer. So we'll create the encodings and then use tokenizer.encode+. We'll give it the question text and the answer document. Let's now print these encodings to see what they look like. We have our token embeddings with the special tokens added to our input IDs, and our token type IDs are used to distinguish the tokens related to our question versus the tokens related to the text containing the answer. We also have an attention mask, but we don't need this at this time. So let's take our inputs, our sentence embeddings, and our tokens. For our inputs, we can take these from encoding the input IDs. Our sentence embeddings come from the token type IDs. And for our tokens, we use tokenizer.convert IDs to tokens over our inputs. We can also check that the special tokens have been added. So you can see in the text we have the special tokens 101 and 102. Let's decode these just to check they are the special tokens we're expecting. So we'll decode 101, and yes, that's the CLS token, and for decoding 102, we can see this is the SEP token. We can then pass these embeddings to our model. So we'll create our output and then run model. And for the input IDs, we want to format these into a tensor, so we use torch.tensor over our inputs. The same for the token type IDs, we convert these to a tensor and then pass them to the model. BERT calculates where the answer to our question is within our text by creating start vectors and end vectors. It then takes these start and end vectors and takes a dot product between these and the final embedding for each token. This output then runs through a softmax function to give a probability score. The word with the highest probability is considered the correct start or end token respectively. So we want to get the start and end token positions from our output. So we'll create our start index and then use torch.argmax. And then from the output we can take the start logits. The same for our end index, we can take the output.end logits and again run this through torch.argmax. Let's then print the start index and end index so we can see which positions are the start token and the end token. So we'll see the answer in our text starts at token 20 and will end at token 23. So let's use this to pull the correct tokens and get our response. We want to create our answer, and then we'll join together the tokens between the start index and the end index position plus 1. We can then print this out and we can see our answer is March 24, 1997. If you remember, we fed the model the question, when was the first DVD released? And our answer document contained the answer March 24, 1997. So our BERT model has worked here, it's found the correct response in our answer document. Let's visualize the different tokens and their probability of being selected as the start or end token. We're going to create some charts, so we're going to want to import matplotlib as PLT and import Seaborn as SNS. We then want to find the scores for each token, pull them out of PyTorch tensors and convert them to NumPy arrays. So for our start scores, we want to take the outputs, the start logits, detach them, run NumPy and then flatten them to convert these into a NumPy array. The same for our end scores. We'll be using the tokens as x-axis labels. In order to do that, they all need to be unique. So we'll add the token index to the end of each one of them. So we want our token labels as a list, and then for I token and enumerate tokens, we take the token labels and append the index to the end of them. This will make each token unique for our axis labels. Next, let's create a bar plot showing the start word score for all of the tokens. So now start bar plot, and X will be our token labels, and Y will be our start scores. We then want to turn the X-axis labels vertical, so we want to set X tick labels and set the rotation to 90. We'll also turn on the vertical grid to help align the words to their scores. Now we have this chart, you can see the probability of each word being selected as the start token. We can see the model considered a few different options, but in the end it was correct at identifying March as the correct start word for the response. We can then do the same for our end tokens, so we can see the different options the model considered of where to end the response. And again, we can see it considered a few options, but it was pretty clear that it knew that 1997 was the end of the answer to the question we were asking. You should hopefully now have a better understanding of how the BERT model ingests and processes data. Let's now imagine a scenario. You're working for a car company, Sunset Motors, who wants to add a chatbot to their website to answer some of customers' most frequently asked questions. They have asked you to create a prototype of this FAQ chatbot. So to do this, the first thing we're going to need is some data about the company. Here we have our Sunset Motors context, and if we print this out, you can see it's some really important information about the business, such as when it opened, where it is, and what kind of cars it sells. We can then create a function which we'll call FAQBot, where we can feed it a question. The model will then look at the context we've provided and provide the correct response. This will be an excellent prototype for our FAQ chatbot for the website. So the first thing we want to do is define the function FAQBot, and the input to this function will be the question we want to answer. We'll then provide our context, so this is the Sunset Motors context. We'll then need to encode the question and the context. So we'll take our input IDs from tokenizer.encode, and we'll take our tokens, where we convert these IDs back to their token values. We then want to create our segment embeddings. So the first thing we need to do is find the separator token within our list of input IDs. So from the input IDs.index, we're looking for the tokenizer and the separation token ID. Once we've got this, we can use this to compute the number of tokens in segment A and the number of tokens in segment B. So for the number in segment A, we take the separation ID plus 1. And for segment B, we take the length of the input IDs and take away the number of segments in segment A that we just calculated. We can then create our list of segment IDs, so we'll do zeros repeated for each token needed in segment 1, and ones for each token in segment 2. We can then feed all this into our model, so we'll take our output and then run model, and we'll convert our input IDs into a torch tensor and our segment IDs, which will also convert into a torch tensor. We then need to create the answer start and answer end positions. So from the outputs, we convert these into torch.argmax, and then we can find our answer start and where our answer should end. We then tell our function that if the answer end is after the answer start, so essentially is the start of the response going to be tokens ahead of the end of the response, then we can print our answer, and our answer is the tokens between the start position and the end position plus 1. If this is not the case, and it looks like the end token is going to come before the start token, then we know something's gone wrong here, so we can print a message instead of providing an answer. So we'll print, "I'm unable to find the answer to this question. Can you please ask me another question?" In our function, we also want to tidy up any responses we might get, because sometimes hash values are left in just because of how the data is tokenized. So we want to create our corrected answer. And then for each word in answer.split, so we're taking each word in our answer. And then if the word contains these hash values, we can just edit this and correct the answer by removing these hash values. We then return this corrected answer. So we've now got our FAQbot function. Let's ask it some questions and test its knowledge. So we can ask, where is the dealership located? And our model has returned the answer Crestwood. Let's try with what make of cars are available. And again, we can see we've got the correct response of Ford, Toyota, Honda, Chevrolet, and BMW. Our model is able to reference the context we gave it to answer these questions. Let's try one more. So how large is the dealership? And again, the model's got this right at 10 acres. You've successfully created a prototype FAQ chatbot. You can imagine just how powerful this could be if you combined it with the LangChain framework to bring in even more custom data. You can find more information about this in the dedicated LangChain course. If you do some further reading into the BERT model, or you look up BERT models on the Hugging Face models page, you'll eventually come across some variations on the BERT model. These are Roberta and DistilBERT. BERT, Roberta, and DistilBERT are all variations of the original BERT model. each with its own unique characteristics and modifications. Let's go through some of the key differences between these models. RoBERTa, which stands for a Robustly Optimized BERT Pre-Training Approach, is a modification and optimization of the BERT model. It employs a larger batch size, longer training sequences, and removes the next section prediction task during pre-training. RoBERTa also uses dynamic masking, where the masking pattern is changed for each batch. The result is a model that achieves better performance on various downstream NLP tasks compared to the original BERT. RoBERTa is known for its robustness and is generally considered an improvement over BERT. Distilled BERT is a smaller and more lightweight version of BERT designed for efficiency and faster inference. It is distilled from the BERT model, where it is trained to mimic the behavior of the larger BERT model while having fewer parameters. It has 40% less parameters than the BERT-based model. It runs 60% faster whilst preserving over 95% of BERT's performance. Distilled BERT retains much of BERT's performance on various NLP tasks, but with significantly fewer parameters, making it more suitable for resource-constrained environments. Let's look at how we could work with RoBERTa and distilled BERT models through the Transformers package. So for RoBERTa, from the Transformers package, we can import a RoBERTa tokenizer and the RoBERTa model. You can specify your model name to be RoBERTa base, and then using the from pre-trained functions we're familiar with, we can load up the RoBERTa tokenizer and the RoBERTa model. There are other functions available for this model for specific types of tasks. There are also lots of fine-tuned models you can look through on the Hugging Face models page. And for distilled BERT, we can use the distilled BERT tokenizer and the distilled BERT model from the Transformers package. So feel free to go back to some of our earlier code and experiment with these RoBERTa and distilled BERT models, switching out our BERT model for one of these variations. So far in the course, you've added working with 2 different types of language models to your NLP toolkit. There are many different language models out there, and so this section of the course, I want to introduce you to another model called XLNet. XLNet is a large language model developed by Google AI in collaboration with universities and other institutions in 2019. It comes in 2 sizes, XLNet Base, which contains 110 million parameters, and XLNet Large, with 340 million parameters. Unlike BERT, which consists of encoder layers stacked on top of one another, XLNet is a decoder-only architecture. We stack several layers of decoders to create the XLNet architecture, 12 layers for XLNet Base, and 24 layers for XLNet Large. The key innovation of XLNet is that it overcomes some of the limitations of previous models in terms of how it processes text to get a deeper understanding of context. One of the fundamental differences between XLNet and earlier models like BERT is the way they handle context. In traditional autoregressive language models like GPT, the training objective is to predict the next word in a sequence given the previous words, typically moving from left to right. In contrast, BERT uses a masked language model objective where some words in a sentence are randomly masked, and the model's task is to predict the masked words based on the surrounding context. XLNet takes a different approach. During pre-training, XLNet can consider all words in the context, not just the words to the left and right of the target word. XLNet samples different permutations of the input data. This means that it considers different ways to mask out and predict words in the sequence. By doing this, it learns to predict the probability of each word given the entire context it has learned from the whole text. This leads to improved contextual understanding. The key advantage of permutation-based training in XLNet is that it can capture bidirectional context effectively. In each training instance, it's as if the model is trying to predict each word in the sequence by considering all the other words around it, not just those to the left and the right. This helps the model understand the relationships between words in a more comprehensive manner. XLNet makes an independence assumption when computing the probability of a word. It assumes that the probability of a word being generated is conditionally independent on the other words in the sequence, given the entire context. To put it simply, this just means that the model doesn't rely on the order of words to predict a particular word, but it considers the entire context, so it looks at all the words in the text rather than just the order and the words either side of the current token. The permutation-based training in XLNet overcomes the limitations of a purely autoregressive model such as GPT. While autoregressive models generate words sequentially, they may not capture long-range dependencies or bidirectional context effectively. In contrast, XLNet maintains the autoregressive property of predicting words one at a time, but it considers the entire sequence during its prediction. XLNet achieved state-of-the-art results on a variety of benchmark NLP tasks, including question answering, text classification, and language modeling. Its ability to model bidirectional context effectively and capture long-range dependencies in text contributed to its success. In the next few lessons, we'll learn how to fine-tune an XLNet model for our own specific tasks. This is a powerful skill and will provide you with the knowledge of how we can use Hugging Face to fine-tune a large language model for yourself. In these next few lessons, we're going to see how we can fine-tune a model based on our own dataset. Our goal is to create a model that can take a piece of text as the input and determine the emotion of the text and return this emotion label for us. To do this, we'll be fine-tuning an XLNet model. We have a labeled dataset of a number of different sentences and their emotion label. We'll be providing this to the model so that it can learn these associations from our data. We'll then have a custom, fine-tuned language model of our own. So let's get started. The first thing we'll want to do is import the packages and functions that we need, so you can see the list that we'll need for the next few lessons here. We have the pandas package, NumPy, clean text, RE. From the transformers, we'll be importing the XLNet tokenizer, the XLNet for sequence classification, the training arguments, the trainer, and pipeline. We'll also import torch, and from sklearn we want to import train test split and the label encoder. We'll also need the datasets, evaluate, and random packages. So the first thing we want to do before we move on to any kind of language modeling is pre-processing our data. So let's load in our data first. We want to load in data train, data test, and data val. Let's then run datatrain.head to see what our data looks like. And yes, you can see we have a piece of text and an associated label. Let's concatenate the train, test, and validation sets together for now so that we can clean them up all in one go. So we'll use pd.concat over data train, data test, and data val, and ignore index equals true. We can then see we have some emojis in the text. We want to remove these. So we'll create a new column, text clean, and then we'll use the clean function over each of the pieces of text in our data set. We'll specify no emoji equals true to remove the emojis from this text. We also want to remove any punctuation from this text. So again, we'll update our data clean column, and then we'll use re.sub to remove any punctuation from this text. We can check this has worked by running data.head. And yes, we can see emojis have been removed and most of the punctuation has been taken out. There is some still left in there, so if you'd like, you are more than welcome to try and update the RE subfunction to remove any extra punctuation. Let's now look to the labels. We can print these out to check how many pieces of text we have associated with each of the labels. We'll take the label column and then do the value counts and plot it as a bar chart. So you can see we've got 4 emotion classifications here: fear, anger, joy and sadness. We can also see this is an unbalanced data set. We have a lot more occurrences of text with the label fear compared to sadness. So we want to make sure we have an equal number of pieces of text for each of our labels. So the first thing we can do is take our data and group it by the label. We then want to create a new data frame. And from this, we're going to sample based on the size of the number of rows in the labels. We'll take the minimum, and then we'll reset the index, where drop equals true. Essentially what this is doing is taking our data frame, grouping it by the label, finding the group with the least number of rows, so in this case that would be sadness, and then using that minimum value to sample from all the other labels. We can check this has worked by reprinting our chart. So data, label column, dot value counts, and then we plot a bar chart, and we can see we now have an equal number of rows per each label. We also want to convert our labels into an integer, so we can use label encoder dot fit transform over our label column. We also want to specify the number of labels as 4, as we'll need to reference this later. The final step in pre-processing our text is creating the training and test data. So first we'll create our train split and our test split using the train test split function from sklearn. We also want to create a validation set, so we'll split our training data set again and put aside 10% for the validation. Let's then print out the lengths to see how many rows we have in each of our splits. So we can see most of our data is going to training, some of it to testing, and then we've left a small sample for validation. We then want to format our data into a dataset dictionary. We also want to remove any columns that we aren't going to be using. So first let's create our train DF. We'll create it as a new pandas data frame with the column label, which takes our integer values for our labels, and a column text, which takes our cleaned up text. We can also do the same for our test DF. So from our test dataset, we'll be taking the label integers and our clean text. We then want to format these into a dataset dictionary. So first we'll take our train df and run datasets.dataset from dict and our train df. We'll then do the same with the test df. And from here we can create our dataset dict. We'll run datasets.datasetDict. And our train will be our train df, and our test df. Let's print this out just to check it's in the right format. Perfect, so we have our dataset dictionary split into train and test, both with the features label and text. We're now ready to create our embeddings. So to create our embeddings, the first step is to load our tokenizer. So we'll initialize the tokenizer and then run xlnet tokenizer.from pre-trained, and the model we're going to use is xlnet base cased. We'll then define our tokenize function. We want to return our tokenizer over our example's text. We'll set the padding to be the max length. And then set the max length to 128. We also want to specify truncation equals true. We can then apply this tokenize function over our dataset dictionary. So we'll create our tokenized datasets and then run datasetdict.map over our tokenize function and specify batch equals true. Once that is run, we can check our tokenized datasets. We can see we've been given a dataset dictionary with the features the label, the text, the input IDs, the token type IDs, and the attention mask. Let's go through and check some of these embeddings. So to start, we'll print a sentence from our data. We'll print tokenized datasets. From our trained dataset, we'll take the text and we'll just take the first occurrence. I then want to check how this has been converted into input IDs. So here we can see how this sentence has been converted into input IDs. It starts with a lot of number 5, so let's decode these just to check what they are. And yes, we can see these are the pad special tokens. Because we wanted to pad our data, these have been added to the start of the sentence to ensure all of our inputs are of the same length. Let's then check the token type IDs. So for the padded tokens, we can see these have been given a token type ID of 3. Our sentence has been given a token type of 0, and one of the special tokens has been given a token type of 2. You can now see how this helps the model distinguish what different things are, what different tokens are within the text that it's been fed. We can also see this with the attention mask. We can see all the pad tokens have been given a value of 0 because the model doesn't need to pay attention to these. The only thing it needs to pay attention to is where the ones are in the attention mask. So this is our sentence and our special tokens. Let's just take a sample of the tokenized dataset for a training demonstration, or it'll take quite a while to run. We'll take our small train dataset, and this will be from our tokenized dataset. We'll shuffle it, and then we'll just select 100 samples. The same for our evaluation dataset. But feel free to leave this step out or take a larger or smaller sample if you so wish. Now we have our training and test datasets prepared, we're now ready to fine-tune our model.
Fine-tuning a model is made easy by the Hugging Face package. To start with, we'll want to initialize the model. So we'll use XLNet for sequence classification, .from pre-trained. We'll want to take XLNet base cased. We then specify the number of labels we have in our dataset, and you'll remember we set this earlier, where we have num labels is 4. We then want to provide the ID to label, which is essentially the mapping of the numeric values to their label representation. Using the evaluate package, we can specify which measure of accuracy we want the model to evaluate when it's training. So we'll specify our metric and then use evaluate.load, and here we'll be using the accuracy. But feel free to use whichever method of accuracy you think would be best in your use case. We then need to define a function to compute the accuracy. So we'll define our compute metrics, and from this we take the logits and the labels. We can then use this to compute our predictions. So we'll use mp.argmax over our logits. And then we want to return our metric.compute, where our predictions equals our predictions and our references are our labels. This will compute the accuracy for us. The next thing we need to do for preparing to train our model is specify a directory to save our training hyperparameters. You can also use this function to add your custom hyperparameters. So we'll create our training args and then use the training argument function. You'll specify the output directory of where to save your hyperparameters. We also want to specify that the accuracy is to be evaluated at each epoch. So we can add evaluation strategy equals epoch, and we can also specify the number of training epochs. Here we'll specify 3. So now we've set up our training arguments and have a method to compute the accuracy of our training, we're ready to set up our trainer. So we can use the trainer function from Hugging Face. We want to specify our model, and then we need to provide our training arguments, our train dataset and our evaluation dataset, and our compute metrics function. We can then run trainer.train. This will train our model based on all the arguments we've set up in our trainer function. We can see that at each epoch the accuracy is being evaluated. And once this is finished running, we have successfully fine-tuned our XLNet model based on our custom data. The last thing to do is now just evaluate the performance of this model. Again, the Hugging Face package makes it easy to evaluate this model. We can run trainer.evaluate. This then provides metrics such as our loss, our accuracy, our runtime, etc. Let's say we're happy with this and we now want to save our custom model. You'll remember we can easily save models using model.savePretrained. We then just specify the directory of where to save our model. Let's now use this model for some more predictions. We've saved our model and now we can load it back in. So we'll run fine-tuned model equals xlnet for sequence classification.from pretrained, and then we specify our fine-tuned model folder where our model is saved. We then want to use the pipeline function with our fine-tuned model. So we're creating a pipeline and the task is text classification. Our model is our fine-tuned model. And our tokenizer is our tokenizer. Let's now run this pipeline over some samples from our validation dataset. First, we'll just specify a random number to take a random row from our dataset. We then want to print the text from this row so that we can inspect it . And then to get our answer, so our classification from the model, we'll use our CLF pipeline we've created over the text, and we'll specify top k equals none, so we can see the prediction scores for each of the labels that we've trained. We can then print this out. So you can see it's been printed our sentence and the associated labels and their scores. So we've successfully created a fine-tuned model based on our own data. In this course, you've learned a number of different ways to interact with large language models, and now you're able to successfully fine-tune a model for your specific task using your own custom data. I hope you've enjoyed this course and now feel confident and comfortable interacting with language models and starting to build large language model solutions of your own.
Hey everyone! Welcome to the Build Chat Applications with OpenAI and LangChain course. It's a pleasure to be your instructor and guide you through this journey of cutting-edge technologies. Let me begin by introducing myself. My name is Christina, and I hold a master's in theoretical physics from Lund University in Sweden. My passion for this subject is tightly intertwined with my interest in mathematics, programming, and ultimately data science. Since joining the 365 team, I've been involved in many intriguing projects, most notably creating 2 machine learning courses on the naive Bayes and k-nearest neighbors algorithms, and a data analytics course dedicated to analyzing student engagement on the 365 platform. Through these courses, I aim to simplify complex theories into digestible pieces and make data your friend with easily interpretable plots and visualizations. Now, I'll take you on another journey. Creating chat applications using the LangChain Python library and OpenAI's large language models. Let's start from the beginning. LLMs are models that can process human language and generate human-like responses. The large part in the name refers to the enormous amount of data these models have been trained on, and consequently their impressive number of parameters. But how large is large? Well, as the training data grows and models become more knowledgeable, the meaning of the word large adapts. OpenAI's GPT-2 model, released in 2019, is reported to have an astonishing 1.5 billion parameters trained on 40 gigabytes of text. We can't argue that these are impressively large numbers. But now compare them to the GPT-3 model released a year later, a model with a whopping 175 billion parameters, trained on 570 gigabytes of data, roughly the equivalent of 400 billion tokens. And imagine that even those are rookie numbers compared to the size and training of the GPT-4 model. So the word large is not anchored to specific numbers, but is an umbrella term for models of this scale. Well, researchers in the field can always take inspiration from the creative names astronomers give to their telescopes, such as large models, very large models, and extremely large models. But given the rate at which new and more capable models are released, I think we'd quickly run out of adjectives. All right, a subset of large language models is explicitly trained to hold a conversation. These are intuitively called chat models. An example of one is GPT, a generative, pre-trained transformer. If you've ever had a conversation with ChatGPT, then you've encountered OpenAI's chat model capabilities. This course will use the GPT-4 model to create custom chatbots. For a more in-depth discussion on the inner workings of LLMs and GPTs, I highly recommend our course, Intro to LLMs with Lauren Newbold. All right, but where does LangChain enter the picture and why is it a big deal? Let's start with what it is. LangChain is a framework that allows for seamless development of applications powered by large language models. Most notably, our focus throughout the course will be to create chatbots that are stateful, context-aware, and reasoning. Being stateful refers to keeping memories of past or ongoing conversations. Context awareness refers to answering questions about information outside the model's training data. And reasoning is the power to choose among various tools and their order of execution to solve a specific task. The use cases to which we can apply such chatbots are endless, but to offer some insight, we can find ones in web browsers for summarizing the most important of today's news. We can use them to query a database through everyday language. Build a multi-source fact checker. Or why not integrate a chatbot into the 365 platform to answer course-related questions? Once we solidify our knowledge of the LangChain library, we'll demonstrate how to build a 365 Q&A chatbot. Sounds cool, right? But now I want to spend a few minutes on intriguing, real-life use cases in which LangChain has played a crucial role. I'll see you shortly.